At the same time, it has to be also local in a way that, that it has to control the heat in a given location. So this is something we have done here, is we were looking at, can we look at fractal curves as a solution for this problem, where fractal curves, as you know, I mean, give a good blend of both local and global phenomena. Okay, so essentially what we have done is tried, for example, Hilbert curve, okay, instead of a zigzag or a area contour filling, etc. And we could see that the deposition or the distortion was almost 40% less. Okay, and this was across shapes and across geometries and across sizes also. Okay, so this was something approach which was independent of the geometry. It was holding true whether you have a circle, it was holding true whether you have a square, or holding true whether it is 100 mm or 50 mm, etc. Okay, because it is how the heat has to be distributed. It has to be distributed both globally across, but has to also accumulate in a local fashion. And that's why we thought, and here, I mean, so what you realized is fractal curves are like ideally suiting that requirement of heat balancing. So coming to the fourth part of the challenge is, again, as I said, how do we ensure that these are in constant manner and is in the I mean, similar properties are visualized. So I've done microstructure analysis, cut across the samples, visualized, etc. Okay, and what we have realized is, true, there are 100 layers, 100 different, each layer has a unique heating curve, a cooling curve, etc. But there is also a remelting phenomena happening every time. And this remelting phenomena is actually what is the final material you are looking. So you're not looking at as deposited, etc. You're looking at deposited, then material which is remelted during the deposition of the subsequent layers, etc. And hence what you realized is, does not matter what is the length of the component, etc. You look for the final parts, okay, how the cooling curve is changing, okay, and how the cooling curve is drastically dropping, where it is again, I mean, how it is in the recrystallization zone. So any component, what we have noticed is, it may be 100 mm, it may be 200 mm, it may be 400 mm. It is the final two layers and the starting two layers which have a distinct nature, because the base plate, because of high conduction, has rapid solidification, and the last layer, because of again high radiation and convection, has very high solidification rate. But the middle layers are what we call as resolidification phenomena, and they are showing similar phenomena or similar material properties across the first two 98 layers, essentially. Okay, that's something we have also noticed. The other thing what we have been also trying to do is how can we introduce the considerations and constraints of additive manufacturing into the topology optimization routine also. Okay, so this is something, for example, I mean, so for example, if you look at it, typically most topology optimization routines gives you shapes like this or like this, where, I mean, naturally they have a algorithm, but from a AM context, this lingering element or this small gap is a cause of headache, because it means more start and stop, more smaller features or discontinuity in the deposition. So actually, in practice, they create more problem than what the theory part of the topology optimization tells us. Okay, so can we add these constraints? Can we bring these constraints into the topology optimization routines itself? Okay, where these stray elements can be really, minimized. Okay, so this is something we have done in addition to the topology optimization course. Okay, so you can look that we have considered the neighborhood as a criterion, and we can see that all the stray elements or dot elements, etc., are reduced as a result. You can even see some of the other examples. Okay, so for example, let us say there are some small components. Okay, so here you see there are if you take the case 3, there are at least 34 voids or 34 small and big elements. And these look fine in a FEM analysis, but when you actually start fabricating them, they become a problem because of the continuity issues, because of the material minimum material resolution issues, etc. And they become actually a liabilities. So how can we reduce them? Okay, you can see that the number of voids or the number of start stops, etc., has been consistently decreased in the AMTO methodology. Okay, and so similarly, even how we can factor in even anisotropy also into the topology optimization. Of course, this is not in the context of metals. This is in the FDM case. Okay, but still, if there is an anisotropy, how can that also be factored in when you're doing the topology optimization? You can see that the 0 degrees and the 90 degrees, the results are drastically different in the output code. Okay, so these are some work which I kind of try to do and are trying to do in our place. Okay, so I think I will be to take any questions. So thank you.
Yeah, Professor Amitabh, please.
Thank you, Dr. Surya. Thank you, Dr. Chatterjee, also for a nice. Thank you, Dr. Surya, for a nice talk. And I think we have 20 minutes kind of thing. So we see that it is over in roughly 15-14 minutes. So we have some time for a few queries. So I think it is also being live streamed at this very moment. So if there are some questions, one can ask directly, or one can also put in the chat box. We can take, I guess, 2 to 3 questions.
I think we started early, so I tried to fit to my 20 minutes.
Yeah, no problem. No problem. Thank you. Thank you so much for that. Yeah. Let us see if there are some questions.
I think Professor Surya,
yeah, Dr. Chatterjee,
this is a technical discussion just for a couple of minutes. This fractal distribution, that is heat deposition in heat imbalances, reduces by approximately 40% when we are going in the fractal self deposition path, other than the conventional contouring, zigzag, etc., etc. I think this is a very important result that we have got. So had it been published, or you are showing it is under publication?
Yes, so we have communicated, we are waiting the review and publication.
So do you feel that when you are depositing in a fractal like pattern, instead of the zigzag contouring, your time is also increasing, I think, the operation time?
Technically, time does not increase because it is the path which is there, which is similar. The challenge, so the total material deposited remains the same, and the path of deposition and the time for deposition remains the same. What there is a challenge is how much is the cell width you take, because some machines usually fractals have a very drastic change in direction. Okay, so whereas zigzag flows continuously, and then you have there is a sense of continuity in zigzag, for example. Whereas in fractals, you have change of direction very frequently. So if the machine has a high inertia, okay, so that is something you need to factor on. You need to not go for very, very small size Hilberts, but you need to scale up the Hilbert size so that the inertia related issues of the machine will be handled. You want it to be spread, but you don't want it to be, otherwise it will end up more like vibration rather than Hilbert.
I think Dr. Maxim has a question. Dr. Maxim, please go ahead. It would be nice if you can kindly also introduce yourself when you ask.
Hello, my name is Хоменко Maxim. And I have a question on the same fractal laser cladding or metal deposition. You know, you will have more homogeneous heat distribution on the substrate using that Hilbert scanning. But what about the all that turns that you do? How about the heat preservation when you in that turnings? So how about that? How about the heat preservation in that scanning strategy?
Yes. So actually, heat reservation is what works in the favor of Hilbert, because if you try to visualize, for example, a contour, okay, so you go around the plate and you come back. By the time you come back for the second layer or the second pass adjoining, the adjoining first layer is already first pass is already very cold, okay, and that results in a large mismatch or a difference between what you are depositing and what your neighbor's temperature is, and that is what is resulting in higher distortions. Whereas, and vice versa, if you do it in a very zigzag and slowly moving in a continuous fashion, then what happens is the neighbors are cumulatively accumulating more and more heat. So the first pass, second pass, so slowly if you are doing in a continuous fashion, let us say zigzag, the difference between your previous pass and the next pass is small, of course, but it is accumulating and going on. All the heat is centered around one portion. Okay, so you need to spread the heat so that the complete base plate is in a fairly hot condition. But you need to also make sure that when you're doing a pass, the adjoining pass is comparatively at a similar, I mean, the thermal gradient is small. So that's why I said you need a combination of global and local phenomena. You need local heating mainly because, as you know, I mean, preheating helps in reducing the residual stresses. And you need global spread because you don't want all the heat accumulation to happen on one corner of the base plate and resulting in a distortion of the overall base plate. So you need a combination of spreading out the heat and also localizedly adding up the heat. And there, I think that's how it is.
Yeah.
Fractal curves are, and I mean,
Yeah,
beauty of the fractal curves are universal. I mean, they can be adapted to different geometries and scales.
Okay, thank you. I got it.
Yeah.
Thank you.
Okay, if there is no other question, thank you, Dr. Surya, very much. Nice to see you doing fantastic work. Please keep on doing so. Dr. Chatterjee, should we invite the next speaker now?
Yeah, sure.
I'm very sorry. I'm very sorry, dear moderators. I would like, before we give a floor to the next speaker, I ask your permission to introduce Professor Shkurinov, who joined us a few minutes ago. May I?
Yeah, sure, ma'am. Go ahead, please.
Alexander Shkurinov, are you here?
Yes, of course.
I would like to introduce you. Professor Alexander Shkurinov is a corresponding member of the Russian Academy of Sciences, Doctor of Physical and Mathematical Sciences, Head of the Institute for Laser and Information Technologies. It is a branch of the Federal Research Center, Crystallography and Photonics of the Russian Academy of Sciences, and Alexander Shkurinov is a professor at Lomonosov Moscow State University and the National Center Nuclear University MIFI. So, Professor Shkurinov, please, you're welcome.
Thank you for the introduction and for introducing me to our very interesting community that will join the conference today. And I'm really very glad to participate in the opening ceremony of this seminar today, all the day. will take place exchange of ideas and results on the very important field of modern technologies. Additive technologies is one of the future technologies which use the lasers and at the same time digital technologies. Because the digital technologies, it's really indication of the new results in the avionics, in marine science, in medicine, and I'm very glad to say that the institution of laser information technologies that I am managing, because I'm director of this institution, and these technologies, in the Laser Information Technology Institution are well developed, and we have future plans for the future development, and as well as in scientific and fundamental domain, and also in the technological domain, which may give a real apparatus for application in industry. Of course, from this point of view, today's seminar is really very important because it may give cooperation between two countries, Russia and India. And I visited India several times, and I'm always very excited with scientific results and the culture of this country. And I'm really, excited to say, crazy about making joint projects with Indian institution. I will be very happy if after today's exchange of ideas, where our two young colleagues will present recent results of their work, we may discuss also, maybe a little bit out of frame of the seminar, possible directions of scientific projects. I know that Russian Ministry of Science and Technology, as well as Russian Scientific Foundation, opens calls for joint projects between Russia and foreign funds, foreign institutions, as well as with the Indian institutions. And I will welcome any contacts and any future applications and joint works between our institution and with Indian partners. So I would like to say good luck to today and good success to today's event, and I'm looking forward for the results of the future cooperation projects. Thank you very much for your attention.
Thank you very much. And dear moderators, you may proceed with the next speaker.
Спасибо. Да не за что. Нас не видно, да? И не слышно.
Thank you, madam. Thank you, madam. I think and also thank you, Professor Stoyanov, for your nice and encouraging words to the participants here and also the organization. I think our next speaker is Dr. Andrei Samokhin from Bykov Institute of Metallurgy and Material Science. The topic of his presentation would be DC-arc plasma spheroidization of powders for additive manufacturing. Professor Samokhin.
Yes. Good afternoon, dear colleagues. I'm greeting all participants of this webinar. I hope that everyone will find something new or interesting today. And I think that we all understand that additive technology now is an important part of modern industry at all. So a lot of scientific institutes all over the world carry out some investigation in this area. And of course, our institution of metallurgy and material science have some experience in this direction. And first of all, in area of materials preparation for additive technology. And in my presentation, I would like to introduce some latest R&D result of our laboratory in the area of thermal plasma spheroidization of powders for additive technology. And now I should open my presentation. Demonstration screen. Okay. Do you see it?
Yes, it has come now.
Okay.
Yeah. Please go ahead.
So high quality powders are used with great efficiency in various additive technology. First of all, this is selective laser melting, selective laser and electron beam laser melting. Of course, direct laser metal deposition however, the field of use of high quality powders is not limited only additive technology. Such powders are also used in a number of other high-tech industries. For example, hot isostatic pressing, plasma spraying, spark plasma sintering, metal injection molding, and so on. So the production of high quality powders is a really actual and important task. When we are talking about high quality powders, we mean a set of certain characteristics. It's first of all spherical shape of particles, proper particle size distribution, high level of fluidity, bulk density, chemical homogeneity, reduced content of gas impurity and oxygen, first of all, and lack or absence of porosity. There are four key methods for producing production high quality powders. It metal melt inert gas atomization, it's metal rod rotating spraying, it's metal wire plasma atomization, and metal powders plasma spheroidization. This is an area of our interest, and we used, I should say that in processes of plasma spheroidization, there are used another kind of plasma generator, plasma sources. It's radio frequency torches, microwave torches, and electro arc torches. We used, in our investigation, we used only DC thermal plasma torches. And here, short description of the processes.
I'm sorry, we can see only your first slide.
Why?
Can you make your presentation mode, Professor Samokin? Can you make it in presentation mode?
One. Can you see the first slide? Second slide.
Yeah.
Yes.
Yeah. Second slide about application of spherical powders.
Yes.
Then requirements of powder for additive technology.
Yes.
You can see that.
Methods, and now scheme of plasma processes. Yes.
Yes.
Do you see?
You can see that.
And I continue.
Yeah, please continue.
Okay. The plasma jet flows to volume of plasma reactor. The powder, precursor of powder, injected to the plasma flow, particles heated and totally melting. Due to the surface tension forces, the resulting liquid droplet become spherical. After cooling, particles collected in the bottom part of the reactor. The powder consumption in our processes is in the rate starting from 1 kilogram per hour and up to 10 kilogram per hour. And power consumption for plasma torch is in the rate from 20 to 50 kilowatts. We use different gases for plasma forming gas. First of all, it's argon, argon hydrogen, and argon helium mixtures. This is, you can see some scheme, technological scheme of plasma aspheroidization system. It consists of following components. It's plasma torch, reactor, filter, apparat of filtration, technological gases, powder feeder, and some system for
Professor Samokin, the slides are not moving. You have to go to the next slide.
Why? I don't know why.
I think you have to go to the presentation mode. Right now you are putting slide by slide. So if you put on the presentation mode, it will move as you press.
Excuse me. One moment. Do you see scheme, technological scheme now?
No, no. It is still the spheroidization process.
Spheroidization process.
Yeah.
There. Now. Not?
No, it is not.
Why not?
I'm sorry. Have you used F5 for your presentation?
I push the button F5, and now I hope you can see some slide with technological scheme. Yes or no?
I guess that the problem is with the Zoom. When you use the demonstration of your screen, you have to, I guess, show the whole your screen, but not only the presentation. That's why the problems.
Уважаемые коллеги, мне кажется, надо выйти из режима показа, включить F5 и опять войти в демонстрацию экрана.
I try to do that. Так, остановить демонстрацию.
Включить F5 и опять включить демонстрацию.
F5 и демонстрация экрана. Так. One moment, I'm sorry.
Yeah, this is okay now. This is good.
Yeah. And now you can see technological scheme. Yes, I'm very sorry for that. I stopped on the support system for all plasma system. It's power supply, some control panel, gas, vacuum, water cooling systems for operation, correct operation, all the system. We have carried out plasma aspheroidization of a large number of powders. They include metals, alloys, inorganic compounds, and composite materials. All powders have significant differences in their properties: melting temperature, particle size distribution, morphology, and so on. We have achieved a high level of particle spheroidization due to the correct set of process parameters and reactor design. On the following slides, you will see the most representative results of our investigations of the process the process plasma spheroidization for different materials. And here on this slide, you can see the titanium particles morphology before and after plasma spheroidization. You can see that high level of spheroidization treated powder, narrow particle size distribution, and a non-porous structure had been reached. What should I say? We used titanium powders for treatment that has been that was prepared by method of dehydrogenation of titanium. So morphology of this powder is very difficult for spheroidization. Plasma spheroidization of tungsten particles was interesting for us because of high melting temperature of these materials. But results of processes is great. You can see all the best of all particles have spherical forms. Some of them have small pores, but their quantity is not critical for their application. For application this powder. So our colleagues told us that quality satisfied them. Heat-resistant nickel alloy powder, which we use for spheroidization in this case, was produced by the method of self-propagating high-temperature synthesis. The initial particles, you can see, have a very complex morphology, irregular shape, and high porosity. As a result of, you can see the section of the particle here, and you can see the pore on the picture. As a result of spheroidization, the particles get spherical forms and doesn't have porosity, some porosity. Samples for mechanical testing were made from this powder in 3D printer. The high quality of obtained materials has been achieved after short investigation of the regimes of melting this powder in printer. Spheroidization of iron powder was interesting for us because of the complex morphology of particles produced in the processes of iron melt water atomization. In the result of investigation, we have determined the process parameters that allow us to obtain a high quality powder. Samples for mechanical testing were made from this powder in 3D printer, and the high quality of obtained material has been achieved. What to say? Powders of high temperature solders on the base of nickel alloys are interesting object for us due to requirements for high fluidity of the powder and the need to preserve the amorphous structure. As a result, we have got high degree of spheroidization, you can see, and fluidity, of course, this powder. And what's important for us, amorphous structure of the particles was saved because of the fast cooling of the particles in plasma reactor, because high velocity of plasma flow and long distance in reactor with cooling, water cooling valves. So the resulting particles, spherical particles, reach the bottom after solidification and after cooling. We have some positive results in spheroidization of oxide powders. Here you can see two samples of three components of oxide oxide system with different melting temperature. These particles, we use fraction less than 10 microns, and the result is pretty good. You can see only spherical particles we've got in this after the treatment particles. We produced a fully spheroidized powder of tantalum oxide with a particle size in the range of 25-50 microns. The powder has a high degree of fluidity. We have demonstrated the possibility. We have experience in the manufacturing of spherical composite powder materials. You can see the morphology of the composite particles, powders, composite powders on the base of nickel alloy and oxide nanoparticles. The concentration of oxide particles is near between 1 or 15%. This powder was made with some grading mill. We can see that particles uniformly distributed in the volume of the materials. And after spheroidization, we've got the high level of sphericity of the particles and high level of distribution of nanoparticles of oxide in the volume of metal matrix. Okay. We have demonstrated also the possibility of producing composite tungsten copper micropowders consist of spherical particles with microstructure. When I speak microstructure, I mean grid size around 1 microns, one micron, more or less. And we've made these powders on the basis of following three-stage approach. The first, plasma chemical synthesis of tungsten copper nanopowders with mean size near 60 nanometers. Then we use spray drying of the suspension on the base of these nanoparticles and product granules, microgranules with mean particle size near 35 micrometers. And all these particles consist of nanoparticles. You can see on this picture. And the last stage is plasma spheroidization of that granules. You can see the results, and the average diameter is near 25 microns. And the structure is very equal, and copper distributed very homogeneously through all the structure of particle. We have demonstrated the possibility of producing composite micropowders on the base of zirconium diboride and silicon carbide. This powder consists of spherical particles with micrometer structure. As a precursor for this process, we used micropowders, which was made by method of self-propagating high temperature synthesis. And again, we pay attention to homogeneously distribution of silicon carbide through the structure of the particles, and you can see that high level of distribution. In this slide, in this place, I would like to say some words about the limitation of the powder's plasma spheroidization processes. You can see this limitation in this place. And by my mind, the more serious problem concerns the presence of nanoparticles in the spheroidized powder. And in this part, you can see some results of the presence nanoparticles in micron size powder. So I can say that results no good. The formation of nanoparticles accompanies all process of plasma spheroidization of powders, regardless of the type of plasma touch. This occurs due to the evaporation of the smallest particles during their heating at the high temperature of plasma flow. And the further follows the condensation of the vapor in the form of nanoparticles. Content of nanoparticles in a spherical powder can vary from 0 to 10%, depends of some technological parameters. And here on these pictures, you can see how it looks. 2.5 mass percent of nanoparticles, and here's this picture, this powder after removing nanopowder. In this case, 5% of nanoparticles and powder after washing. We wash the powder into the water suspension under ultrasound treatment. It's very easy and quickly. This information on this slide may be interesting for those who work on 3D printer, and I even say hard work on 3D printers with big quantity of the powders, because it's well known that the more cycles the powder is used in 3D printer, the worse its quality becomes. I mean, increased the oxygen containing, getting worse the morphology of powders, and so on. The plasma sterilization method can be used to regenerate the powder. I mean, restore its properties to properties of virgin powders, or closer to virgin powders. It was because we use a hydrogen-containing plasma-forming gas, and after that, oxygen impurities in the powder are reduced. You can see these places up to 3 times, as we get with regeneration powders of alloy, cobalt alloy.
Professor Samokin,
yeah.
may I remind you that, time limit.
So 1 minute, only 1 minute, excuse me.
Sure.
The experience which we got during the study of plasma sterilization process allowed us to develop and manufacture the base design of plasma setup. The productivity up to 10 kilogram, it can work with different powder fraction, with different gas and gas mixtures. We use some system improve quality of the operation of this system. And during the past 5 years, we have developed and manufactured 4 plasma sterilization systems. Each sample, as you can see, was superior to the previous one in productivity and efficiency. And finally, thank you very much for your attention.
Thank you. Thank you, Professor Samukin. It was a very nice presentation, I must say. Very interesting talk, because we crossed the time limit and we have many presenters. We can have one question from the audience. If anyone has any query, please. I don't see any hands raised. Is there any query from anyone? We can take one question.
Excuse me, please.
Yeah, please go ahead.
Excuse me, I don't understand even what you mean.
No, I am just asking if anybody has any question from the audience who are listening. So I'm just opening it for discussion.
Yes, I'm ready to discuss all concern our system or our technology.
Professor Day. May
please.
I come in?
Sure.
I think we can go for the next speaker.
Okay.
And if anybody has any question, we can discuss it during the panel discussion. Okay, because we have some time constraint also.
That is correct.
So let us. You please invite Professor Pandey now.
Pandey, yeah. We can request. We can invite Professor Pandey. Professor Pulak Mohan Pandey, Director, Bundelkhand Institute of Engineering and Technology. Professor Pandey, would you like to come?
Yeah. Should I start now?
Yeah, please go ahead. Yeah.
Okay.
If you wish, you can, introduce yourself.
Okay.
Yeah, please go ahead.
Yeah, so very warm welcome to this webinar, everyone, especially our friends from Russia and my friends from this place, our country. So I'm Professor P.M. Pandey, and I'm working in the field of additive manufacturing for around more than 20 years or so. And I did my PhD in the area when people used to call these technologies as rapid prototyping. So I worked on fused deposition modeling in my PhD. And afterwards, when I joined IIT Delhi as a faculty member, I had an opportunity to work on selective laser sintering process. So very fundamental issues about selective laser sintering process, which are related to, developing software support for it. Because what personally I feel that it is the software which can control so many things, because the success of any additive manufacturing process depends on the digital model which is being created. So the digital model, if it is having inconsistencies, if it has inaccuracies, the same will be added, and finally it will be reflected on the quality of the product. So it's the geometry, it's the parameters, which may be the laser parameters, which may be the parameters related to controls for having, when the laser spot is moving, for example, if it is, how much is the hatch spacing, how much is the speed of scanning. There are so many parameters, like what happens, and these parameters vary from process to process, and the kind of deposition technology which is being used in a particular AM technology. So like the contributions, if you really see the research direction in this area of additive manufacturing, you are realizing, rather you will realize that it's the geometry which is very important, because even today, if you see, it's the accuracy and it's the surface quality which is the drawback and the bottleneck of these technologies. Now coming to the strengths that was supposed to be one of the bottlenecks, typically if we consider the direct plastic sintering kind of processes, which is quite inferior as compared to if we try to develop the component using injection molding kind or compression molding kind of processes, you will realize that there was a lot of problem in the strength. But with the lot of development which has taken place for the metal manufacturing or the metal additive manufacturing, today it is the time when we are having the rapid manufacturing processes, or maybe the laser metal deposition kind of processes, which sometimes we also term as direct energy deposition. We have solution today that sometimes when you optimize the process parameter or you select in a very precise way, you can realize that the strength which can be obtained in various processes is as good as forged components. Now today it is the time. There's another domain, like I was just listening the talk by Professor Samukin, and I could realize that there's a lot of focus in developing spherical powders, the perfectly spherical powders for lasers for the various AM processes. Now I'm going to demonstrate to you a few of our recent, very recent research attempts which we did at IIT Delhi, and we also had the patent on those processes where the spherical metallic powder, typically the iron powder, has been utilized, and we could achieve a pressureless sintering and create very complex components of pure carbonyl iron powder as well as the copper powder. So I'm going to share my screen, and let me see that my presentation may not be very long, because let me just share my screen. Yeah. Okay, so so my screen has been shared, I believe.
Yeah. Please go ahead.
Yes, so the title of my talk is Development of Rapid Manufacturing Processes for Fabrication of Customized Scaffolds and Implants for Orthopedic and Cardiovascular Applications. So thank you once again for giving me this opportunity to talk to you. So, talk about the process which is about the porous biodegradable iron implant using 3D printing and pressureless microwave sintering. So here, what we did, like the idea is to have very fine surface quality and also to have accuracy. These are the major problems as far as the geometry is concerned, whether it is a powder bed based process or it is a powder blown process. In both the cases, you will realize these are the bottlenecks. So here we did the CAD model, and we created the template using stereolithography. The stereolithography can give you quite nice finish and accuracy too. And then this is with some typical materials which we developed at IIT Delhi, and we could develop a mold. And this has been inserted in this particular material, and then we have taken this to a furnace where this particular material is being vaporized. It is some sort of a sublimation kind of a process, and we could get such a complex cavity. Now this particular complex cavity is being filled with the carbonyl iron powders, and these are the spherical powders which we have imported from one of the leading countries, and afterwards this is being microwave processed. So we are getting this kind of very complex scaffolds. Now in this particular diagram, you can have a look the different geometries, like we had CAD designs and the unit cell which we have selected, that is based on the variety of geometries depending upon the literature, which tells about the kind of geometries which suits nicely for the various implant and scaffold applications that we have taken, and the sizes have been developed, and you can see the kind of perfect geometries which we could produce with a, and here we did the kind of fitting, that is the fitness, or you can say tolerance testing, and we could establish that the tolerances of the order of IT16, that is a IT16 grade tolerances we could achieve. And this is a case study where this particular, scaffold, which is developed using this technology, that has been fitted to this human skull. Now, why this geometry? Now the question comes, why this kind of geometry, and why this biodegradable material? Now, iron is a constituent element of human body, but it is toxic if you take it, a lot of dose if you take. So what we do, and there's another problem with this material, is the stress shielding problem, that when we are putting it in the human body, you'll find there's a stress shielding problem. These two challenges we have to meet. Now you have to increase the biodegradation rate so that the biodegradation rate matches with the degradation of with the bone growth rate. That is one thing. And second, you have to solve the problem of stress shielding. Now these two problems have been handled very nicely with these kinds of designs, and this is a diagram, I believe, that this talks about the degradation. Now this corrosion or degradation studies have shown that we are able to improve the degradation rate, and if you refer the paper in the matter, you will find out that the degradation rate is of the order of bone growth rate in this case. And we could also see this, do the biological studies where we try to perform the cytocompatibility assay results, which clearly indicates that there's some toxicity, but this toxicity is also within the permissible limits. And when you keep on do the dilution as the blood keeps circulating in the body, you will find that this is not there. So these results are very much validated at AIIMS New Delhi. Now let me talk about another similar process which we developed at IIT Delhi. Once again, because the idea was that to bring more consolidation, to improve the density of the components, and also you need to develop sometimes a heat sink or a heat dissipating body, and you want to have something which we call as some sort of shock absorbing body or scaffold. So here copper is a material. Now copper is a very problematic material as far as additive manufacturing is concerned, as far as the powder bed fusion technology is concerned, or maybe even the powder blown technology is concerned. It is very reactive, susceptible to oxidation, and there are many other problems. Very high heat conduction is another trouble. Now here, what did we do? We created our, this printed model using stereolithography, created a mold, burnt out the mold by doing it by heating it and sublimation process, and then we filled the copper powder, spherical copper powder in this cavity. And then this is again a new process which we have developed. Here, it is an ultrasonically assisted, vibration assisted, sintering. So this is the complete horn design which we did. And after that, with the FEM adjustments, because you have to, when you're putting your crucible, you will find that there's a problem in vibration, so that we manufactured the horn. And there's a cooling arrangement also for the horn. There's a cooling jacket. And afterwards, in this tubular furnace in an inert atmosphere, we could sinter the material, and we could provide this very, very complex, shaped components. And this is the powder geometry. And we also studied the model, basically the neck growth kinetics. So these are the two very recent attempts which we did at IIT Delhi. Now, before moving to this, let me talk about another very interesting attempt we did. That is the acoustic liquid manipulation assisted jet electrochemical microdeposition. Now here, it's very easy to understand that if I am having an electrochemical jet and it is a high-speed jet, if I put it onto the proper substrate with the proper combination of electrolyte and maybe something else, with the cathode anode combination, you are able to deposit the material on this substrate. Now there are problems of hydraulic jump, and when you try to deposit the material and you move this, electrolyte jet or maybe the table on XY platform, you will realize that this is the problem, which is called edge effect. Now this problem of edge effect, that was a challenge before us, that how to handle this problem. And this problem was resolved by superimposing the ultrasonic energy or the waves on this moving jet. And what we could see is that there are very few papers which we obtained. This idea was derived from one of the papers, very basic fundamental papers published by NASA, where they have developed some sort of convex head or the vibrating horn, which could focus the mechanical waves, and they could make it. So I am having certain ideas in this direction, and if possible, I would like to collaborate in this area. So here, this edge effect was eliminated when this particular mechanical waves are superimposed on this thing, so we could get a continuous structure like this. Now afterwards, like when we supplied a DC, DC current or a DC voltage we applied to this shell, electrochemical shell, we realized that there's a larger grains. But when we went for nano pulse DC, which the equipment which I got personally fabricated because of some other work we tried to introduce here, we realized that we are able to create nano structures. So here the important point which I would like to mention is that I can make a micro-sized component, ensuring all 100% nano grains in that particular nanostructure. But the limitation is, once again, you have to take a proper substrate. There has to be compatible electrolyte combination so that you can, get such things done. Okay, now let me come back to this. That is a biodegradable polymeric cardiovascular stent. This is a very new work. We have developed our own 3D printer in IIT Delhi lab, and this is the rotating mandrel. Now on this rotating mandrel, using the solvent cast process, we have developed our own ink that is a biocompatible and biodegradable ink. This is being synthesized for a proper rheology and proper viscosity conditions, and we could extrude it on this particular rotating mandrel, which is only 1.5 millimeter in diameter, and different CAD models can be created. And once you rotate and deposit, you are able to make this kind of stent. So different standard designs of the stents were created, and we tested these stents for radial compression test and bending test, and we could see that they qualifies the ASTM standards in the area, and this is the stent behavior during ballooning. So when people perform angioplasty, they undergo this kind of system. So we collaborated with the AIMS, and we did this thing. We did the ballooning, and we could establish that they can undergo those kinds of loads and pressures. Then it's not only this. We did the biodegradation study too. So here we did the biodegradation study. We took we mimicked this kind of function of heart, and at a 37 degrees Celsius in a phosphate-based solution, the stent were placed, and we could see the, there's a dynamic degradation, as well as we did the immersion test. And we also performed the test on, biological test for the cell morphology, cell growth, and also having the presence of dead and live cells on these particular, developed stents. So this is something, which I want to tell. But before that, before I really finish, this is another important. So Professor Avik, you may stop me when the time is over. So this is the clubfoot correction. This is another very interesting biomedical application we did around 7 years back. So if you see these are the kids which are born with these fit twisted inward like this. So this is called club fit or club foot. If it is in two, then we call it club fit. Now this defect is being there are a number of ways, but the most popular way to rectify this problem, to treat this problem, is by morphing the geometry. That is called Ponseti method. And here a orthopedic surgeon puts plaster and changes the plaster every 7 to 10 days. And after 7 to 8 iterations, the surgeon is able to morph the shape of this human kid to the regular shape or the actual shape, the correct shape. Now, for doing this, we developed these. We took the MRI scans of these newly born kids, and we created these silicon rubber models. Definitely, we have to use the additive manufacturing concepts. And after that, we developed this orthosis rather than going for because plaster has several problems. So we developed this clubfoot orthosis, and we did the finite element analysis considering the bone properties, because in the beginning these bones are cartilages, and we could perform the experiment on these these clubfoots, and finally this orthosis was made successful by these clinical trials which were conducted at SGPGI Chandigarh, and within a week's time we could rectify this defect on the human foot. Now, in continuation to this particular, this particular clubfoot orthosis, we also developed this instrument, we can see, which is to measure the deformity. So this instrument has 7 scales. You can see here scale 1, 2, 3, 4, and there's a 7th scale. Now this particular instrument can be put on the baby foot, and you will get these numbers. So you will have an assessment that what is the deformity. And later on, when the correction is taking place, one can, understand, because the numbers will be changing, you can have an assessment of how really the things are changing. Now, let me go to my last slide for today's presentation. So this is a very interesting and classical work, I consider, because the bottleneck of these processes is to control the shrinkage, to control the dimensions, to control the tolerances, and to control the geometry and surface quality. So here, this is an attempt where a non-homogeneous shrinkage compensation methodology was developed. And what we do, generally in additive manufacturing, the shrinkage factors are applied on the various directions, that is X, Y, and Z directions. But here, at every dexel level means if my laser is moving like this, if my laser spot is moving like this, then only on this volume I am going to apply some correction factor. And on the second dexel, I am going to apply another correction factor. There are models developed for these correction factors, and so everywhere there's a different correction factor. So that's why it is a non-homogeneous. We developed a software and the common layer interface file that has been modified, and we could show for this NAS part. This is a NAS piece which is used to establish the accuracy in the components. So with our method, we could show that with flexible scaling, our parts were much accurate as compared to the rigid scaling, which is even today. Now, if you really see today's state of the art, people have tried to locally apply the shrinkage compensation. Even the people have not gone up to this level. And then we have also made methodology where the finite element has been taken as an input. And at every layer, we are able to, modify different properties, process parameters, so that we are able to create a functionally graded material in case of DPLS components. So with this, I thank you everyone for giving me this opportunity and for your patient listening. Thanks a lot.
Thank you, Professor Pandey. Very nice talk, especially we could realize several areas of application that you have and looked into. Very nice talk. In case anyone has any query, we can have one query at least. Please go ahead. I don't see any hands raised. There is no query. So thank you, Professor Pandey, once again for such a fantastic talk. Yeah.
Thank you very much, Professor Day. And it is, I really wanted to be here full time, but I have another commitment. So I have to move to Lucknow to meet Principal Secretary. So I'll be leaving now, but definitely I would love to be in touch with this group, because this additive manufacturing is something that remains in my.
Yeah. Thank you. Yeah, sure. I think
thanks a lot.
I am requesting Dr. Chatterjee to kindly note this. I know Dr. Professor Pandey is very busy, I know. So I'm not surprised that he has to go somewhere now to meet someone.
Yeah.
But I am requesting once again Dr. Chatterjee to note his interest to be in touch with this.
Sure.
Thank you very much. Thank you.
The recordings of the webinar are live, sir, and they'll be recorded and kept on YouTube. So Professor Pandey can see it later also.
That's correct. So without any further delay, can we invite Professor Aliumov from his director, if my pronunciation is correct, Marchanov Institute of Structural Macrokinetics and Material Science. Professor Aliumov, please.
Thank you, colleagues. Thank you for opportunities to take part in this conference. May I make my presentation? Yes.
Professor Aliumov, can you kindly go into the demonstration mode?
Yes. One second. Excuse me. Нужно вот войти, да? 1 minute. 1 second.
Sure. No problem.
Прошу прощения. May I speak Russian for a moment? I'm sorry.
Yes, please.
Sure. We are waiting.
Вы не могли бы сначала убрать демонстрацию экрана, как это сделал вот российский предыдущий докладчик? То есть вы сначала выключите демонстрацию экрана, потом нажмите F5 для показа слайдов, а потом уже демонстрируйте ваш экран.
Хорошо. Сейчас. Массаж экрана будет включить.
Прошу прощения. Мне кажется, вы не нажали F5 в презентации.
Сейчас видно?
Да, все видно.
Все видно, хорошо?
Видно, но не полный экран. опять.
Полный экран, да?
Хорошо, пусть будет так, ничего страшного. Давайте так посмотрим.
My presentation concerned with self-propagating high-temperature synthesis, SHS, metallurgy of heat-resistant alloys and granules from them for additive technologies. Between introduction and conclusion, I would speak about production, alloy production and granules from them, and the properties of the SHS metallurgy process for production heat-resistant alloys, some cooperation and equipment for research, and examples of alloys and granules of them. To develop a new generation of engines, it is necessary to create new alloys with a large level of performance and technologies for their production. The most promising technology for manufacturing parts of gas turbine engines with a shape close to a final form are additive technologies of selective electron beam melting, a selective laser melting. Powders of various dispersity particle size distribution are used for these technologies, and Dr. Samokhin said about it. However, the spectrum of new alloys is very small. This report discusses the results of a new approach to solving the problems, including the production of new cast heat-resistant alloys by centrifugal SHS metallurgy and subsequent production of powders from them. This report reviews the results obtained by the Office of Report with colleagues and partners over a number of years. Here you can see the in the first stage we produced ingots by SHS technologies. After that, we remelted it to cylindrical rods. It means electrodes, and these electrodes atomized to spherical granules. About the developing the SHS metallurgy used for synthesis high exothermic mixtures of metal oxide with active metal oxide with active reducing agent and non-metals. Such mixtures can burn. Combustion products are carbides, barytes, silicides, metal oxides, and composite materials on their basis. The temperature of the combustion mixture can exceed the melting temperature of the final products. In this case, the final products are obtained as cast. Here you can see the 3 steps of SHS process. First stage, combustion. Second stage, gravity separation, metals and oxide fast. And the third stage is cooling and forming of a crystal structure. This is a main slide of this presentation. Initially, we have initial mixture of powders. In the first step, we ignite it, and we have a combustion process. Here is a boundary between initial mixture and combustion products. Here, this combustion process consists of oxide phase and metallic drops. So we have to make only metallic drops. So we used gravity separation. Gravity force is in these directions, and metallic phase with more density moving to the bottom of this vessel, and oxide phase is on the upper part of the vessel. And the second stage, cooling and formation of crystal structure, we have metallic phase and oxide phase in the upper of the vessel. And in this slide, SHS metallurgy carried out in the reactors or centrifugal installation under effect of high gravity. The reactor is here and is here. Acceleration is from 1 to 50 G. G is the free fall acceleration. Mass of a mixture differ from 20 grams to 1 kilograms. In this centrifuge, acceleration is up to 500 G, the free fall acceleration. The mass of mixture is near 1 kilogram. Here you can see some results about nickel aluminum alloy. For the synthesis of alloys on the basis of nickel aluminum with alloying additives, chrome, cobalt, titanium, molybdenum, a mixture of oxides, and aluminum was used. The combustion temperature of the mixtures is more than 3000 Kelvin, and the acceleration is significantly different. This makes it possible to realize high output of a target product in the ingot and produced cast alloys based on nickel aluminum. Integral chemical composition of ingot is close to a calculated one. Calculating composition, experimental composition. Microanalysis showed that the nickel monoluminide forms the basis of an alloy, and cobalt chrome solution forms boundary. For the chemical scheme for obtaining titanium, aluminum, and niobium chromium alloy with niobium chromium alloying agent is represented in this slide. The initial mixture for production of the alloy comprises a base mixture, alloying agent, and energy additives. In this way, we could expect to raise combustion temperature to 2,500 degree centigrade. Here you can see some results concerned with cast alloy, cobalt, chrome, niobium, tungsten, molybdenum, aluminum, and carbon alloy was obtained from a mixture of oxides by centrifugal SHS metallurgy. According to the data of spectral analysis, electron microanalysis, and X-ray diffraction phase analysis, a matrix is formed from a solid solution with a cobalt lattice in which finely dispersed particles. Next results concerned with niobium silicide based alloys. It was shown in the experimental that hafnium actively participates in the reduction of niobium oxide, which complicates its introduction to the alloy. The replacement of hafnium by aluminum hafnium reduces its activity and decreases its content in the alloy to 6%. In the joint studies with Messi, Sisman, Composite, the new technologies for these alloys was developed. Technologies includes production of ingot, production of electrodes, cylindrical electrode, and centrifugal plasma atomization of casted electrode. Here you can see technological centrifugal installation. Possibility of this centrifuge allows to burn mixture with mass to 5 kilogram, and acceleration is very high to 400 G. Technological this technological centrifuge give possibility to produce up to 200 kilograms cast alloys for subsequent manufacturing of electrodes. Pilot batches of these alloys and their chemical compositions are presented in this slide. The remelting of SHS product produced titanium and titanium aluminum ingots was performed in vacuum induction furnace at these temperatures. The melt was cast into a steel mold heated to 700 degrees centigrade to obtain a cylinder with mass near 15 kilograms. This it will be electrodes. Here you can see such electrodes. You can see that chemical composition before remelting and chemical composition of structure after remelting is very close. It's very famous, very good result. Installation, last step is atomization with cylinder electrodes to produce powder. Here you can see working camera, plasmatron, electrode, and electrode is wearing. After we can obtain powder in this chamber. The installation for preparation of spherical granules by centrifugal plasma sputtering of electrodes shown in this slide, where installation includes systems for control of electrode rotation, plasmatron for electrode surface heating, and working camera where granules are accumulated. Where here you can see the view of granules is given in this slide. The structure of the granules you can see in this slide, and conclusion: the integral technologies, including SHS metallurgy for heat-resistant alloys and production of granules from heat-resistant alloys, will to obtain a wide range of granules from refractory compounds and composite materials for solving problems of additive technologies. Now, here you can see our international journal of self-propagating high-temperature synthesis, and some results were published in this book, and last year we have this book, and you can read it more. Thank you very much for your attention. Now I'm sitting in this place. Thank you.
Yeah, thank you, Professor Alimov, for this beautiful and informative sharing this information. And it is the granules of heat-resistant alloys. So this is a very important area, and of course we are very much interested in that. Okay, and since we are lagging some time of around 10 minutes, so I think we can entertain questions during panel discussions. So let us quickly go to the next speaker. So once again, my thanks to Professor Alimov for your informative presentation. So our next speaker is Dr. Biswas R. Putiji. Dr. Biswas, you are here?
Yes, sir, I'm here. Am I audible?
Yeah, you are audible. Yeah. Now we can see you.
Right.
So we all know that role of industries are very important in this emerging area and developing area of additive manufacturing. So we have a industrial partner from India. He is Dr. Biswas R. Putiji. He is business head, MS Solutions Private Limited, Bangalore. And he will share that some of the recent advancement in metal additive manufacturing in India. So I think Dr. Biswas, you can proceed and share how industry can be joined or industry can be collaborated and what capabilities and facilities you have.
Yes, sir. Is my screen visible?
Yeah, screen is visible.
My slides are visible, right, sir?
Yeah.
All right, great. So first of all, I'd like to take this opportunity to thank the organizers for giving us this opportunity to present to this elite gathering. So we are Amaze Solutions. We are a part of ACE Micromatic Group. I've gone to the next slide. I hope it's visible. Just wanted to reconfirm.
Yeah, visible.
Fantastic. So ACE Micromatic Group is a machine tool group from India. We've been in the industry for 40 plus years now, making conventional machines, CNC machines of different types. So you can see some of them are here right now, which is CNC turning machines, grinding machines, CNC milling solutions. We have automation solutions. We make tool turrets and automatic tool changers. And of course, IoT solutions also. So one of the newer entrants. So additive manufacturing for us came in as a complementary technology from the parent company. So way back in 2015, we decided to start researching on this subject. And then what started off as an R&D project in one of the parent companies ended up getting spun off as a separate entity early 2018. So for over 4.5 years now, we've been working on additive manufacturing in different arenas of metal additive manufacturing. So today, I'd like to present some of the activities in this. But before that, just to give you a perspective of what we are and where we are, these are the different places that ACE Micromatic is right now present. We have either our own presence or through our dealer partners. We are present in multiple of these countries, and Russia is a very good market for us. We've collaborated with a company called Ural Pomori, who represent us, with whom we develop products, and we also cater to the Russian requirements of all types of products, milling and turning and grinding machines, and many other countries. So since this is a Russian forum, we thought we should bring that to the notice of our friends from Russia too. So moving ahead, Amaze Solutions is basically a joint venture between ACE Designers and ACE Manufacturing Systems, the milling and the turning company. Basically, we call ourselves as the additive manufacturing wing of ACE Micromatic. So we have two separate sections of the company. One is to provide services, which means we print parts in metal for different applications, and we meet the requirement of customers for different metal printing requirements. And we also have the larger team to develop machines, to produce machines. So this is the two segments. So that's what we've been doing. But just to give you a narrative of where India stands today from a perspective of additive manufacturing. So India is a fairly good market. We have good, so pardon my conversions, I missed converting this into US dollars. in terms of where we are. This is about $100 million in numbers in terms of where India stands from a additive manufacturing market. This is purely from applications and services that are being taken in. But what is interesting is we are growing at over 40% annually, year on year. The industry, there's a lot of adoption, there's a lot of increasing demand domestically for this technology, which is very encouraging for us. Over 100 plus service providers in India from a non-metal perspective who have different types of printing technologies from a non-metal perspective, who've been printing parts for different applications. A lot of them have started adopting polymer printing for prototyping and other applications, including batch productions and in some case even serial production applications. And we have over, this is a good guesstimate where we believe over 150 plus metal printers have been installed in the country today, which follow predominantly the powder bed fusion technology, laser-based powder bed fusion technology here in India. And most of them are engaged in either developing prototypes or doing small batch production for manufacturers here within the country. In fact, dental is a big market growing at a very fast pace where there are at least about 20 or 25 plus machines which are being used to print dental copings and then are being exported to requirements in many other countries. So that's a growing industry today. And from a service providers or service bureau perspective, there are at least 20 plus manufacturers who have metal printers with them, who produce parts for different end-use applications within the country. Again, so 25 plus polymer manufacturers in India. So from a machine equipment manufacturers, there are over 25 plus plastic and polymer machine manufacturers here in India who've come up predominantly following the FDM technology, who've been making these machines and catering to the local requirements. So from a broad perspective, this is the landscape of where India stands and what has been happening within the country. We'll look at specifically what more in detail what we have. So a good consumer of this is automotive from a prototyping perspective, and in some cases some batch production, and also production assist or production support requirement is what we've seen, where people are using it for not only prototyping but also some mold making or fixture making, jigs and fixtures for their applications. A lot of energy companies are using this for low volume manufacturing because the batches are small in size. Then we have medical, which is an emerging market, like I said, medical and dental, which is growing at a very fast rate. And as I said, a third of the machines, more than 50 machines are installed with government institutions, which means a lot of research and development happening from aerospace, aviation, outer space, defense and other equipment manufacturing that is going on in India. We discussed that. So from an OEM perspective, we have some of the leading automotive manufacturers like the Hero, the Bajaj Autos, and tire manufacturers and others who have invested a significant amount of time, effort, and money in using metal additive manufacturing for their requirement. As I said, some of the mold manufacturers have also started using conformally cooled dies for their requirement to improve productivities. And of course, yeah, so we looked at those numbers. So we look at predominantly the powder bed fusion, which is a technology which we follow and which we believe is 80% of the metal machine consumers today, both, I mean, globally. So our focus was to develop something which is more from a metal printing perspective, our goal was to develop something that would be more production focused, something high volume based. So we went ahead and developed something that would be of a need. So this is something that we have put together. This is our own product. We'll touch base on that just to develop or demonstrate that technology of powder bed fusion is what we're trying to showcase here. But we cater to, from a services perspective, we've had the experience of catering to diverse market segments from medical, aerospace, automotive, tooling, and general engineering for prototypes and others. So just to run through some of the parts, different diverse parts that we've been working on, automotive industries like these, what you can see, not just printing, but also some lightweighting done on parts where people have experimented with topology optimized designs for either lightweighting or printing complex geometries. You can see this one was an aluminum one. Similarly, this is a very interesting case where an automotive electric motorcycle manufacturer has gone about 3D printing motorcycle. We are very proud to be saying about 65 to 70% of this motorcycle has been 3D printed by us. And today, as we speak, they're out to set a Guinness Book of World Record for riding the longest distance by continuously from an electric motorcycle of clocking about 14,000 plus kilometers within the country. So they're going all around the country riding this motorcycle. So this manufacturer, we've done 3+ motorcycles for them, which have been 3D printed for them. So the idea is to see how we can bring down the entire manufacturing lead time. So in this very specific case, from the design completion till the point that the entire motorcycle was put together was less than 30 days. Where 3D printing took about 8-9 days, and then the entire assembly took less than 20 days time. So just to give you how product development is shrinking with time, and we are supporting it through our 3D printing process. So this is what they're set out to do, a record of 14,000 plus kilometers going around the country. And this is what we've been doing with manufacturers like them. Many other parts with topology optimization, just to give you a flavor of what we are involved in terms of printing and developing here. Also, over 35% of weight reduction was done. This is a brake pedal for an automotive. This was for a Formula SAE car developer where we did this, and they were able to demonstrate value for having gone with the 3D printing process. And a lot of welding was reduced. So again, automotive parts from a powertrain perspective, you have different components that have been done. Time is the essence. You develop these parts in a very short time for their requirements. So the whole product development life cycle is shrunken. Next, we have the die casting industry, which we've been supporting through conformally cooled dies. In this case, you can see the requirement was a lot of rejections which were there, which have been reduced. In this case, the customer, this was a aluminum die casting customer who had blowholes that were reported in the part that were being produced, or the aluminum die casted part, where through the conformal cooling channels, they were able to reduce that significantly. And then they've gone ahead with using this for production. So you can see the design, which was printed and then finally ground and given to them a few numbers, which helped them reduce not only the cycle time, but also the rejection rate. Similarly, from a plastic injection molding, you can see what we've done is also done hybrid printing. So where we've taken a conventionally made plate with pre-machined holes, and then we've printed parts with conformal cooling. So you can see the cooling channels on this, where we've done a lot of cooling channels, which help the customer reduce a lot of production time. And then you can see the sandwiched material in design and in actual. This was heat treated to about 54 HRC and then machined. As you can see the machine part here to produce a prototype like this, which is basically a battery case for an automobile manufacturer. So like this, hybrid manufacturing also has been done by us using conformal cooling channels. So here, thereby we have been able to reduce cost. Otherwise, printing a whole part would have costed much more. We've worked with foundry pattern manufacturers where complex geometries have been 3D printed both in aluminum and in maraging steel, where instead of doing it in wood or other materials, customers have gone ahead with printing such complex geometries, thereby reducing time significantly. Fixtures, to give you an idea, some of the fixtures for metal machine cutting, metal cutting machines, and also some assembly fixtures have been done in different materials. So this is just an example of something like that. Moving on to space, a lot of space parts today. One of the most fastest growing industry in India also is space. We have a lot of space, spacecraft, rocket, engine, as well as satellite manufacturers in India who've come up, who are using 3D printing for reducing the time and also printing complex geometry. So this is just an example of what has been done of different parts. Here you can see a very thin, this is basically a collimator, X-ray collimator, which had a very thin wall of 0.3 mm wall thickness, 1.3 mm by 1.3 mm over a length of about 200 plus mm. Height was printed in aluminum with a very good surface finish inside, has been done and offered to customers. So your waveguide antennas for some defense applications where multiple parts were integrated into a single assembly and then printed, where thereby reducing a lot of the development time, and also leakages. Signal loss was a big issue here that has been reduced by printing them in tandem. So these are parts that we put on the moon also in terms of what was done as a part of our moon mission, which is an ongoing process, which is now reiterated with the Chandrayaan-3 project, where we printed parts for them, which have been deployed already to various missions, including the moon mission. So like this, our journey of AM with design, manufacturing, printing a whole lot of parts and different materials has helped us understand the whole process and given us more confidence in developing the technology. So with over 15,000 hours of printing and having worked with customers from different parts of the world, and also our endeavor of developing materials, we've been able to put together a product which we believe is ahead of its time in terms of acceptance, and right now we're already technology development. So right now you see this is what we have developed from a Stellar, we call it as STLR 400 or Stellar 400. This is a high productivity, large sized machine that we've come up with. So this has a 400 size by 400 by 400 mm envelope, which with multi lasers and high powered lasers to be able to print high volumes of material in a very short period of time. So this is the product, just to say, 100% made by us, made in India by us, of course, with the technology learnings from different parts of the world, but yeah, made by us. The goal is large volumes of part, and when you compare it on a cost per part, the goal was to bring it down very close to conventionally made parts. So just to give you an analogy, so from a productivity perspective, we are over double of what can be done from a conventional machine or a conventionally available 3D printing machines. And this is with the host of IoT solutions and smart features on the machine. So you can see a part which was made in Inconel, took less than 19 hours on the machine, an exhaust mixer of 375 mm size or external diameter. In Inconel 625, just to demonstrate the capability of the machine. A lot of user-friendly features on the machine, which is available in terms of digital cockpit and intuitive features, which has been put together by us. Now, just to draw some parallels as to where we are from what we intend to achieve. So conventionally, what machines are available with single lasers from a metal printing perspective, we have done a cost comparison, and you can see in line with where we are with conventional manufacturing. When I say conventional manufacturing, conventionally traditionally made part, there's a huge gap of over 20-25 times the cost of the part. Now, what we've gone ahead doing is progressively increase configuration of the product to bring it much closer to this, which means larger build volume, dual laser systems, high powered system, where we've gone ahead with developing materials at a higher layer thickness, which we'll see soon, and also much more cost-effective powder. So we've done few things differently there. So the idea is to see how, by doing things differently, we can get very close to parts that would be made conventionally and make this available more and make it more suitable for production applications, not just for prototyping and very small volumes. So the idea is to address the gap between the conventionally made one and 3D printed process, thereby improving the rate of adoption in the whole process of the 3D printing. So similarly, looking at what we've developed as a concept called volume melt, here we are trying to see how we can go about printing aluminum parts in a very, very high productivity level. So from a 30 micron, we've come up to about 120 microns. We call this as volume melt parameters, where with the dual laser, we've been able to achieve very close to what conventional parts can be made with the high-powered special parameters and special powders. So this is the focus that we are right now working on to see qualify applications and processes, or get the process qualified for parts suiting different applications in different market segments. So we also have a smaller machine that is that's available for more small component manufacturers. This is largely for prototyping and other smaller applications. Still very good in productivity, but from a smaller size perspective. So we call it as a STLR 180. But from a perspective of R&D, it doesn't stop with this. We've been collaborating with different academic institutions for multiple technologies. We've been working on electron beam melting as a development. We have that going on right now as a project. We have worked on a concept called as multi-stage, multi-axis machine. So I'd like to put together a small video of what was done along with a university called Indian Institute of Technology, Bombay, where we have a machine that was developed with multiple heads of printing. We have different different configurations of TIG welding, MIG welding, we have a hammering station, and then we have a machining inside. So multi-station, multiple technologies all integrated into a single product is what has been put together. What you can see here, we call it as multi-stage, multi-axis hybrid layer manufacturing. So on a machining concept, we have each of these stations that have been interfaced, which has the capability of producing part using different technologies. So this could be configured to multiple different other concepts also. But just to tell you, we're working on a couple of other technologies also from an R&D perspective. So that's what we had from a demonstration perspective of what we are capable of. But nevertheless, just to conclude, what we believe, there's a lot of opportunity today in each domain. We've been promoting, we've been pushing this technology for a wider adoption, for a better adoption, and we strongly believe it's not just suitable for prototyping, small batch production. There is a capability to produce high volume parts for industrial applications today, which we are seeing already, and not just for end-use parts, but a lot of production support and assist parts, like either your tools and toolings and fixtures that are required to improve productivity of parts, and also fixtures for assemblies and machining, and of course inspection. We've worked with many customers, but a lot of the work that we've done are subject to NDA, which is restricting us from demonstrating things here. But today we are working with customers where we're doing serial production also of different parts for different industries. But again, they're all subject to confidentiality, which is why we are unable to show them here. But today additive has come of age, where it is being considered seriously by manufacturers within India too, as a very useful technology for production from an industrial perspective. So this is what we had in a short time to demonstrate what we've done. We'd be very happy to take any questions. You can reach us out at the coordinates given here. Thank you so much for the opportunity.
Thank you, Dr. Biswas, for sharing your capabilities of MS and the range of services that you are offering. I think it is a nice thing. But from the R&D institutes and academic universities, we are more interested in commercialization of the technologies that the scientists and researchers and professors, they are developing.
Sir, I can't hear you.
Am I audible now?
Yes, you are audible.
Okay. Okay, I think Dr. Biswas, am I audible to you now? Oh, I think there is some issues.
I think he has some technical problems.
Okay, okay.
But you are audible for everybody.
Okay, so let us go for our next speaker. May I have the pleasure to invite Dr. Natalia Sayatura. Please forgive me if my pronunciation is wrong. She is a PhD researcher at Semenov Research Center of Chemical Physics, Russian Academy of Science. And she will enlighten us by her work, particles with aluminum core and a hydroxide cell as a basis for creating ceramic metal product by SLS. So welcome, Dr. Sayatura. Please, you may start your presentation.
Good afternoon. Can you see my presentation?
Yeah, we can see, but can you go for the slide mode?
Slide moving.
Yeah.
Yeah. Okay. Thank you. Dear colleagues.
The slides are not moving. You have to make it in the full screen mode, please.
Yeah.
Full screen. I try, but.
Miss Inna, can you help her?
Наталья, Максим, у вас хорошо получается помочь.
Я пытаюсь на F5 нажать.
Надо выйти из демонстрации экрана, выйти, развернуть в полный экран и опять войти в демонстрацию экрана.
А как потом войти в демонстрацию экрана?
Опять зелененькую внизу нажмете.
Если у меня full screen, то уже я не знаю, как Zoom
потом вы переключаетесь в Zoom, нажимаете снизу зелененькую демонстрацию экрана и выбираете среди открытых окошек вот это вот full-screen окошко.
Из демонстрации экрана Alt-табуляция. Alt и табуляция. Можно программу выбирать. Нажимаете F5. Когда развернется экран Alt-табуляции, переходите в Zoom. И там выбираете уже то, что надо.
Так.
F5.
Надо выйти сначала из демонстрации.
Ага.
Остановить демонстрацию. Угу.
Так. А чтобы в Zoom вернуться, Alt, что-то...
Alt и табуляция.
Alt.
И таба.
Угу.
Одновременно и выбираете программу, куда вы перейти.
Так получилось?
Вот, так получилось.
Да. Thank you. Dear colleagues, let me express my sincere gratitude for the kind of opportunity to speak at this seminar.
Yeah.
At the beginning of my report, I would like to focus on the object of the study. These are spherical particles with an aluminum core coated with an oxide shell. They are supposed to be obtained by oxidation of aluminum particles with water, followed by thermal conversion of hydroxide into oxide. An important argument in favor of carrying out a low temperature up to 100 degrees process of aluminum oxidation with water in order to obtain such particles is the possibility of stopping the process quickly when a given degree of aluminum conversion is reached. This makes it possible to control the process of forming a coating of the required thickness. For the oxidation of aluminum, installation have been created that allow such oxidation of aluminum particles to be carried out accurately. The degree of transformation of aluminum was controlled by the volume of hydrogen released at the same time. The oxidation products were dried by steam of dry air, ensuring a quick stop of the process.
Простите, не листается, это правильно? Так должно быть?
Мы пока видим только первый слайд.
Да, так. Ой.
Коллеги, пусть будет так.
We can see changing the properties of the oxide cell. That slide.
Changing. Yes.
Yeah.
Сейчас мы видим третий слайд.
It is. I show you the third slide.
Okay.
Okay.
Could you please try to change slide?
Чтобы мы убедились, что они у вас двигаются. Попробуйте какой-то другой слайд показать.
Сейчас показываю, двигаются?
Нет, no.
Нет. Даже не знаю. Никак, да, не двигаются?
Нет.
Так, тогда что ли остановлю?
Попробуйте еще раз зайти, может быть.
You can use the left slider for selecting the slide now. It's not in full screen, but you can use the left slider. Select one by one when you are speaking.
Yeah, this, yes. We can see the next slide.
Moving?
Yeah.
Да.
Yeah.
Thank you. Activities can be used to accelerate the oxidation of the particle surface. For example, ultrasonic and chemical compounds. In our work, it was shown that some activities are able not only activate the process of aluminum oxidation, but also to change the structure of the hydroxide shell. Thus, when polyethylene glycol is added, the pore size in the hydroxide shell increases from 2 to 6 nanometers. The density of the shell can be changed by ultrasonic explosion. The addition of sodium, calcium, or magnesium, in addition to activating the oxidation process, is capable of modifying the surface and composition of the resulting oxide shell, changing its catalytic properties. Thus, the method of liquid fast oxidation of the surface of aluminum particles by water, particles with an aluminum core, and a shell formed of hydroxide can be produced. We can control the thickness, composition, and structure of the shell. The next step is the conversion of hydroxide shell into oxide shell. It is reasonable to use a thermal exposure for this. This slide presents the results of synchronous thermal analysis carried out simultaneously with mass spectrum analysis of released gas phase compounds. The sample was heated at a rate of 20 degrees per minute. The temperature range from 100 to 300 degrees corresponds to a loss of at least boiled water contained in the studied samples, the loss of water by hydroxide gel. With an increase in the degree of transformation of aluminum in composition of samples, the amount of this water in the composition of the hydrogel decreases and the heating temperature increases, at which the maximum of its release is observed. At temperature about 300 degrees, the decomposition of crystalline hydroxide occurs. At this temperature, the formation of diamide occurs. The minimum corresponding to the fast transition is fixed on differential thermal analysis dependence. At this temperature, the most intense release of water is observed. In this case, the peak of water release is split, which is apparently corresponds to the transition to boehmite of various modification of aluminum hydroxide. Further heating of the boehmite formed at 300 degrees is accompanied by phase transitions observed at temperature around 400, 450, 520, and 620 degrees, associated with its fast transition into various modification of aluminum oxide. This is evidenced by the local maxima of the intensity of the lines related to the mass spectrum of water. Upon further heating of the particles at a temperature above 600 degrees, an exothermic effect is recorded on the differential thermal analysis dependence. At the same time, there is an increase in thermogravimetry. These effects are explained by oxidation of metallic aluminum with oxygen in air. The magnitude of the effect in the value of temperature at which the oxidation process begins depends on the thickness of the oxide layer. Mass spectrometry data show that at given temperature, when particles are heated in inert medium, hydrogen is released. Apparently, at this temperature range, cracking of the oxide shells occurs, as a result of which hydrogen is released and oxygen opens access to metallic aluminum. If oxygen is present in the atmosphere, hydrogen reacts with the release of heat and with formation of water, which is observed using mass spectrometry. At the same time, aluminum melt is squeezed out of cracks and pores in the form of drops that do not spread over the surface. These aluminum drops can be used to bind the core of particles to a metal matrix if particles are used as fillers in the formation of metal oxide materials. It seems appropriate to use the obtained aluminum particles coated with an oxide shell for the formation of two types of metal oxide materials. First, metal oxide frame in the metal matrix. This type can be implemented by the method of selective laser sintering using metallic aluminum core particles appearing on its surface during the formation of an oxide coating. At the same time, matrices of different densities can be implemented. Sintering of contents in this case is possible by additional of aluminum particles. Products obtained by this method can be used, for example, in catalysis, since aluminum oxide, which has a developed surface, is widely used as catalysis and catalysis carrier. And one of the requirements for the modern catalysis is the presence of a spherical shape that provides optimal dynamic gas or liquid flows. The second variant of the metal oxide materials can be implemented by selective laser melting at such parameters of the 3D printer, at which not only aluminum melts, but also the oxide shell. In this case, dense, non-porous, solid products of complex shape will be obtained. In this case, this work demonstrates the process of using particles with aluminum core and hydroxide shell in 3D printing, and surely requires its continuation. Thank you for your attention and for opportunity to make this report. Sorry, but I can't hear you.
Oh, sorry, my mic was muted. So thank you, Dr. Natalia, for sharing your work, aluminum core and with a hydroxyl coating. I think it is very interesting to develop porous structures that you were telling. So I think we will look into that for collaboration on this area and future joint working. It's a very important area, what we think. We can take questions and discuss in the panel during the panel discussion session, as we are lagging to 10 to 12 minutes. So may I have the pleasure to invite Dr. Valla. So Dr. Valla is here.
Yeah, good afternoon.
Yeah,
Sharing.
Yeah, so Dr. Valla is Chief Scientist and Head of Bioceramics and Coating Division. It is in the CSR CGCRI. CGCRI is one of our sister labs under CSR. And Dr. Valla will talk and share his working experience on low-cost additive manufacturing of metals and ceramics using material extrusion process. So, Dr. Valla, it is up to you.
Thank you, Dr. Chatterjee. Yes. Good afternoon to all of you. I hope my slides are visible.
Yeah, it is visible.
Yeah. Okay, thank you. So I am Vamsi Krishna from CSIR Central Glass and Ceramic Research Institute, which is located in eastern part of India. So today I would like to share some of our experiences in manufacturing metal and ceramic components using a material extrusion process, which is one of the additive manufacturing process. Essentially, why I said low cost is if you look at any metal, especially metal additive manufacturing technology, the most popular is laser powder bed fusion or electron beam melting, which are highly capital intensive. It is known that each technology has its own advantages and disadvantages, but some of the applications of the components which are fabricated using these technologies may not require very stringent certification requirements. For example, for aerospace, we need a highly restricted and significant amount of time is consumed in certification. But other areas where that such certification is not there, and functional requirements or property requirements are at a relatively lower end, the other technologies, especially the material extrusion, comes into play, and currently it is gaining a lot of importance and traction as well. So what is material extrusion? Okay. Yeah. So material extrusion is essentially, it will selectively dispense material through a tiny nozzle or orifice as shown here. And then there are three major extrusion mechanisms. One is plunger-based, filament-based, and screw-based. There are other mechanisms which are based on pneumatic, electrical, and magnetic, which are still under development. But the most popular extrusion method is the filament-based extrusion method. And the screw-based is also has its own advantages because the feedstock can be in the form of granules. You need not to make any filaments. As with other additive manufacturing process, there are several important parameters such as speed, feed rate, and other things which are very critical to achieve high performance parts using this technology. And extrusion-based technology is most popular, as we all know, that to process thermoplastic polymers and their composites. But currently, people are extending its use or applications to print metal, ceramics, and glasses and their composites, primarily to using highly filled polymers. And especially, I will show how what are the challenges we face when we are going to fabricate these components using this technology. But if you look at the general strength of this extrusion-based manufacturing, additive manufacturing compared to other technologies, it is inexpensive, especially capital investment is very low, it's very simple to use, and large variety of materials. As you can see, polymer, ceramics, glass, metals, everything can be processed using this. And we can also make components with multi-materials. We can mix them to make composites, or we can have a laminates of different materials wherever you want. But it also comes with some weaknesses, especially the roughness and limited resolution. The resolution essentially depends on the nozzle size. Currently, the nozzle size can range from 200 to 500 microns. So that is one limitation, because it has also some process capability. If you reduce the nozzle size even below like 100 microns or 50 microns, the extrusion pressure becomes so high and the machine capability will not be there. And also it suffers from relatively low speed of printing. But on the other side, if you look at it, the microstructures, especially ceramics or metals processed using this technology, microstructures are always equiax, and there is minimal grain growth. And also this process is last step involves sintering, conventional sintering process. So there is no residual stresses involved or directional solidification, which is the primary concern in metal components manufactured using DED, that is directed laser energy deposition, or laser powder bed fusion and other technologies. So this slide shows some of the typical components which we have successfully manufactured using material extrusion. These are the titanium alloy components, spinal cage, porous scaffolds, automotive brake lever, etc. And similarly, same technology we have used to process some ceramic parts, and then scaffolds, especially using hydroxyapatite material, which is for biomedical applications. So whatever the material is, whether it is a polymer, ceramic, or metal, whatever we are printing using this technology, the primary bonding between the two layers in Z direction or between the beads in X and Y direction depends on the effective diffusion between the layers. That can only achieve if you have a sufficient time, interaction time between the beads, that we can achieve by changing several process parameters, which can be categorized into machine related, such as extrusion type, what type of extrusion we are using, what is the feed type, and print parameters, and also material properties, which are extremely important when we want to process metals and ceramics and composites using this technology. So the major difference between polymers or composite processing using this technology compared to metal, ceramics, or glass, in this metal, glass, and ceramics manufacturing using this technology involves two steps. The first step is a direct printing. After printing, we get a green body. That is further processed in second step, which involves debinding, either solvent extraction or thermal decomposition, followed by sintering, high temperature sintering. As you can see here, this step, second step, the fundamental understanding of the second step is well established, because this is a similar step which currently industry uses in powder injection molding, that is metal injection molding or ceramic injection molding. As you can see here, this video shows printing of titanium, aluminum, 6 aluminum 4 vanadium alloy using this extrusion process, which done on desktop 3D printer. And before printing, we need to work on developing appropriate feedstock. Typically, that contains 90 to 95% of powders, either metal or ceramic, and the balance is the binder. But the printing looks very good, but it also has a lot of challenges compared to pure polymer or polymer composite printing. I have highlighted some of them here. As you can see here, whenever we add metal or ceramic powder, the viscosity of the melt increases, because the FDM or the extrusion has low pressures, inherently low pressure. So we need to optimize that. And also nozzle size and feature resolution is another problem. And the most important challenge which we normally face in making is the blocking and wear of print heads, because these metal ceramic powders which are extruding to this nozzle can easily wear the nozzles. But if we can overcome these challenges, we can reap several benefits. First of all, like we can tailor and control precisely the mechanical and other functional properties at site specific. In a single component, we can have multiple properties. And also we can have a high performance parts using this technology. So let me share some of the challenges which we have faced during manufacturing metal and ceramic components. As you can see here, the filament failure under shear, if this filament, feedstock filament is not proper or if it is weak. And even if the filament is very good, if its distribution and the binder content is not sufficient, we will have an inconsistent material extrusion. So we may not have a consistent flow of material coming out of the nozzle. Even after printing, if my feedstock is not of appropriate quality, I may end up with a lot of porosity, both in green stage and also after sintering. As you can see here, these big, large, continued black areas are the pores which are induced due to improper printing parameters. But within this white beads, you can still see some dark space which are inherent porosity that arises due to improper feedstock, that is filament. Even after that, when we are removing the binder, we can end up with a lot of problems like warpage, shrinkage, and cracks as shown here. And this slide shows how low green density filaments can lead to very low green density printed parts that will, after sintering, we eventually end up with a low density sintered product. That means we started with 90% relative density of feedstock material, but after sintering, we got only 84%. That means there are several parameters that we need to address to get a fully dense and then high strength metal or ceramic parts. In that, the first and most critical step is to prepare a feedstock material, which normally we have used powder and then binder, used raw binder mixture, prepare a feedstock and then extrude in the form of filament. Here, the advantage of this technology is we can also use powder injection molding feedstock, whether it is metal injection molding feedstock or ceramic injection molding feedstock in the form of granules and then making the filaments. There are new machines, printing machines are coming up which can take granules. So in that case, directly instead of making filament, we can directly feed the granules and then directly print into a desired shape. That is still under development. And these feedstock material, that is the filaments for metal or ceramic printing, contains large amount of metal or ceramic powder with a small amount of binder in it. So their physical properties, especially the specific heat, thermal conductivity, coefficient of thermal expansion, and its viscosity, all will play a significant role in getting a good quality prints and then also the final properties. And then as you can, I have listed some of the important effects of these material properties. That means the feedstock material properties. The printability can be affected, warpage, shrinkage, temperature distribution, and finally final parts. So to achieve or address all these issues, we optimize the solid loadings by measuring the torque during feedstock preparation. As you can see, the torque increases as you increase the solid loadings. That is, this is for titanium alloy powder. And then at certain concentration of solid loading, the torque increases rapidly. So this is the critical loading. But normally we could keep it at very low, like that is around 60 volume % of loading. That is essential to ensure low viscosity of the feedstock material during extrusion so that consistent metal flow can happen during printing without much extrusion pressures. So to achieve that, we have also optimized the filament extrusion temperature starting from 105 degrees centigrade to 145 degrees centigrade. And then here I showed the morphology, surface morphology, cross-section of filaments with its relative density. As you can see here, when we extrude at 145, fully dense, almost like 99.9% relative density filaments can be achieved. And using that, the next step is to ensure good printing and optimizing the printing parameters such as layer height, extrusion multiplier, and overlap, etc. By using simple Taguchi method, we have optimized three important printing parameters. As you can see here, when you have a very low optimized process parameters, we can see a lot of porosity between the beads and between the layers. As you can see on the top surface also, the filling was not proper. But by having a appropriate amount of extrusion multiplier, these gaps can be filled and then we get a fully dense green body. Green density of the printed part is very essential because the final sinter density depends on the green density. As you can see here, if you start with low green density part, your final density will be less. So if you start with high green density printed part, our sinter density will be very high, so that we can achieve better mechanical properties. Another important observation which we have made during this investigation is, as you know that most of the additive manufacturing technologies are slow in the output. So we wanted to assess how we can increase the printing speed, for example, from 0.5 millimeter per second printing speed to up to like 16, whether we can increase it. And what is the influence of powder size? As you can see here, fine powder, which is like 13 microns, D5013, which is the typical size of powder injection molding feedstock powder, whether it is ceramic or powder, metal. And another one is 30 micron size D50 powder, which is like most commonly used powder size for laser powder bed fusion or any other powder bed fusion process for metals. As you can see here, when we use little bit coarser powder, we can go up to like 8 millimeters per second speed. But when we want to use very fine powders, which will also help in better sintering kinetics and better mechanical properties due to finer grain size, but our speed we cannot limit, we cannot go beyond like approximately 3 millimeters per second. But what is the reason behind that? So in the extrusion process, especially in using filaments, the filament is extruded using through pinch rolls that will bite these filaments. If the sufficient strength is not there or the extrusion pressure is very high, it will crack. That's what is happening when we increase the speed. And we have used some empirical relations to estimate how much force required to extrude these two different filaments as a function of speed. As you can see here, this horizontal line is the filament failure force in shear failure force, that is around 1.1 Newton. Whenever the estimated extrusion force crosses this 1 Newton per second, the filament failed by shear. As you can see, that's why because of that filament failure, at the end of the nozzle, we will not be able to see consistent flow of material, as you can see in this picture top view. But with the 30 micron powder size, we can go up to like 7 or 8 millimeters per second higher, because here the internal friction within the filament or the friction between the powders is relatively less. That's why the extrusion force is also less. But we can still go up to like 2 to 3 millimeters per second with very fine powders, which is 30 microns of powder size. And the next step, after achieving the good green density, the next step is to remove the binder, which is thermal debinding, which is extremely challenging because we have a multi-component binder and we need to identify at what temperature these binders are eliminated. As you can see here by DTA, TGA, we have observed two different temperatures where two different components of the binder are removed. So based on this, the thermal debinding cycle has been designed, and then we can achieve complete debinding process with a good microstructures up to 99% density. And as you can see here, mechanical properties, ultimate tensile strength versus elongation, we have achieved, which is comparable to metal injection molding parts. Elongation is even comparable to wrought annealed titanium alloy. So this shows that we can optimize the process parameters to achieve better mechanical properties in metals. Similarly, those are all in small coupon level or tensile test samples we have made. We have extended that process to make patient-specific implants, as I have shown here, and we got a very good density, approximately 82%. For this particular application, the surface roughness, as you can see here, very high surface roughness is beneficial for bone ingrowth and bone anchorage. But for other applications, we may need some post-processing, such as grinding and polishing to achieve better surface finish. And in the same way, we have prepared ceramic feedstock, which is hydroxyapatite and also hydroxyapatite and silicon nitrate composites, and processed them, sintered. As you can see here, this is the scanning electron microstructure, shows significant improvement in grain size when you add silicon nitrate to hydroxyapatite. In terms of mechanical properties, as you can see here, I have highlighted the hardness of pure hydroxyapatite is around 0.8 GPa, which can be increased up to like 3.77 GPa, significant improvement in the hardness, primarily due to reduction in grain size from 7.5 micron to 2.2 microns, and strength also almost doubled from 16 MPa compressive strength to around 40 MPa of these fully dense materials, scaffolds. Another beauty of this technology, as you can see here, we have demonstrated that this nozzle, whatever we are using in a desktop printer here, we can design our own nozzle, and we have designed one. As you can see here, from top, the filament will go, or the main matrix, for example, polymer or metal or whatever. And from the side, we can insert a continuous fiber and then prepare a continuous fiber reinforced composites. As you can see here in the video, we have designed the nozzle and then printed using another additive manufacturing technology, which is laser-based powder bed fusion, fitted with the existing desktop printer. And then, as you can see, we printed as a proof of concept, the continuous fiber is going, and then in a polymer matrix, we have printed. And the reinforcements is continuous along the deposition paths, and we have made several test coupons as well. And similarly, by changing...
Dr. Valla, may I just interrupt you for a second?
Yeah.
Yeah, you have to come because we have some time limitation also.
Well, last slide only.
Yeah,
last slide. I'm done.
Thank you, thank you.
So by having a new nozzles, we can have multiples, several variety of deposition modules using different materials and different architectures we can achieve. And at last, at CGCRI, we have a expertise, good amount of expertise in process optimization, development, and new material in various technologies: directed energy deposition, powder bed fusion, material jetting, extrusion based, and also direct type processing. And these are the areas we are like to collaborate with other people and learn and contribute to the science and technology of additive manufacturing. Thank you very much.
Thank you, Dr. Valla, for sharing your work. So, because again, you know, the time limitation is the
yeah,
key.
I do understand.
Yeah, so we will definitely interact with you, and if time permits, in a panel discussions, because many people may have some questions on that. Okay, so now let us go to our next presentation. So our next speaker is Dr. Mikhail Slobodian. So please pardon me if my pronunciation is wrong or
it's
bad.
Okay, it's very good.
Yeah. So Dr. Mikhail is senior researcher, research laboratory at Advanced Technologies, Tomsk Scientific Center. So he will enlighten us on work on electron beam technologies for additive manufacturing of metal products and subsequent processing of their surfaces. So Dr. Mikhail, the floor is on yours now, please.
Yes, thank you very much, dear colleagues. Good day. Do you see my presentation?
Yeah, we can see.
Yeah. Okay. Today I am a representative of our scientific collaborative group, which include several institutes and universities, including one from India. And I will briefly explain our research area since our time limit is overcome as already. First of all, I want to say about our available installations for additive manufacturers, which are based on electron beam technology. This is one of the examples. Such facilities have been designed and fabricated in Tomsk Polytechnic University, and it can use powders, wires, or foils for additive manufacturing of any metal products. As an example, you can see as built sample from a titanium alloy. Also, I present some our publications where you can read in more details this information, or you can write me and we will discuss with any interested person in more details. Also, we have some non-destructive testing facilities which can facilitate to understanding the behavior of materials, including 3D printed and tensile or compressive loads. For example, you can see computed tomography of the titanium additive manufactured samples from the previous slide, and you can see pores in this sample under compressive loads. Our available software can process this data and show, for example, distribution of pores, etc. Also, this equipment enable to show another discontinuous such as cracks, laps of fusion, etc., which is a huge challenge for all additive manufactured metal products. Another our facilities which we can use, it's optical system for assessing strain distribution. This is shown our recent published results, which can demonstrate the possibility of such systems on the examples of as received and welded samples, but the same techniques can be applied for additive manufacturing as well. Also, we have another facility for post-building surface processing, because there are a lot of small discontinuous such as lack of fusions, microcracks, and pores on the surfaces of 3D printed products. As you can see, this pulsed electrons beams are about 10 centimeters in diameters, which can refuse some small discontinuous and improve properties of various metal materials after 3D printed. On this slide, you can see some achievements in these techniques. It's a very recent published result, and several scientific groups investigate these methods nowadays. Also, this facility enabled to coat the metal products with different metal coatings, including multi-component ones, and processed them in a single vacuum cycle. Also, I want to say about some positive results in our collaboration with Indian colleagues. in our another research field, we have published journal paper, and nowadays we are waiting for results from joint competition which was organized by Russian Scientific Foundation with Indian Department of Science and Technology. The results had to be published 2 months ago, but unfortunately we have not results yet. But it is a positive example of collaboration. If anybody will be interested in maybe some other collaborative opportunities, please write me and we will discuss in more details. In general, that's all from me. And you have any questions, I want to answer it. Thank you very much. And I am finished.
Yes, thank you very much. I just wanted our moderator to say a few words. Okay, thank you, Mikhail, for your participation. It is very valuable, as always, I should say, because you are participating not in the first our webinar. So see you next time.
Thank you very much.
Thank you. And the next our participant is Mr.
Anthony Paul from Larsen.
Yes,
yeah.
Mr. Anthony Paul, you're welcome.
Please. Mr. Paul, I think you are muted.
It should be audible now?
Yeah, it's
okay, great. Sorry about that inconvenience. Let me repeat. My name is Anthony, and I lead the Additive Manufacturing Center of Excellence at L&T Defense. Before I start, I would like to thank the organizers for the webinar today, including Russian Academy of Sciences, CSIR India, and Embassy of India in Moscow. Thank you for this opportunity to be part of this webinar and to be part of this forum of established and leading researchers in additive manufacturing. So we all know that additive manufacturing has made a wide adoption within the industries, and there are many technologies which are available. But as Dr. Vishwas had brought out earlier, the degree of adoption among these technologies is highly disproportionate. We have seen a wider adoption of powder bed fusion, particularly laser, and maybe to a smaller degree in the other technologies that we have. So the topic of my session today is the necessity for diverse technologies, especially in metal additive manufacturing. So before we start, I would like to just confirm that my screen is visible in full screen mode.
Yeah,
yes.
It is visible.
It is visible. Please go ahead. Yeah.
All right, thank you. So before we start, I'd like to give a quick summary of the company that I represent, Larsen & Toubro Limited. It is a group of companies into multiple domains in the engineering sector. We are India's largest engineering, manufacturing, and technology company. We are approximately 83 years old. We are a publicly limited company. We are professionally managed, and we have our revenues of approximately $21 billion. And as you can see in this slide, we range across the industrial portfolio from construction, hydrocarbon engineering, power, heavy engineering, defense, shipbuilding, financial services, metro, realty, etc. So it is a diverse portfolio that we handle. And we have, again, customers across the globe and who require our services for their exacting requirements. And we also have the distinction of building the world's biggest statue, the longest bridges, the largest oil and gas platform, the largest reactors. So many records have been set by L&T, both in India and globally, for the various projects that we have undertaken. One of the independent companies under the Larsen & Toubro group of companies is L&T Defense, which is what I'm part of. And our portfolio covers guns, missiles, and armored systems, weapon and engineering systems, military communication, shipbuilding, submarines, and underwater platforms. And as you can see from this portfolio and from the wider portfolio of L&T, the necessity to use additive manufacturing is very strong. And the kind of additive manufacturing technologies that would suit each of these products and portfolios are different. So there are some products and portfolios which require smaller parts which are highly precise, whereas the other products and portfolios require parts which are much larger and which do not need the kind of accuracy that we require in the first place, or it can be achieved through subsequent post-processing. So L&T Defense has offered end-to-end solutions to our customers, starting from design and detail engineering, prototyping, precision manufacturing, assembly integration testing, project management, and through life support. So one key aspect of that which differentiates us from our competitors and from others in the industry is our capability in precision manufacturing, specifically covering critical part manufacturing, sub-assembly, composite manufacturing, final integration validation, and program management. In addition to this, we have recently deployed additive manufacturing into a basket of capabilities. And this is what we'll be covering today. Why has L&T gotten into additive manufacturing? Because we see there are two distinct benefits that we can achieve with AM. The first is the design benefits, which allows us to create complex geometries, and which in turn allows us to get higher degree of performance optimization. It also allows us to get into part consolidation, saving cost, weight, and eventually achieving the performance that we require. It allows us to get produce parts which are having a multi-material kind of composition. So it allows the designers at L&T to leverage the freedom of the technology to create highly optimized, highly customized solutions for our customers. The second aspect that we cover is the supply chain benefit. As a company with AM, we are able to offer a flexible and efficient production, which allows us to reduce the lead time, it allows us to reduce the cost, and it allows us to minimize our footprint to create many parts of one type or many parts of different type. And certain technology, especially DED, allows us to repair and do feature addition, which will also help us to extend the life and to minimize waste. So we understand the various technologies which are available for the industry, and each of them address different baskets in terms of capability. So when we look at aerospace and defense, the typical scale is that we're looking at prototype to small series production. There are projects which require large series production, but they are very rare. And typically, the level of optimization which are there in aerospace and defense require manufacturing of parts having high degree of complexity. So both of these make additive manufacturing well suited for the aerospace and defense industry. And we would like to also stress that additive manufacturing is not a substitute for conventional manufacturing. It is a complement to conventional manufacturing. And that is what we believe, and that is what we go forward with. But we also understand with additive manufacturing, there are certain constraints which come with it. First and foremost, though the technology has advanced significantly and there have been 2-3 decades of development and commercialization, the materials available are still limited, be it powder bed fusion or wire deposition. And we also know among the commercialized or industrialized solutions, you have a trade-off between component size or complexity. You cannot have both. You cannot have a large part which is highly precise or complex, or you cannot have both functionalities in the same feature. And we also know that because they are niche technologies and a lot of R&D has gone into it, there is a high cost of both machines and materials, which limit the adoption within the industry. So these are the 3 main reasons which require us to adopt a variety of metal AM technologies at L&T. Of course, there are other constraints in additive manufacturing, such as geometric and orientation constraints, the resulting porosity, watt plate surface roughness, etc., and the need for post-processing because of the above constraints. We also know that there is some anisotropy depending on the process and the method you follow, and there is an impact on fatigue life, which is critical for defense and aerospace application. So, as I mentioned, there is a wide variety of technologies available covering polymer, composite, metals, etc. The focus at L&T is for direct metal additive manufacturing. Of course, we know that polymer can be used for indirect metal manufacturing, but our focus at L&T is for direct metal additive manufacturing. So the most popular of this technology is powder bed fusion. You have both laser-based powder bed fusion and electron beam-based melting. So this is widely available, and I think the proportion is largely skewed towards laser-based melting. And that, as Dr. Vishwas also mentioned, the large number of machines which are available both in India and globally are in DMLM or DMLS or SLM solutions, which is powder bed fusion with laser. There are very few companies offering EBM, which are established or widely available. But I think the trend is slowly coming in favor of EBM as well. The advantage of both these technologies are that you're able to create relatively smaller parts, but with higher precision and higher accuracy and complex geometries. So this is definitely a necessity for aerospace and defense, but this does not fulfill the entire gamut of requirements that we have. So when we want larger size parts as needed for, let's say, a hull structure or a turret structure or a fuel tank, for example, which are beyond 1 meter in dimension, we will need to look at other technologies, such as direct energy deposition with wire and powder. Under wire-based direct energy deposition, you have electron beam additive manufacturing, which requires a vacuum chamber for processing it without contamination. But then that limits the size of the part that you can do. Of course, it's bigger than powder bed fusion, but there is still a limitation on the size that you can create. The other option that is available is wire arc additive manufacturing, which is typically a large format, open format process, which allows us to have a technically infinite dimension for the part that you create. But in this case, there is a higher risk of contamination and control, and also some distortion that will come through. So these are the technologies available with wire as the feedstock, and keeping wire as a feedstock also improves your material flexibility and the ability and availability. Of course, there is one more technology under direct energy deposition, which is powder-based technology. You have both laser engineered shape or LMD, and you have cladding, both laser cladding and kinetic fusion. So this falls somewhere in between powder bed fusion and direct energy deposition. It has some of the benefits and disadvantages of both technologies. Now, when you compare all these technologies, what L&T has done when we looked at the portfolio of products that we have and which our customers require, we looked at each of these technologies and we tried to assess, can we look at only one technology for all our requirements? And as you can see in the spider chart on the left, if you look at each of these processes under various metrics, such as complexity, accuracy, the as deposited surface finish, the productivity or the build rates that we look at, and the requirement for processing, each of these processes have advantages with respect to each other and also certain disadvantages. So parts which are having high accuracy and relatively smaller size would tend to be done in powder bed fusion, DMLM and EBM, whereas parts which are requiring bigger geometries or which can do with subsequent machining would opt for, would be sent through DED, either through powder bed, DED wire or DED powder. But at L&T, we were looking at more at DED wire, VAM and EBAM processes. And the other aspect, as I mentioned before and going into a little bit more detail, is the resolution that you get for the deposition and also the surface roughness that you get are also typically poorer than what you get with conventional manufacturing. So this was also a choice that we have done. So we needed to do a trade-off analysis on the cost, on the time, and also on the capability of the geometries that can be manufactured through each of these processes. And another aspect that we need to definitely consider is the materials available. As I mentioned earlier, the constraint of additive manufacturing are the type of materials available. So this is just a synopsis of what we have understood. I'm sure there are a lot of R&D going on globally and in India on expanding this material portfolio for each of the technologies that are available. So as you can see, there are certain materials, if you need to create a part, it may not be available in EBM technology or in wire arc additive manufacturing, or a lot of R&D might be required before you can establish the process and validate your component. So when we look at the spectrum of metal AM technologies, what L&T has looked at and what we have chosen to follow is that we will procure powder bed fusion technologies, both laser-based and electron beam-based, because there are a lot of commercial options available, which are mature, which have been utilized and validated. However, the technologies for DED are very few, which are available at a mature stage or available commercially. So there is a lot of research going on both in academia and in the industry for each of these technologies. But we felt that there is a big gap and there is a lot of head start that powder bed fusion have got over DED wire. So this is something that we like to focus on, which is DED wire technologies at L&D. Of course, DED powder is also there, but we would like to address them slightly at a later stage. And our choice of going with DED wire as opposed to DED powder is so that we have a larger gamut of capabilities when you look at feature size, part size, the densities and productivity, and also the cost. So we have looked at the two extremities of the metal additive manufacturing, but eliminating the parts, the processes where the densities are poorer than what is acceptable. So we have established at L&T an additive manufacturing center of excellence. We are leveraging our existing know-how in design, optimization, and engineering, and our established capabilities and infrastructure for post-processing, which is heat treatment, surface treatment, and machining. We have expertise also in testing and qualification of processes and parts for our customers. What we have done is we have added in-house AM facility. We are looking at establishing multiple metal AM technologies under one roof. And with this, we hope to offer design for additive manufacturing services, material characterization and handling, material and parameter development for each of the processes that we have. So this shows some of the development that we have undertaken in-house at L&T, completely leveraging our welding expertise and infrastructure. So this was for a defense application where we have, what I've shown is a representative component that can be done through wire arc additive manufacturing, where we have deposited an aluminum component in a near-net shape format. And we were able to achieve a significant reduction in cost and lead time compared to the original method of casting. And we were able to improve the component performance. We were able to improve some of the operational requirements, such as inventory and logistics concerns we had. And ultimately, we were able to reduce the material wastage through this process. So these are some of the components that we have developed and qualified for use in defense application. And this is also currently implemented in one of our products that we have done right now. So I will just wait for the video to conclude and before we go to the next slide. So let me speed this up in the interest of time. So as you can see here, unlike powder bed fusion, the as deposited part is a near-net part, which requires subsequent machining. And for L&T and for this particular application, the cumulative cost of deposition plus machining was still cheaper than going through either powder bed fusion or through a machining route. So which is why wire arc additive manufacturing was a good solution for this particular set of components. So the previous process, we had used MIG-based process or GMO, and we were looking at aluminum as a component there. And the second part we're looking at is titanium. So here we are looking at GTOR-based process. So what we are trying to do is to establish other welding technologies within wire arc additive manufacturing. And we will eventually like to go forward with CMT also, cold metal transfer. So these are some of the experiments we have done, and all of these are done as a process capability. These are not specifically for defense. These are for general industry. We would be deploying these technologies for our heavy engineering application. We'll be deploying this technology for construction and tooling requirements as well. So some of the challenges that we see in VAM are, one, presently, a lot of the toolpath planning is done manually. Though you use softwares, a lot of effort is required to plan these toolpaths effectively to get a good control on the deposition. So some advancements that we would like to do is intelligent toolpath planning with an automated software. The second aspect that we see here is a distortion during deposition. As we know, it's a hot process, and therefore there is a significant distortion that takes place and which needs to be controlled through refining the process parameter. The interlayer fusion during deposition is also a challenge that we have, which we like to address through thermal management and parameter refinement. And lastly, because it is a hot process, we also have some oxidation which takes place during deposition, which we need to control through localized shielding and inertization. And another set of technologies, as I mentioned earlier, is that we are developing is electron beam hybrid manufacturing. This is similar to EBAM, but we are having subsequent machining capability in-house. So this is something that we are developing with academic collaboration in India with IIT. And we are at initial stage of this development, and we hope to take it forward in the coming months and years. So in this process, we are using an electron beam to melt and deposit metal from a wire feedstock. And in the same chamber, without moving it out, we are able to machine out the required features before we continue with the subsequent deposition. So it gives us a lot of advantages when you combine both the additive and the subtractive part. First and foremost, this technology allows us to use wire feedstock, which allows us to have a higher variety of materials and wire diameters. We have an omnidirectional cladding capability that we are following over here. We are considering five-axis kinematics for the motion control, which allows us to have more complex geometries. We are looking at conformal growth for the parts that we are developing so that we have, again, complex geometries which can be created. And being in a hybrid process, it also allows us to get parts in a finished format at the end of the process. And also, we are able to undertake some of the surfacing requirements within the process. So some challenges in the EBHLM process, which we are working on, and we are trying to come up with some innovative solutions with academic collaboration, is a good trade-off between precision and productivity. So this is something which is important, and as an industry, we need to step in when the time is correct to ensure that we have an appropriate assessment done and we give the correct feedback. The second part is during deposition, we are looking at achieving omnidirectionality. So depending on the cathode that we use, the degree of omnidirectionality would change. So that is something that we look at. And another process challenge is the type of cathode we use also require a higher vacuum, which is required, which has an impact on the design. And the last few other chamber size limitations and motion control schemes which are required to be developed. And all of these will allow us to create a machine which is ready for industrial application. So I would like to summarize my presentation today with a few points. The first point is that additive manufacturing has unshackled the designer in defining what is possible. It provides greater design flexibility and agility. It allows us to optimize the performance for a particular application. It reduces lead time and inventory. It lowers development cost. But multiple AM technologies are available, each having unique advantage and constraints. So we need to select which of these technologies are useful. And unless you do that, force fitting a component to AM or to a specific AM process may be counterproductive. While a broad spectrum of technologies are available, the adoption is very different, but we need to ensure that the niche technologies and the novel technologies are adopted in a wider format. And lastly, I'd like to say that there is a significant opportunity for collaboration to advance state-of-the-art and commercial solutions in additive manufacturing. With that, I would like to conclude. If there are any questions, you can reach out to me at the address and contact details given. Thank you.
Thank you, Mr. Paul. Can we take one or two questions?
Yeah, definitely.
I'm not sure how good are we on the timing front. I don't see.
We are lagging in the timing front.
So we can
I
go
think
ahead,
in
right?
after the speaker, we have a panel discussion slot of 20 minutes.
Okay,
so we can try to accommodate that. Okay.
Okay.
Definitely, I can connect that.
Yeah. Sure.
Thank you.
I think we can invite the next speaker.
Good afternoon.
Yeah.
I think we have no the problem with my slides. Good afternoon. I'm Natalia Lisnina, and today,
right?
Yes, it's me.
Please go ahead.
And today I would like to talk to you about the nickel titanium shaped memory alloys produced by wire arc additive manufacturing. Most presentations before were devoted to the technological aspects of the additive manufacturing. In my presentation, I would like to talk about the structure and the functional properties of the nickel titanium produced by the wire arc additive manufacturing. And this work was carried out within the joint project between our group from St. Petersburg State University and a group of Dr. Palani from Indian Institute of Technology, Indore. First of all, I would like to talk some words about the shape memory alloys. These are very interesting materials which exhibit a very unusual mechanical behavior. First of all, this is the shape memory effect. This is the ability of the alloy to recover the initial shape on heating after the pre-deformation. Here on this video, you can see the spring made from the shape memory alloys. At room temperature, this spring were deformed. After unloading, the spring keeps the deformed shape, but during heating, this spring completely recovers the initial shape. And after heating, the spring has the same length as before the deformation. This is the shape memory effect. The other interesting effect, this is the super elasticity. You know that if we, for instance, take the aluminum, copper, or steel wire and we deform this wire, for instance, we bend, after unloading, this wire keeps the bending shape. But in shape memory alloys, at some conditions, there is the observation of the super elasticity. On this video, you can see the shape memory alloy wire with a diameter of 3 millimeters. And you can see that this wire, after bending, during unloading, completely recovers the initial shape. This is a super elasticity. There are some other effects, but these are two main effects. And this unusual behavior makes these materials to be very promising for different applications in different technological and medical branches. For instance, like a thermomechanical coupling to join some pipes, or like different types of the actuator, one-way or multiple action actuator, which may be used in different technology of cars, aircraft, robots, and any other technologies. And moreover, some years ago, the NASA announced the rover tire made from the shape memory alloys with super elasticity effect. And the other main application, this is a biomedical application, because this materials are used as medical devices or some medical objects like stents or implants. The nature of the shape memory alloys are the thermoelastic magnetic transformation, and now there are a lot of alloy systems which undergo such transformations. However, the most applicable is the nickel titanium based alloys, due to these materials demonstrate the best combination of the functional properties. They can recover approximately 9% of pre-strain, and the good corrosion resistance, biocompatibility, and high strength. However, the nickel titanium shape memory alloys have one huge disadvantage. These materials demonstrate a weak machinability and workability, so it is very difficult to produce the elements with a complex shape from nickel titanium, and this is very expensive. So in this case, the using of the additive manufacturing seems to be very promising to solve this problem, and it was confirmed by the using of the selective laser melting. Now there are a lot of works which show that this technology can be successfully used for the production of different objects from the shape memory alloys, including nickel titanium shape memory alloys. However, you know that there are some limitations. First of all, this is the high price of the nickel titanium powder. this significantly increases the price of the object. And the other is the limitation of the elements by the chamber where the selective laser melting occurs. So this technology is very convenient and useful for the production of the small objects, for instance, for the biomedical application, but it is not very convenient for the production of the massive of large objects from the shape memory alloys. In this case, the application of the wire arc additive manufacturing seems to be more convenient because, first of all, in this technology, we use a nickel titanium wire, which price is less than the price of the powder. And this technology does not limit us for size of the elements. This technology is very widely used for the production of different materials, titanium-based steels and others. But unfortunately, the nickel titanium was first produced by this technology in the 2016-2018 years. So before we started our collaborative work with our Indian colleagues, only few publications were about the structure and the functional properties of the nickel titanium objects produced by wire arc additive manufacturing. So our main aim was to adjust this technology for the production of nickel titanium and to study the peculiarities in the structure and the martensitic transformation and functional properties. Here there are some parameters of our processes, and first, we started our work from the study of the structure and the properties of the simple walls. Our Indian colleagues produced different type of walls with different number of layers, 3, 5, 10 layers. We cut these walls to the cross sections and cut some small samples from different layers and different sites in the layer to study the structure, chemical composition, and the martensitic transformation by differential scanning calorimetry. Moreover, we use these cross sections plates to cut the samples for the mechanical study, for the study of the functional properties. These are the photo image of our samples. And I would like to talk to you about the results. First, we studied from this started from the study of the structure. We found that in our nickel titanium walls, the structure was typical for the structure of the sample produced by wire arc additive manufacturing. The structure of the first layer significantly differed from the structure of the next layers, but the second, third, fourth, and other layers contain the columnar grains, which grows along the building directions. For us, it was more important that we found the significant variation in the chemical composition, the concentration of titanium in nickel in titanium phase, in nickel titanium phase across the layers. In our samples, we used the nickel-rich nickel titanium wire, where the concentration of titanium was approximately 49 atomic %. But in our samples, we obtained that the concentration of titanium in the first, second, and third layer was significantly larger. In the first layer, it was approximately 52 atomic %. This concentration decreased, and only starting the fourth layer, the concentration of titanium in the nickel titanium phase was close to the composition of titanium in the wire. It was due to the penetration of the titanium elements from the substrate, because we use a titanium stripe substrate for these samples. So it increases the concentration. Why it was very important for us? Because, as I said before, the nature of the shape memory effects are the ferroelastic martensitic transformation, which parameters, first of all, the temperatures, significantly depend on the titanium and nickel concentration in the nickel titanium phase. And such huge difference in the concentration in different layers led to different layers underwent the martensitic transformation at different temperatures. Here you can see the differential scanning calorimetry results. And we see that in the first layer, the martensitic transformation occurred at high temperatures. In the middle layer, this transformation occurred at the temperatures close to room temperature. And in the fourth and fifth layers, the martensitic transformation occurred at temperatures below 0. Moreover, you can see that the intensity of the calorimetric peak significantly decreased. It showed that in these layers, only a small amount of the alloy underwent the martensitic transformation due to a high concentration of the nickel inside, and the heterogeneous distribution of the titanium in nickel in these layers. So it is obvious that such sample cannot demonstrate good functional behavior because all layers underwent the Martin-City transformation at different temperatures. And for us, first, it was necessary to restore the Martin-City transformation and to decrease the titanium and nickel heterogeneity in the layers. It is known that for nickel titanium, it may be done by annealing, so we carried out a huge work to find the optimal parameters for the annealing for heat treatment of our samples. And it was found that the best modification of the structure was observed after the annealing at these temperatures for 6 and more hours. This is a long time annealing. After such heat treatment, we found that the chemical composition in the 3rd, 4th, and 5th layer were close to each other. And it was confirmed by the observation of the Martin-City transformation. This is the same colorimetric curves, L1, L2, 3, 4, 5. This is the number of the layers. And you can see that after the optimal heat treatment, the 3rd, 4th, and 5th layers underwent the Martin-City transformation in the same temperature range. Moreover, the intensity of this peak were close to the intensity of the peak in the 1st layer. It shows that the volume fraction of the alloy undergoing the transformation significantly increased after the heat treatment. And we believe that such layers should demonstrate a good functional properties. To study the functional properties, to study the functional properties, we studied the realization of the 4 main effects. First of all, it was the shape memory effect and two-way shape memory effect. To study these effects, the samples were predeformed by tension at a temperature at which all layers were in the Martensite state at low temperatures. Then the sample was heated through the temperature range of the reverse transformation to study the strain recovery on heating, and then subjected to cooling and heating to study the two-way shape memory effect. This effect is very important for the multiple application, for multiple actuator, because this sample can demonstrate the strain recovery on heating in many cycles. The third effect was the recoverable strain variation on cooling and heating under the stress. In these experiments, the samples were loaded by some stress at temperature at which all layers were in the austenite phase, in high temperature phase. And then the sample was subjected to cooling and heating under the stress through the temperature range of the Martin-City transformation. And the last effect was the study of the superelasticity, at which the sample was deformed at a temperature at which all layers were in the austenite state. The sample was, loaded and unloaded, and we studied how the superelasticity was observed. So now I would like to show you the real curves obtained in our samples. First, we studied the functional properties in the samples, which include in the working length only the layers with nickel-rich composition. This is the 3rd and 4th layers. We study all these effects in this sample, and you can see that such sample demonstrate all functional properties. This is a deformation in Martensite state, unloading. During heating, we observe the shape memory effect. During next cooling and heating, we observe the two-way shape memory effect. If we loaded the sample at high temperature and cool and heated through the temperature range under the stress, we observe the recoverable strain variation. And if we deform our sample at the conditions of superelasticity, we observed good superelastic response of our samples. If we change the residual strain in these experiments or stress which acted on cooling and heating in these experiments, we can increase the value of the recoverable strain, and the maximum about 4% was observed in such experiments. In this scheme, we observed the maximum approximately 3%. The maximum value of the two-way shape memory effect, this strain, was approximately 1%. So for us, it was interesting how we can change the properties if we include in the working length the layer with the other chemical composition. So we produce such samples where in the working length we additionally included the second layer with the titanium-rich nickel-titanium phase. And we studied how it affected the functional properties. First of all, we found that in such samples, we did not observe the superelasticity because These layers has different chemical composition and they deform by different mechanisms during loading. It prevented from the observation of the superelasticity. However, the one-way shape memory effect, the two-way shape memory effect, and the recoverable strain on cooling and heating under the stress were observed in these samples. We found that the including of the titanium-rich layer in the working lens led to the observation of the additional stage of strain variation at high temperatures, because the second layer underwent the martensitic transformation at high temperatures. And while one may assume that the observation of the additional stage of strain variation increases the maximum recoverable strain. However, our results showed that the maximum recoverable strain for both cases decreased and was not larger than the 3%. However, we found that the inclusion of this layer with titanium-rich nickel titanium phase significantly increased the value of the two-way shape memory effect. In this, you can see for this sample, the value of the two-way shape memory effect was significantly less than the one-way shape memory effect. However, excuse me, in this sample, the value of the two-way shape memory effect was comparable to the one-way shape memory effect. It is very important for the application. And we showed that this was due to the second and the third layer had the different chemical composition. They deformed by different mechanisms during preliminary tension, and it led to the formation of the internal stresses on the border between the second and the third layer. So these internal stresses additionally increase the value of the two-way shape memory effect. So we can conclude that the nickel titanium shape memory alloys produced by wire arc additive manufacturing demonstrate all functional behavior typical for the nickel titanium produced by conventional technology. The maximum recoverable strain was approximately 3%, and it was twice less than in the nickel titanium produced by conventional technology, because these materials demonstrate approximately 9% of the recoverable strain. We found two main reasons for the small recoverable strain. First of all, it was the formation of the texture. As I said, the inner layers of our sample contain the columnar grains, which long axis was close to the 001 direction. But nickel titanium showed the strong orientational dependence of the functional properties. And as a group of Professor Chumlykov showed, the 001 direction, if we tensile our sample along the 001 direction, this direction was characterized by the smallest recoverable strain, approximately 3%. That was why we observed the small recoverable strain. And the other reason was a small strain up to failure. We found that in the titanium to nickel brittle precipitates during the deformation, during the preliminary deformation, a lot of cracks appeared, and these cracks led to the failure of our sample at small strain. The maximum strain up to failure was approximately 6%. On the basis of our results, we can conclude that to improve the functional properties of the nickel titanium produced by this technology, it is necessary to suppress the formation of the columnar grain structure during solidification, to decrease the average grain size, to suppress the formation of the brittle titanium to nickel precipitates, and to minimize the chemical gradient in the titanium and nickel concentration across the alloys. And we can assume three possible ways to solve these problems. First of all, this is a variation in the parameters of the wire arc additive manufacturing. And we carried out a study of a work where we studied the influence of the arc energy, substrate materials, and substrate temperature on the structure and the properties of our samples. We showed that the variation of these parameters allowed to make some variation, some modification of the structure. The second way is it is necessary to cut the first, second, and third layers, because these layers demonstrate the other chemical compositions than the wire and then the other layers due to the penetration of the substrate elements inside these layers. To decrease the amount of the nickel titanium which should be cut, it is necessary to deposit it the first, second, and third layer with the smallest thickness as possible. And after that, the fourth, fifth, and other layers should be with the normal thickness. And the third way is it is necessary to make some cooling or metal forming between the passes. I know that such procedures are used for the production of the non-shape memory loss materials, and it leads to significantly improvement of the structure. And we hope that in future we will be able to carry out such experiments and to improve the functional properties of our samples. Thank you very much for your attention.
Okay, thank you. Thank you. So Dr. Chatterjee, how do we proceed now?
Now, all participants of the first session, and we have, if we have participants from the second session, are invited to participate in a panel discussion. And I see that Dr. Maxim Homenko wants to say something.
Yes, may I ask a question to the presenter before we start the panel discussion?
Yeah, sure.
So the question is, have you tried to optimize the geometry of your thin wall? As you can see, it is not very square and it is not very strict. That's why I'm asking.
Yes, our Indian colleagues adjust the technologies to produce the samples with a good quality of the walls, and they have we have some publication about it. They use some after each passes, they make some not channels. They modify the structure of the surface by the laser to make some this shape of the channel to increase the heat absorption during the solidification. It allows to improve the quality of the sample and to produce the samples with a thin walls.
Thank you.
You're welcome.
That's all I have.
I think all the participants can open their video also, so that we can start discussion, and if somebody have any questions or collaboration aspect, we can briefly discuss that, because I cannot see the video of many persons. Yeah.
I have also a question to the first speaker, to the Professor Shurukumar. If he is here, he may answer about large metal additive manufacturing.
Yeah.
The first speaker.
Are you here?
Yeah, Professor Surya Kumar, are you here? I don't think so. His mail ID is there. Okay. So
yes, yeah, I see that. Okay.
Yeah. So
okay,
you can
Maxim, anyway, you may put your question to Dr. Surya Kumar, writing him an email, and which is stipulated in the program. So I hope your question will be answered.
Yeah.
So just may I say a few words, sirs? May?
Yeah, please.
I just want to welcome, once again, to welcome you on behalf of the Department for International Cooperation of the Russian Academy of Sciences, and I want to thank you, our moderators of the first session, that made a good job. I know that it's quite difficult job to listen, to understand, to hold the session. It's very important for us. Thank you, sirs. And
thank you.
Thank you.
It's a pleasure and honor for me to greet our colleagues in India carrying out studies in this area, because additive technologies are one of the key areas of modern scientific and technological progress, which have already demonstrated significance over former technologies. And you are well aware that the range of applications for additive technologies is very wide. These fields are mechanical engineering, automotive, auto space, nuclear industry and oil and gas industry, education and science, energy, construction and architecture, and many, many others. And thank you very much that you found this opportunity to participate in our webinar presenting your research. Thank you very much once again. And it's a pleasure to know that today additive technologies are becoming the subject of brainstorming, international cooperation, and interaction of groups of scientists from different countries. And the events like this webinar are a good platform for Russian and Indian scientists, researchers to present their work, share their last achievements and scientific experience with their foreign colleagues. And I would like to conclude by wishing you all a successful event and as well as new achievements and interesting discoveries in your scientific work. Thank you very much.
Thank you. So you can also welcome Dr. Maria from Mendeleev University.
Unfortunately, I don't see her joining us, perhaps some unexpected circumstances, and she doesn't participate.
All right. So we could start the panel discussions.
Yeah, Professor Surya Kumar is there. So Dr. Maxim, if you have any questions or briefly, he will respond. Because we have a couple of minutes still left, 2-3 minutes.
Yeah, Dr. Surya is already there.
Yeah. We have 2-3 minutes.
Sorry.
So you can raise your questions and.
Okay. So I thought I saw some news on the largest facility in additive manufacturing of titanium powder made in South Africa. And I was to ask, have you heard about that? And have you discussed some problems with the large facility concerning its larger to be the largest?
Maybe I will respond. No, in fact, this is the first time I'm hearing about the South African. So I'll be eager to take some details from you. Unfortunately, no. But we ourselves are in the process of building a 3-meter large component. Machine capable of printing up to 3-meter large. Already we have
they made 2 meter.
Yes,
they made 2-meter facility.
Okay, so we are under the process of building that currently in our facility. So it is mainly for rocket components or casings, etc. We have finished the design and development. If we finish that, it will be capable of printing 3-meter long components. So that's essentially, we hope, next time we meet, we will have some pictures of the work done, carried out there with me to share. But right now it's just ongoing work.
Yeah, may I just add, Mr. Antony from L&T, 2-meter to 3-meter component size. I think L&T are making that through WAM.
So we are able to do such large parts. We have not reached that in a validated state yet. So our configuration of our equipment and the process we have established can do up to 2-meter size parts. But as I discussed, there are a lot of distortion constraints that we need to address for such a large component.
Yeah. In the second session, we have a presentation of Dr. Monidipta Mukherjee, where he will present that work on WAM, wire arc additive, which has been done in our institute, and the components that has been made on that, mainly automobile, on a single robot depositions and a hybrid system, that is a single robot additive subtractive hybrid. Okay. So that we'll have the presentation in the second session. Yeah.
I look forward to that.
Yeah. So, Madam Ina, can we take one more questions?
Dr. Avik Chatterjee, I am Deepak from Sikri Karaikudi.
Yeah.
Can I connect to Dr. Andre Samkin? Is he available?
Yeah, Professor Samokin is available. We can see him in the video. Yeah.
Dr. Samkin, actually I attended his presentation, and he's into AM grade metal powder. Since I'm working in the field of biomedical materials and implants and medical devices, I'll be interested to know whether he has the capability of making the beta titanium alloys like titanium, niobium, zirconium, or TNZT series, titanium, niobium, zirconium, tantalum kind of alloy. Is it possible to make by DC arc plasma spheroidization technique?
We can't hear you. Please turn on your microphone.
Professor Samokin, your video, you're muted.
Yeah. Okay. If I correct understand the question, I think that I can answer that it's possible to spheroidize the powders of titanium niobium systems with particle size no more than maybe 80 microns.
So titanium, niobium, titanium, zirconium, or tantalum.
Titanium, zirconium too. Yes, it's possible. Yes, we did that. So it's possible. But a very important thing is the more narrow particle size distribution, the best results we'll get. You should prepare particle size distribution. The more narrow, the best.
I understand. But it is possible to make beta.
Yes, we can do that. But we can connect it through the email or telephone. It's possible.
Yeah, I will separately. I will write email and we'll discuss.
Yes, it's convenient. It's more convenient.
Since I'm working on additively manufactured bio implants and medical devices, so on titanium and titanium alloys, I will be discussing in the second half of the presentation, and I am more interested in the beta alloys for biomedical application.
But it's a very important thing. I need powders from you. I need to get powders from you, and we can spheroidize this powder in our setup. So it's a question from me. What method of powder production do you use?
So I will be for basically 40 to 65 micron particle size will be better for the processing, because we are using this selective laser melting facility to make the components. Yeah, around 325 mesh.
I think we should
I will separately
by email.
I will separately email you so that we can discuss.
Yes. It will be good.
Thank you, Dr. Avi.
Thank you. So, Ina, can we now proceed to our second session?
Yes, sure. I welcome everybody to the second session, and may I introduce you the moderator of the second session. It is Dr. Maxim Khomenko. He has his PhD, and he is a researcher at the Institute of Laser and Information Technologies. This is the branch of the the branch of the Federal Research Center, Crystallography and Photonics of the Russian Academy of Sciences. And please, Maxim, take this session in your hands.
Okay.
Floor is
Okay.
yours.
First of all, I would like to say some words on this section. So I'm happy to moderate. Thank you very much for giving me this opportunity. We've got very interesting program, a huge program. That's why I would ask everybody to be more strict in meeting the time limits. I can see that we have a very interesting presentation here, very good geography of the presenters, both from Russia and from India, thanks to organizing that. So let me introduce the first speaker, who is Professor Lityuk, with his Prof. Are you here?
Yes, I can see him. Vasily Lutsik.
Hello.
Lutsik, I'm sorry.
Good afternoon, dear colleagues. Do you hear me?
Yes.
I am very glad to welcome you from the city of Ulan-Ude, capital of the Republic Buryatia and capital of the Russian Buddhism. We are very grateful for the Embassy of India for the opportunity to participate in the India-Russia scientific webinar on additive manufacturing technologies and to inform you about the results of our research team. This year, during World February, we celebrate White Month. It is New Year in Mongolia and Buryatia. Mongolian Lunar New Year, commonly known as Tsagan Sar. So, Happy New Year. We wish you a healthy and wealthy life. Firstly, we had joined the so-called additive community in 2015 at the first international conference, Additive Technologies, the Present and the Future, in Moscow at the All-Russian Institute of Aviation Materials. We participated with the report Computer Models of Phase Diagrams to design the additive technology materials. This year, on October 6-7, this conference will be held for the 8th time at the same place. The fact is that we offered an innovative technology to assemble the space computer models for the multidimensional phase diagrams of the multi-component system. Our special session, titled Phase Diagrams as a Tool of Material Science, worked within the frames of 2nd, 3rd, and 4th international conferences on competitive materials and technology processes in Hungary. Here you see the schedule of our session, and my colleague, co-chair, Professor Dedenak from France. Our innovation was initiated in Donetsk, USSR, Ukraine, and now it is unrecognized the Donetsk People's Republic. This innovation is based on the fundamentals of the famous scientist school of the academician Kurnakov. Max Mokosoyev, Buryatian by nationality, was my dean at the chemical department of the Donetsk University. Now we usually inform our innovation by comparing this possibility to calculate thermodynamically phase diagrams and less known approach in Moscow University of Professor Voronin. And below you see information that computer models of phase diagrams with kinematical and minimal surfaces with thermodynamic contours after space schemes of phase reactions, meaningful designation of geometrical elements and material balances. It is used only in Ulan-Ude, Russian Federation. Let me now advertise my colleagues and countrymen in Ulan-Ude that elaborate new inorganic materials for the additive technology. I hope it will be conveniently this way to move from the session 1, advancement in different additive manufacturing processes, to the session 2, additive manufacturing applications. You see here in red my colleagues and their papers. Now we return to our approach to assemble the multidimensional phase diagrams of multi-component systems as a new tool of material sciences. In 2009, we firstly informed this technology for the international community as a 38 Kalfat meeting in Czech Republic. And we told that on this example of a diagram with low temperature modifications A1 and B1 of components A and B, this diagram has 90 surfaces, 5 of them liquidus and 5 solidus, 6 solvus, 12 unruled surfaces or transverse borders of 2 phase regions and 42 ruled surfaces, 20 horizontal simplexes, and 33 phase regions. Univariant and invariant state scheme in a table form for the diagram with 2 allotropes of the component B is showed here with surfaces of liquidus, solidus, solvus, transverse, ruled surfaces, horizontal simplexes, total number of surfaces the same as in the previous example, 90, and total number of phase regions, 32. Really, by our software, we use 3D variants of table schemes showed in the previous slides, and this space scheme is possibility to produce the ruled surfaces and later to add for them the non-ruled ones, non-ruled surfaces. So 3D computer models of ternary diagrams for visualization and verification or validation of calculation and experimental interpretations consists of 3 steps. Definition of geometric structure, number and type of surfaces and phase regions of TXY diagrams by table to D, union and invariant state scheme. It means phase reaction schemes plus 3 phase reaction reactance trajectories. Next step, TXY diagram prototype design by space, 3D union invariant state scheme. And last step, input of real, more exact parameters of the XY diagram, and more precise, authentic view about the surface curvature of for more perfect model. One example of possibility of this type of diagrams you see on this slide. Usually for this very important ternary system, there are only about 10 crystallization paths discussed in the textbooks for the students, but we analyzed the possibility of existence 117 fields of 2 dimension and 133 fields of 1 dimension on the borders of these 2-dimensional fields, and 45 fields of 0 dimension. It means surely those, and as a result, it's possible to produce 325 crystallization paths, and for all these crystallization paths, it's possible to produce material balances and microstructures that formed during the crystallization of such materials. More close to our report now, an analysis of the current state of research on TXY diagrams of ternary systems and TXYZ diagrams of quaternary systems constructed from experimental data and thermodynamic calculation leads to the conclusion that they need additional verification by 3D and 4D computer models. It means exploded phase diagrams consisted from the 3D printed phase regions. Such verification either confirms these results, it means validation, or corrects them. It's possible to have graphical error even in famous, in very known monographs, as you see on this slide. And as a result, this error, it exactly additional low line here, really only upper line is possible, and lower line, it is error. And it is produced in 2 issues of this monograph, and as a result, this error repeated in this paper, modern paper. Nevertheless, this type of diagram is very known, and it is used on the cover of this very known journal, very known journal. So to protect these errors, it is better to have experience to work with exploded phase diagrams, and later I will show you this in practice. But firstly, I will start with our experience to work with this Atlas of Phase Diagrams for Lead-Free Soldering, issued in 2008. And you see here below 20 ternary phase diagrams. We worked with now with all of them, and here we see by red diagrams that we confirmed the graphics of these diagrams, and by blue that these diagrams had problems. Now I will tell you about the diagram silver copper nickel, and here on this slide you see it by red that we confirmed results about this diagram in this atlas. But later we analyzed, we were very astonished to see errors with this diagram. Scheme of phase reaction eliminates the possibility of the existence of a three-phase region, silver plus copper plus nickel, and two research teams from China and Japan in 2007 published a scheme of phase reactions of ternary system, which prohibits the existence of a three-phase region. But later, a year later, the same two teams, the same authors, published paper in which this three-phase region, you see it in red, not possible. They show this phase region on the section of this ternary diagram. To the right of it, it is the same incision obtained with the help of our computer model. And in 2009, they again repeated this error in next their paper. It is from two different papers of 2008 and 2009. One more example of the same authors with this impossible three-phase region. We are not talking about the shortcomings of the thermodynamic calculation methodology for experimental errors. We are talking about errors in the interpretation of experimental data and the results of thermodynamic calculations, which our computer models help to identify. Surely our idea is based on a different type of models to image ternary phase diagrams. It is made from wire, and this type of 3D printed phase regions of phase diagram of eutectic type, which consists of 13 phase regions. Now I will show you the results of our simulation of this ternary system of silver, copper, nickel, and our specifications for printing these exploded phase regions. Computer model of phase diagram allow you to reproduce a space model of phase diagram and its geometrical elements, surfaces and phase regions, to consider arbitrary sections, to decipher them. The finished 3D model makes it possible to build any sections, as well as perform calculations of material balances, tracing the history of crystallization and changes in the phase and conglomerate composition of the alloy on the diagram of the material balance. In addition, 3D models are effectively used to verify published phase diagrams. Our approach allows the construction of KXY diagram even in the absence of some data. I mean the prediction of some elements of the diagram which cannot be achieved by similar thermodynamic models. But always, even a primitive model built on the minimum amount of available information is consistent with the basic principles of geometric thermodynamics. I mean phase rule and the rule of adjusting state spaces. The same diagram here is shown as a prototype of exploded phase diagram silver, copper, nickel with 9 phase regions. We use these phase regions to make the specifications for every region before 3D printing.
Sorry,
here is one of these phase region. The phase region is faceted by 3 ruled surfaces formed as horizontal segment move along the guidelines. We see here contour of these 3 ruled surfaces. Here we see 3 points. I'm sorry, in 2 lines 4 points, and in the 3rd line 3 points. In order to increase the volume of this phase region, it is necessary to set a large temperature difference between the triad of upper points with constant temperature and a pair of lower points with constant temperature, and the antibate character of the directing curves, and which form 3 ruled surfaces, and 2 variants of convexities for these 3 guidelines should be considered. And in the process of consideration, it is necessary to decide which way is preferable. First variant, the 2 branches of the loop with these 3 points should be convex down, and the line should be convex up. Both curves should turn into extremes. And second variant, the 2 branches of the loop with the same 3 points should be convex up, and the line should be convex down. Both curves shouldn't turn into extremes. This specification is made for the 3D printing of these phase regions. And now I will show you
I'm sorry.
Example of our cooperation with a colleague from India. Our research team participated in the project application with a joint call of proposal between Russian Science Foundation and the same organization in India. And till now, we wait the results of this contest. Our project, experimental investigation and thermodynamic modeling of high temperature phase equilibria of the quaternary iron, nickel, copper, sulfur, and iron, nickel, cobalt, sulfur systems supplemented with a geometrical description is co-headed by Professor Hari Kumar. And next slide, we show that our colleague Hari Kumar will lecture at this winter school in Germany for the young scientists. In conclusion, I would like to emphasize that our approach doesn't compete with thermodynamics or first principle calculations, but can help to identify the possible errors that, in our opinion, should be excluded. We believe that even well-trained scientists should practice with the exploded phase diagrams produced by 3D printing, because errors can occur even in the simplest cases. Now I told you about the diagrams consisting of only 6 and 9 phase regions, and being there may exist mistakes. So 3D puzzles with 3D printed exploded phase diagrams will make the progress in the material sciences. Thank you for your attention.
Thank you, Professor.
I'm ready to answer the question.
Let we have one short question.
Yes, yes.
Are there any questions? Okay. Then we will go to the next speaker. We are now already 5 minutes late. The next speaker is Dr. De. So please start your presentation. Can you hear me?
Yes, I can hear you.
Please take your time.
Yeah. Is my screen visible?
Yes.
Okay, good afternoon to all my colleagues in India and Russia. Firstly, I must thank to the organizers, in particular the organizers at CSIR lab for kindly inviting me for this presentation. The topic I would like to talk on is computer-based models for design for additive manufacturing. As we all know, I will try to just be very brief on this. There are different directions, different variants of additive manufacturing as we have seen. So I would not like to talk much on this, like powder bed based process, directed energy deposition using powder as well as filler wire, for example. And these are different features for different types of variants of processes like laser, EV. In case of wire as a feedstock, we have electron beam and electric arc as a heat source. And typically we refer to nomenclatures like DED, electron beam, DED, gas metal arc, although there are other power sources that are also being used. But these are the most popular ones. And typical build size features like medium to large, surface finish, some broad category is mentioned here. And if we look at the applications of additive manufacturing, as several respected speakers have already pointed out, that it has now gained a very fair attraction from a wide range of industries. As you can see, that includes like several applications like hydraulic valve, fuel nozzle, gas turbine blades. The industries varying from consumer, automotive, healthcare, energy, aerospace, and so much. So it is not surprising, as especially our friend from L&T, Mr. Paul, has presented, that it has some unique strengths, like it has very short lead time. The important thing that it has an ability to use of the same equipment for different products, which is very welcoming for industry in particular. Subsequented by favorable return on investment due to lesser part counts, ability to work with difficult to process materials. One important feature in particular, because most of the popular processes in additive manufacturing are based on melting of materials. So it is easy to process materials in some way. And it is a kind of open-end building. So we often do not need any mold or so on. So free-form production is one of the primary features of additive manufacturing. So it is very easy to process difficult to manufacture materials. If we just quickly go into the current challenges are in primarily 3 directions. One, like all other manufacturing processes, the process structure property relations in additive manufacturing are currently evolving. And I can point out here, as you all know, similar relations for other manufacturing processes have evolved over a large period of time, I mean, fairly large number of decades. So it's not surprising that it is taking a little time. But to add to the complexity, there are also pilot tests, I mean, which are costly for additive manufacturing, because as we know, the feedstock material like powders is very costly. And till date, only a few commercial alloys can be processed with reliability. So if we look at that, there are different directions. One is scientific challenge, economic challenge, and technological challenge. In all three directions, we are now in a stage where we must be able to successfully understand or take care of these challenges in all three directions, so that the process can be utilized more and more in a commercial manner, economically successfully. I would like to go quickly to the common defects that many of us know, but these are very basic things, like we have balling and porosity that deteriorates property and serviceability of the build part that we all know, and this porosity is very common in not only laser powder bed fusion, but other form of additive manufacturing processes also. Here it is shown, for example, in this slide, that it depends on powder layer thickness, but it is not only one powder layer thickness. There are many other parameters that indirectly or directly influence the fraction of porosity in the final part. So this is a very difficult problem even as of now in most cases. Distortion, as many speakers have pointed out, cracks, delamination are some of the more important difficulties, especially for processes when we have large area manufacturing or high volume production and so on. So these are examples of one case, but there are many similar examples where distortion and stresses have led to delamination and cracks. Now, these are not new. We must remember similar problems have been there of sister processes like welding, and over a long period of learning, pilot tests, we have learned to overcome many such problems in casting and welding problems, which are similar to additive manufacturing. And currently we are going through that stages in many cases to overcome these problems and come to a situation where we can use parameters correctly to get a defect-free part. So I would skip this. This is something a little, more to understand that to go from a small scale part to a large scale part, there is always a standard manufacturing issue, that there will be some stage, some time that will be required, and which has been noted in most cases. So there will be a lot of difficulty at this stage to bring to a concept stage to a stage where we can manufacture, we can use the process commercially successfully to produce defect-free parts with longevity and serviceability. Now, to reduce this and make this thing faster, of course, because we cannot wait the way we have done it in earlier manufacturing processes. I mean, many of us know, for example, just before additive manufacturing, there was a very popular, there has been a swift development of another typical manufacturing process. Many of us are aware of that, like friction stir welding. It took also not like a huge amount of time to get to a mature stage, only because there have been tremendous effort in different corners at different laboratories to understand it experimentally, also based on computer-based models, using computer-based models. So to mention here that the computer-based models have been able to help in better and quicker understanding and a more deterministic understanding of the process fundamentals, and that has helped to use the processes in a more confident manner. Likewise, in additive manufacturing also, if we look at the recently published paper in the last 5 years, especially, we'll see there is a huge volume of research that has gone into development of computational models for additive manufacturing processes, primarily to understand the fundamentals and then to mitigate defects and to develop maps that can help in application of the process in a more deterministic manner, commercially successful manner. So the primary objectives of development of computational models, like in any previous manufacturing processes, here also to understand the geometry, composition, structure of parts, and various in process parameters and alloys using scientific principles to minimize trial and error tests, to avoid defects. That's the most important thing. There are many, like inadequate fusion, porosity, distortion. Of course, to estimate the impacts of alloy and change in AM processes, and more going into fine issues, like in particular, because it is a primarily thermal process. So to calculate, for example, understand the thermal treatment and how does it help in, or how does it impact the evolution of structure, how does it influence the homogeneity or inhomogeneity of structures, mechanical properties, distortion, residual stress, and finally serviceability. So there are many such targets which a computational model for these processes can provide if these models are developed properly and validated extensively. Now, unlike in other processes, the development of models, computer-based models for additive manufacturing has some unique challenges. Unlike any other process, additive manufacturing is typically manufacturing track by track and layer by layer. So a part typically can be built by a huge number of tracks and layers, often well over 1,000. And the picture on the right, as you can see, it simply shows the scale, the way a part is being manufactured. So this is a unique challenge. This is not like in any other process where the scale of the manufactured part is much smaller. So for example, imagine a situation that 1 millimeter cube equivalent cells of 10 micron to be considered for 1 million time steps or more. I mean, this is what we are trying to model. You know, this is a huge computational challenge. In other words, powder by powder, building a sort of centimeter, meter, or meters of lengths of part. If we when we try to develop some computational models for this, it definitely becomes a huge task to take care of. So there are many techniques which are created or which are being generated. People have started using, evaluating how the scalability, how it is work, how can they work, like multi-scale models, adaptive meshing for computational models, microscale, mesoscale, macroscale. So there are different scale models which are echoes, I would say, and being attempted by different researchers and in labs and universities. This is a typical challenge. I mean, in a very basic level, if we can look at, if we can think of a simple thin wall is being built by layer by a DVD process, laser direct energy deposition, laser process. So if we can think of that, every bits of powders we'll try to model how they are, each powder particle is melting, or a set of powder particles are melting and solidifying to give a part shape like this. I mean, every such step, every such cells or these unit blocks are to be modeled by some kind of numerical methods or so. And these models have to understand what is the temperature and when it is melted, what are the, the way how the molten metal moves within the pool. So there are a huge challenge if we think of the typical variables that we have to analyze, like velocity, pressure, enthalpy, or temperature, and so many equations we have to solve. And this is a real challenge for most of the situations. And this is for a simple case. as you can see, the larger the size of the part, the more complex the geometry of the parts, the more complex will be such calculation. So there are different multi-scale models that have been there now. People have been trying to a level of success now, I would say. Like we go for, you see, for very small level, powder level models where we track, or people track what is happening at a very small scale, how much is melting for a given application of power, steam, and so on. Then from there from a small scale level, go to a slightly larger scale, so that interpolation of results to see what are the slightly larger values of, dimension of the pools, what will happen if we go from one layer to multiple layers, and then from layer to even larger scale, like in a much bigger scale, where we want to see if this is the volume of molten pool and so on, what will be the distortion, like, or stresses or lack of efficiency in a larger track by track and layer by layer model. So such integration of small scale to large scale models are now being tried, and different numerical processes or algorithms are being utilized for going from micro scale to meso scale to macro scale, with at each level different outputs are being analyzed. Of course, this is a task by itself, and often this itself takes a huge time to integrate such models. The validation of such models are also often a big challenge, because at every stage it has to be examined whether the computed results from the models in terms of melt pool geometry, temperature field that is coming, part distortion, residual stress field, whether they are really predicting true to the reality. Only when these models are validated intimately, such models can be utilized for future prediction, which is often yet, I would say, still not very well established, the best of my knowledge. Just a glimpse of what can these models can do, for example. It can, for example, simulate how these layer by layer powders are built. So as you can see, it's simulating typically layer by layer, and then these simulated results can be compared with a real build scenario. And from there, one can also go for this kind of models, like how typically layer by layer, as it is going up, how the size of the pools are increasing, simply because as you go up, more and more heat is accumulated. So of course, if you do not stop in between, do not bring down the residence temperature of the bead, the pool size will go up. Not only that, the pool size will also go up, because as we go further, the channel of heat loss with dissipation is reducing, so size will go up. So this shows, for example, that if we want to have some uniform melt dimension, crack dimensions, we must have to do something so that the size of the pools remain uniform, for example, as it tells. As I mentioned sometimes in a few slides back, that there are ways to reduce the computational demand. There are schemes like this. For example, a very fine mesh like this is used to model a small area where the melting happens, and so that we do not have a huge amount of these typical unit cells, such a fine mesh can be moving as it is moved along with the actual deposition process. So, meaning thereby the overall size of the domain, computational domain, remains the same, but a fine mesh continuously moves all through the domain, taking care of the local variations of temperature field as a product of the power and speed of the laser beam which is being applied. And as you can see, these models can provide very nice results. Interestingly, they can tell us the effect of process conditions like this, for example. And as I said, if we can validate these results, these models can suffice to actually, design of the final part, that what should be the process power, what should be the speed, and so on. And if it can be done intelligently, this is something what we can do. For example, a very regular calculation model, a regular simulation model can perhaps take an hours, whereas an intelligently done model can take only few hours for a large scale simulation. A 3-layer, 3-hatch, or even more layers and hatches in a typical scheme. Not only that, if we go further, these kind of computed results can even show that, okay, if we take a certain strategy, it will lead to certain porosity between successive adjacent tracks and successive layers. For other case, for another material, there will be sufficient overlap leading to no porosity and no lack of fusion, for example. So this is definitely an effect of material properties which are instrumental in thermal or heat dissipation analysis, actual intrinsic property of the material. So what it shows in particular, that before going to the actual deposition process, these models can actually tell us that if we can do this exercise and try to set up the process, design the process accordingly, we may avoid defects, mitigate the defects very well established in a very validated. So similar models are now, just wanted to show you that across the different research groups, similar models are also now established for wire arc additive manufacturing, as it shows here, for example, for H13, 1 track, 1 layer. Or similar models can also be done for 3 tracks, 1 layer, and this has been now done. Although, as someone has already pointed out, that as we go to a process where the deposition rate is more and volume of deposition is more, the computational challenges increase. So here, for example, modeling or calculating such deposition process for a larger number of track and layers would be very difficult. In fact, at some point of time, it will be impossible to model within the computational power that are currently available. Of course, if we develop these models and compute the thermal cycles, they can be used in different ways, like cooling rates calculated across the layers can be used to predict the spacings of the cells from top to bottom layers, which can be used further to compute mechanical properties. This is one way to show that to what extent the computational model can support the design of process variables to get a better part. These models can also be used for computing the residual stresses, which is well known. For example, in this case, as we know, similar problems were faced in welding, which is a similar process. So models like these can be used to compute the longitudinal residual stresses, transverse residual stresses, normal residual stresses for a typical DED laser-based process. And as I said, this can be done for different processes. It's all in the computational domain. So current status, as you can see for computational models, more or less models are there, available, capabilities are developed to prepare or compute how the made full dimensions will be happening because of certain power, speed, powder, tracks and layers, but in a smaller scale. At that level of scale, locally, what will be the plane orientations, structural morphology are also being predicted or being computed by several research groups. There are also models which has gone into powder levels and predicted with certain certainty what would be the porosity, susceptibility to porosity for different cases, depending on what are the made full dimensions or whether there is a keyhole instability. So such models are already being used in many cases, but at the R&D level, and harnessing them for actual industry or design for the process, to the best of my knowledge, is only on the growing stage. The scaling up of models have got another opportunity. For example, people have been also trying to develop very simple models where a large number of layers or tracks are being considered as one equivalent layer or equivalent set of deposition. And by doing so, although the local history gets lost, which can be obtained, of course, by local area simulation, but using this, a large part can be simulated in a relatively smaller computational challenge. It can be done. Alternately, one can also go for analytical models, which are being also developed. And today, I can say that there are very good articles reported in the literature which can analytically solve, compute such made pool dimensions in at least powder-based processes, not so yet in wire or wire-based processes. As you can see, different tracks can be predicted. For example, I mean, it can be modeled that how the made pool will continuously change, what will be the size of the pool. And these models can be used to develop maps like as a function of power and speed for different materials. What will be the size of the pool length, width as well as depth, which can of course be used further to see whether there will be a lack of fusion between tracks and layers. So these are typical maps which can be used essentially for the design of power and speed, so that there are no porosity, for example, or complete fusion, for example. A quick glimpse of what are different capability of such models. For example, if an analytical heat conduction model can take very fast, can work very fast, for example, typically this size of build. Okay, this can be simulated in seconds and minutes, whereas simple conduction-based numerical calculation can take hours and days. For example, if you go for a higher build, and if you go for powder scale model, go to very local level to see what is happening to each powder particle. These simulations can, for example, take hours and some days, which I mean years, for example. So of course, these are completely impractical. So we have to develop more and more strategies how such models can be utilized for real. One another direction of
I'm sorry, Prof.
Yeah, 2 more minutes.
Okay. Okay.
So there are also another direction of machine language based models which are being investigated now, where different types of machine language based algorithms like artificial neural network, random forest based algorithms, and so on are being used, where the data that are generated as a part of a huge amount of experiments as well as validated simulations, these data are being used to find out how are they related and what are the reliable zone of these deep parameters, process variables, which can provide a desired process condition. So using these algorithms without going into detailed numerical simulation, such kind of maps are now being attempted to generate, where a function of different process variables can be shown in a map, and the zone of process variables can be considered to avoid defects and to gain a certain property and so on. For example, with and without flaw can be sort of targeted based on certain algorithm based models, which are based on entirely data, as it is shown here. For example, see some as a function of 2 variables, it can be speed and power. For example, it can be shown that if we remain in this level, there would be susceptibility to porosity. If the range can be here, it will be defect-free path. So these kind of models are also being now generated. These models are also helping in understanding the importance, the relative importance of path, which is very essential, especially for process development. For example, for typical stresses, what are the relative importance of the different important variables? Is preheating more important, or is rigidity of the part more important? This is a very essential thing when we develop the process. So this shows, for example, that for among different process conditions, preheat is very important if we want to control the residual stress, especially in OM type of wire arc additive manufacturing. Across different process variables, now as you can see, if we can again look at the temperature gradient, if we can reduce, it will reduce the overall residual stress. This shows the relative importance of the variables towards their influence on the final stress and distortion or delamination of form. These are the rough summary and outlook that computer-based models provide a quantitative insight towards understanding. Not only that, these models can help a lot towards process building if they can be validated properly. Of course, more work is needed to develop scaled up models that not only can predict process versus structure versus property reliably, but they can do it also for small to larger scales. I stop here. I will be happy if there are any questions. Thank you.
Thank you, Professor De. It is very interesting presentation, but unfortunately we have no time for question now. If there are any, we can have a short one. Okay, we can discuss. I have questions to you, but we can discuss it later at the panel discussion.
Yeah,
so
sure.
The next presentation is mine. I will show you now my screen. Okay, can you see it? Can you see it?
Yes, it's okay.
Okay. So let me start. Does it changes?
Yes,
okay.
Yes. You can
okay. Okay, let me start my presentation. I will go in some details on numerical modeling and exactly on the use of high performance computing for the process planning and microstructure control in additive manufacturing and precisely in laser metal deposition. So it's about the question of taking a lot of hours for a model, but you can use more high performance computer, and you can make this year or a lot of hours into some hours. So I will have a short introduction. I will tell about the model which is developed and its reliability. I will talk about the microstructure control, the process planning, and I will conclude everything. So everybody know here what is the additive manufacturing. It uses the computer aided design to build the actual 3D part from the computer design in layer by layer production in layer by layer technique. And I will speak about exactly the laser metal deposition and its optimization and the microstructure control. So such arrangement of the production enables a very high process planning opportunities. That's why I investigate this. So I will tell about numerical modeling in this sphere. And I am showing here how it is done nowadays by me. So I've got a lot of discussions and a lot of emails with a laser center engineer who has additive manufacturing technology. So we discuss it, and I try to help him to optimize this complex technology. What could be done here is to involve some automation for automation for this technology by using some web interface for laser center engineering, for preparing a task for simulation, which could be taken in a computer center, and the process map could be returned to the laser center engineer. And I also would like to show how it could be done in future. So the laser center engineer could share the part design, and the computer center, using numerical modeling, can develop the building strategy and return to the laser center engineer. So now we are not here, and we are trying to involve. So definitely, to have reasonable computing time, you have to use high performance computing, some big computers. I show here a computer in our institute that I used for my modeling. So it improves time for modeling, even hydrodynamic models, to a reasonable for investigation time. So I use an open source software for modeling. So I use OpenFOAM for CFD modeling models, and also I use CP2K open source molecular dynamics software for computational chemistry, which is also rather rapidly used in additive manufacturing and reinforces in investigations. So I'm not showing the details of the developed model, only the segments of it. So we developed a rather complicated model with a hydrodynamics, conduction, phase change involved, solute transport, and some powder feed. So this model, every segment of this model have to be verified, calibrated, and after that the validation of the whole model should be done. And the main question to such increasing the reliability of the model is that the data should be used different data for all of these steps. So here are some details on the verification of the developed model. So we use some analytical solutions for some simple problems, such as capillary drop, or some boxes with the fluid, to compare the results of the model. And we show here that our model works rather well, and also the spurious currents could be reduced, which is very favorable for reducing the computational cost of the model. So we also have calibrated our model in the sphere of numerical simulation of the microstructure. We use different data for the calibration and for validation. So we use a rather narrow laser beam results for calibration, and rather wide laser beam laser cladding for validation, and we have reasonable correspondence to the experimental data. So after that, we also validated the model. You can see the progress of such validation. So we validated the model for some different materials, for steel powder, and for the nickel-based alloy powder. We are now using rather wide parameters of the tracks for validation. We use also the wide range of the processing parameters, and we also validated the results for microstructure. So these are the recent results. The model show rather good correspondence, and even for the microstructure, the correspondence is very good. So after that, we start using the model, and we try to optimize the LMD process. And there are a lot of publications already published in literature about the processing parameters influence on the single track parameters. So, and in the optimal regime, they are rather straightforward. So you increase the scanning speed, and you've got the decrease of the width of the track, the height of the track is decreased, and also the microstructure is decreased. So we've got twice decrease in scanning speed, and we see the twice decrease in the average size. So the opposite has the laser power influence. So its increase results in the average size and width increase. So it is known from the literature, and also we can see it from our modeling. So, and what we go further is that we can control the properties of the resultant part by using different processing parameters. So, and this goes in the need of some optimization. So you need to optimize the single track parameters. After that, you go to the single layer parameters, and after that you need to optimize the multi-layer building, and then you get some objectives. For example, some certain microstructure of the part. But if you need to change to control the microstructure or some other functional properties of the part, you need to change processing parameters, and after that you will definitely have different track parameters, and after that you have to start again these optimizations to get your some different objectives. So our method is to adopt processing parameters of the single track. So we would like to make only a single track optimization and get different objectives. So I'm showing this on the example of the microstructure. So we use increased scanning speed to have a less average size of the track, and we use the change in the laser power, we can get the similar track geometry. So the height and the width of the track could be the same, while the microstructure is not the same. That's why we can control the microstructure in a part. So we also see that in the experiments. So the experiments correspond to our numerical simulations. After that, we also show the same for single layer microstructure. We show that we can preserve the scanning strategy, but we can control the microstructure of the layer. And following this method, we also show some typical heat dissipation cases. We found laser power to get similar the tracks with the similar geometry on different heat dissipation cases. And also we using our model, we show that we can plan the process, for example, with the acceleration, the finite acceleration aware, when on the tracks, on the tones with the radius below critical, where acceleration could not be reached. So the scanning speed is reduced, and after that we show that we need to not only to increase the laser power in such cases, but also we have to reduce powder feed rate, which is not very easy to do. But after that we can make the tracks without any defects, having the geometry of the melt pool the same as in on a thin wall. So these are my conclusions. So we developed a numerical model for investigation of laser in laser additive manufacturing applications. So we show the method for changing average crystalline size while closely preserving the growth parameters. We show also that the microstructure could be controlled in multi-track laser metal deposition, which allows building parts with a defined quality without any parameter optimization in terms of layer geometry and scanning strategy. Also, we discussed typical situation of heat dissipation. We show, we developed a process map for laser cladding of tracks with the same size. And we also show the processing parameters, how the processing parameters could be adjusted to correct some defects with on sharp turns. So that is all. Thank you. Any questions?
Thank you very much, Dr. Homenko, for following your time limits. And now we may proceed to the next speaker.
Do we have any time for questions?
Unfortunately not. I recommend to leave all the questions to the panel discussion.
Okay. So the next speaker is Dr. Ravi Babu. So you can start, please. We can't hear you.
Dr. Ravi Babu, am I audible? I think perhaps he has some technical problem.
Yeah.
Dr. Ravi Babu.
Are you here with us?
Yes, yes.
Okay. Would you start?
Yes. Yeah, my slides are visible.
Yes.
Yes. Good afternoon to all the delegates from both the sides. Actually, we are working on polymer and polymer composite based inks, and as well as composite filaments for structural component developments. Yeah. So when it is coming to the polymer printing facility at SICRI in our institute, we are having thermoplastic extrusion based system where we can melt the polymer and we can print based on this pneumatic pressure. And another one is we are having a pneumatic based printer where we can dissolve the polymers and as well as the polymer composite materials, and then we can print using the pneumatic based. And at the same time, we are also having inkjet printer, and then we are also having UV curing polymer printer and fused diffusion modeling FDM based printer in our facility. So at present, we are having 4 different projects, coming to these polymer and polymer composites. And we are working on majorly 3D printed polymer scaffolds for bone tissue engineering applications, and 3D printed monoliths for the gas separation, especially for the chemical industries, and as well as 3D printable batteries in energy sector. And we are also working for filament fabrication, because as we know that limitation of materials in terms of polymers when we are targeting for commercial applications. So based on that, we are able to make in-house filaments with pure polymers and as well as the polymer composite materials. This is what at present we are doing in different areas. So coming to this 3D polymer and polymer composite based scaffolds, as we know that the conventional technologies are there to make scaffolds. So there is a limitations of the conventional process, especially when it is coming to the biomedical. What is that exactly? When we are talking about implants, it should have a proper self proliferation and adhesion on the scaffolds. So here it is that it is having a possibility to have a tune the porosity where the cells can have a nice adhesion or as well as a proliferation in scaffolds. And at the same time, we are also targeting to go for a bioprinting, where we can have a printing of cells on a scaffold. And at the same time, even we are in future, we are planning to proceed for the organ printing. So it is possible to go for even a drug screening using this particular organ printing process. So now we are working for the cranial burr-hole plex. And here, as we know that the cranial burr-holes will be created when neurosurgical procedures are happening. So initially, when they previously they used to do the burr-holes, and when we are doing the burr-holes, at that time the bone will become a powder. So after surgical procedures, actually, we won't have any bone to fill that gap. So that's why what they used to do, they used to keep it open and they used to close with the scalp. So because of that, it will form some defects, and at the same time it will create post surgical treatment. So then based on that, the people are now coming up with the titanium metal plex. It's very expensive and it takes very long time to heal. And at the same time, results of titanium plex, we can see it here in
image D, and we can see the impression of this burr hole. So now the people are trying to proceed for this biodegradable cranial burr hole plaques. It means that it can regenerate the bone. So here we can see in image 4, and we can see that a nice cosmetic look after healing of the burr hole. So based on that, we are we want to develop a cranial burr hole plaque, and using our own formulation with the 3D printing technique. So first we have synthesized our own bioactive glass, and then we have reinforced in a polymer, and we made a ink. So the challenge here it is that when we are coming to the 3D printing, especially for these biomedical implants, so here it is how we are going to print in a composite. The reason is that it is easy to have a printing with the pure polymer. The reason is that it will have a less viscosity when comparing with the composite. So there the printing parameters need to be optimized based on this composite and as well as the pure polymer. So the when we are seeing, we have done a lot of trial and error procedure based on this viscosity. So pure polymer, when we are printing, and you can see that we have given the 3-color chart here in this the red color. It is showing that improper flow of bio ink. So improper flow in the sense when at this particular pressure and at the same time the printing speed, if you are fixing it maybe the 2 mm per minute or 5 mm per minute, we won't get a proper flow of printing. So then simultaneously we have increased the pressure, and for the pure polymer we are able to come up with a nice scaffold with 125 kilopascals and the printing speed of 2 mm per second. So, and at the same time, when we are going for a composite, why we want to go for a composite? The reason is that when we are seeing the human bone, it is a combination of both organic and inorganic material. So the inorganic material is a 70% and organic material is a 30%. Based on that, we want to tune it. So here it is that MBG is the inorganic material, and as well as the polymer PLA is an organic material. So we want to reinforce the 70% of inorganic material in the PLA, and we want to make a paste, and we want to go for a printing of a scaffold. That's a challenging, and we have to optimize the printing parameters to get a better printability. So blue indicates that irregular pore size and architecture during the 3D printing. Blue indicates that irregular pore size we are getting. The reason is that why we are selecting the 3D printing, the selective porosity is required to have a better cell proliferation and cell adhesion. So based on that, we are selecting this 3D printing. So when we are seeing the different pressure and the printing speeds, and especially when it is looking at blue color, there the pore size and architecture is not uniform. So then the green, we can see that we have loaded a different loading. We have to optimize, because directly we cannot load the 70%. Optimizing the printing parameters is difficult. So that's why initially we have tried with 10%, and then we have gone for 20%. Finally, we are able to achieve 70 to 30% combination of this polymer and bioactive glass. And at 200 kilopascals and 5 mm per second, if you're able to print the composite printer, we can achieve the nice with uniform porosity, and then we are able to come up with a scaffold of PLA MBG. So after printing, then we have tested in vitro bioactivity test. So you can see that nice when it is coming to the pure PLA. So we want to compare with the PLA and the composite. So you can see that hydroxyapatite formation. So in case of the pure PLA, the first day it's a very limited it formed, and when it is growing with respect to the day of incubation. So whereas in case of the composite, because the bioactive glass can give a better growth of hydroxyapatite. So based on that, we can see that the nice formulation even in the first day of incubation in the SBF solution. So the 3D printed components is able to give a better hydroxyapatite formation when we are having this composite. So it means that it is having the better porosity and architecture of the 3D printed scaffold, and it is showing it. So when it is coming to this in vitro studies like ulcerating grid staining, The images are showing that calcium deposition in 3D printed scaffolds, and at the same time mineralization ability also we can see in case of PLA composites comparing with the pure PLA, and the gene expression upregulations almost all shown in both the PLA and PLA composite, but the PLA composite is having a prominent results when it is coming to the cell adhesion or cell proliferation when it is comparing with the PLA. So this is what we are doing in the biomedical side, and then future we are planning to go for even in bioprinting of organs and other stuff. And this is a small work we are showing in biomedical side, and we are doing the multiple works in the same line for different applications. And coming to this 3D printed monoliths for the gas separation, the second project which we are doing it. So as we know that when it is coming to the chemical industries, especially catalysis or the adsorption process, so we used to do this packed bed reactors, when we are having the adsorption process. So when we are seeing this adsorption process, it's an irregular, packing of the bed. So because of that irregular packing of the bed, what it will happen? So whatever we are sending in the reactor, all the reacting molecules inside, it may not stay at the same time. So the reason is that it will form some channels. Some molecules may escape easily. It means a short duration of time it will spend in the reactor. And some cases it may form a pockets, it may stay for a longer time, and some molecules may have as for a theoretical value, it can stay the same time. So it means in a random packaging we may not get uniform what I want to say, the spending of these molecules in the time in the reactor. So here it is that we are having a possibility with the 3D printing, we can nicely tune the porosity, and we can maintain the molecules can stay at same time, equal time in the reactor, so that we can get a better efficiency in the product formation. So whether it may be adsorption process or whether it may be catalysis side. And another key point is that when we are going for industries, so the pressure drop, when we are having a packing, it will have a pressure drop. Because of that, huge energy penalty will be there. Here is that we can tune the porosity to reduce the energy penalty by reducing the energy usage consumption. So based on that, actually we are also working on carbon capture. So it means adsorption process, and when it is coming to this carbon capture, we are having a patented material in-house. So where the material can be absorb the carbon at flue gas conditions. So that's what the world is looking, because the reason is that already we are having a materials at the carbon capture like zeolites, metal organic frameworks, or the activated carbon, but these materials will work at high pressures and at the same time at room temperatures. So but the flue gas, whichever it is coming from the thermal power plants, it will come at atmospheric pressure. It means opposite. The conventional materials will work at high pressure, but the flue gas will come at 1 bar pressure, and the temperature is about 75 degrees. But these materials will work at room temperature or below room temperature. So because of that, it requires a lot of energy. So that is where the world is struggling to have a material where with a less energy penalty material required for the carbon capture. So there we are working, and we are able to achieve at 75 degrees temperature where the flue gas is coming, and it reached the US DOE target. And at the same time, we have also tested multi-cycle stability, and now we are going for a bulk synthesis of this material. So with this material now, conventional process we have done, and now we are going for a pilot scale studies for carbon capture at flue gas conditions. And now based on this, we have one project. So to make a 3D printable monoliths for the carbon capture. So that's what where we are doing it now. So we are having the adsorbent, and we are making adsorbent inks, and then we are printing the monoliths with different formulations, because it should have a nice mechanical strength. At the same time, we don't want to compromise on adsorption capacity. So based on that, we are also working with the different three formulations. And here it is that you can see that this is the CO2 adsorption studies powder adsorbent. This is actually it is in the studies are in like a conventional materials we have done, and now we are going for with our patented material. Now the works are in progress. So here it is that if you're seeing a conventional material, it is able to absorb around 1.2 millimole per gram of adsorbent, and whereas in case of adsorption with our monoliths, it is coming around 1. So it means that there is a little drop in adsorption capacity. This the reason is like to have a monolith, we used to add some binders. So there the binder volume maybe around 5 to 10% we used to add, and we used to make the monoliths. So if you're removing that, then the adsorption capacity is on par with the conventional process. So it means this 3D printing can have a good advantages even in the chemical industries when it is coming to the catalysis and as well as adsorption process. So coming to this 3D printing energy storage devices, we are working on this energy storage devices. So this is another project which we are doing it. As we know that lithium-ion batteries, we are taking one example. So why we want to go for a 3D printing? The reason is that if you are using the conventional process, very simple. So we are having some specific shapes and specific sizes. So when we are having the 3D printing, we can have a flexible batteries, and based on the the requirement. So it means we no need to stick to the specific shapes or specific sizes, because we will have a lot of design features when it is coming to the 3D printing. Another thing is that when it is coming to the lithium-ion batteries, as we know that the lithium ions used to shuttle from one electrode to another electrode. It means the cathode to anode, anode to cathode, when it is having a charging and discharging profiles. So here it is that whatever we are using conventional electrodes, these electrodes are 2D electrodes. So what is the issue with the 2D electrodes? We have to coat a very thin coating. So the reason is that if you're increasing the coating of the maximum coating, it means that if you're increasing the micron thickness levels more, then what it will happen, the lithium ions, whatever it is shuttling, those lithium ions cannot penetrate inside the pores. It means to the end. Sorry. So that's why if we are able to tune this porosity with the 3D printed electrodes, so we can have a better utilization of the electrode material, and at the same time even we can increase the thickness of the electrodes and have a better performance when it is coming to these lithium-ion batteries. And another advantage of this 3D printing in coming to these batteries, lithium-ion batteries, usually we used to use a liquid electrolyte, where it can have a shortage and it may have a accidents. So that's why the people are moving with the solid state batteries. But the issue with the solid state batteries is resistance between these electrodes and electrolytes to shuttling of these lithium ions. So that's why we are working and we are developing electrolytes and as well as the electrodes, so that it can have a better compactability and we can reduce the resistance between the electrodes and the electrolytes. So based on that, we have come up with a 3D printable polymer electrolyte, and you can see that flexible electrolytes we have made, and we have you can see that nice porosity of our membrane, and at the same time you can see that we are able to achieve 10 to the minus 3 ionic conductivity of our membrane. So what exactly we are doing now? Now we are progressing towards a complete 3D printable batteries. Completely 3D printable batteries means the electrodes, electrolytes, everything we want to do the 3D printing, and we want to make cells, and so that it can give a better performance. That's what we are doing it. So you can you can see that we have fabricated a coin cell using the 3D printing materials, and that's what present work is in progress. And coming to this another work which we are doing is a 3D printable polymer and polymer composite filaments. So actually as we know that there is a limitation of the materials. In this case we want to make composite materials, and at the same time in-house filaments in a cheaper price we want to make it. So whatever the available materials, say especially in-house, it means that in India, with that material we want to make a filaments, because most of the cases the filaments we are importing. So that's why the cost of the filaments are a bit expensive. So that's why we want to make in our in-house filaments, and as well as for when we are going for application side, industrial side, they will expect the composite components. So that's where we are working, and you can see that we are able to make our own in-house filament with the ABS, and as well as we have reinforced the graphene in ABS and as well as the PLA, and we are able to come up with the in-house made filaments, and at the same time we made components with the in-house filaments. And these components actually, when we are we are in lockdown, first lockdown in India, at that time there is a huge requirement of ventilators. So at the time completely the all India is in lockdown, so we don't have sources to make any ventilators. So whatever is possible within in our institute, we are come up with printing, because as we know that we have design, and with the design, if I want to go for a conventional way, so what it will happen, we need to make again a die and fabricating the components and bringing it will take a very long time. So in a short duration of time, within 20 days of time, we are able to come up with ICU ventilator with the 3D printed components, and now it is in the market. The broadline you can check, and this broadline ICU ventilator presently. Yes. Thank you one and all for patient listening to us. Yeah, thank you.
Thank you, Prof. Dr. Babu, for your vital applications. So we already used 20 minutes, so that's why we are going to the next speaker. We will have we may have some discussion later. So the next speaker is Professor Anatoly Bareysho. Are you here with us?
Лазерные системы.
Окей. Презентацию. Вот это, да? Все видно? Okay, I would like to present you some results by our cooperation scientists of the Physical Science Division of Russian Academy of Science and engineers of Laser System Company developing the advanced machines that open up opportunity for the new materials, practical application during the implementation of fundamentally new equipment system. The additive manufacturing technologies are among the most advanced and popular all over the world, and therefore they are one of the priority fields of research, engineering, and technology development in Russia also. We will present here the latest additive system developed mass produced by Laser System Company, which implement the technology of selective laser melting, SLM, one of the most interested and at the same time the most complex area of modern machinery production. This slide demonstrates the key scheme of a laser melting machine, laser scanning system, powder, and interaction between laser beam and the powder. The additive machine M250 and M350 developed and produced by Laser System. The name indicates the maximum dimension of the operation area or manufactured parts in millimeter. For example, the M350 means the 350 by 350 by 350 millimeters. The machines were designed to work with a wide range of various metal powders and alloys and can be easily adopted for materials of the different manufacturers, both Russians and foreign manufacturers. Technical parameters of the machines presented on this slide, and they meet the most strong requirements, most advanced requirements for machines of this type involved. And they are the only Russian SLM machine which have the certified to use a modern high-tech production line, including the aviation, aerospace, military, and the power engineering industries. The next slides demonstrate the software and hardware suite developed by our programmers and engineers, provide a reliable operation of the machines and technical subsystem control at full and the continuous monitoring of all operation parameters, as well as compatibility with almost all known formats and design documentation. Here is functional diagram, hardware, software, and some software for preparation, software of different models. And the scanning system, it is a very special system, 2 laser with output power up to 1 kilowatt. And difference from analog is the full overlapping of scanning fields of by both lasers, and both lasers refocusing in 20 milliseconds during scanning. It is very good. Maybe the best results involved. This is original powder fit and leveling system presented here. Service software, vacuum gas motors, machine, which was developed by us, absolutely original. And geometric control system online during the work. And finally, this is Laser Studio software, which can provide the operation with different engineering documentation. Here is some photo of metal parts growing in these machines, and the video, different processes, staging here, and the filling processes during complex product growth in the machine. However, the first initial test of the machines with growing real parts showed that it was very difficult to ensure the accurate quality of the obtained parts. The analysis of these results showed that the technology is very sensitive to many parameters of the operating process. And the process of interaction of laser beam with metal powders was accompanied by various high-intensity physical and chemical processes followed with absorption of and release of large amount of energy in very short time. It became clear that the successful operation of the machine required a deeper understanding of physical and chemical processes, the development of adequate mathematical models, and scientifically based algorithm for control parts creation process. We carefully studied all available funding and experimental and theoretical research on the process of interaction with laser beam with metal powders, and undertook our own experimental investigation also. Here you can see micrographs of the process, side view and top view of interaction of laser beam with metallic powder. The process of molten zone formation and intense particle emission are clearly visible when the laser beam comes into contact with the powder surface. It is clear that the process is very depends on laser powder and scanning speed. Changing the parameters, we can get absolutely different picture of the interaction. It is very important. No less complex and large-scale process. Not only micro-level, but the large-scale processes take place in the working chamber volume. Very false eddies and are generated due to interaction of the plasma stream flowing from the surface and metal vapors. The buffer gas heated in the boundary layer and the gas flow aerating the chamber. All the process are especially well observed during the high-speed Schlieren video recording of the working procedure. You can see the gas flow and even separate individual particle. It is clear that the high-quality operating of SLM additive machine is only possible if there is the right qualitative and quantitative understanding of all the processes taking place and the unification of the adequate mathematical models with control algorithm, i.e. the development of SLM machine digital twin. It was our task for our work. The digital twin includes both offline preliminary, does not depend on the SLM machine printing time, and online in-time simulation and modeling processes on macro level, meso level, and micro level. For example, here is an example of micro-level model and physical processes which take into account in this model. Here is gravity, surface tension, Marangoni effect, and so on. It is mathematical models, momentum equation, energy equation. The model was extension. Here is numerical implementation. Here is metal, blue gas is specified by the function presented on this slide. Он должен кино не показывать. Окей. This slide show result of numerical example for the calculation. Unfortunately, we cannot demonstrate the real process on video.
You can click on it. I guess you can. Okay. Never mind. I'm sorry.
Okay. Nevertheless, it is possible to see that the results of our calculation is very similar to the video recording demonstrated above. So it's micro level. Meso level model is consolidated hydrodynamics and thermophysics tasking for SLM process, and the simulation scale in this case exceed the particle size, and the medium is considered as continuous with the variable properties. You see here the meso-level models. Here is the mathematical also models, and using the here you can see the results of the simulation of the parts and experimental results, the sample growing. Qualitatively, the results are absolutely the same. No overheating zone observed. So the first examples that would work together our mathematical digital film and the real experimental results. The simulation of operating procedure in the chamber is no less important part of the machine digital twin. The next several slides illustrate the calculation procedure and some result also here. It is our software vacuum gas system. Here is the same simulation, mathematical model, and over here is it is working. You see the real moving of gas inside within the chamber, and it is also results of simulation of vortex flow and trajectories of individual particles here. We consider it in the micro level also. We take into account convective upgrade flow, gas, droplets, solids, ablation plasma, gas phase, molecules, neutral atoms, ions, electrons, metal vapors, droplets also, and two-phase convectively unbalanced flow. Here is some illustration of this, and here you can see the main conclusion made from the calculation and experimental studies. There's many interesting effects. However, mostly we can use in our model of digital twin. And a large number of the calculation, theoretical and experimental studies led to development of physical and mathematical models of all the working process for melting powder and growing real parts, as well as model of the operation of all subsystem and elements of the additive machine, which ultimately made it possible to develop effective control algorithms for producing high-quality parts which meet the requirement of customer. Look here, the samples for testing and see the microphoto. This is scale 0.1 millimeters. You see how good surface here. Melting, you can see melting tracks, which scale is less than 1/10 millimeters. And moreover, we presented here the result of porosity study by independent certified laboratory of leading Russian institution. For example, here is Russian Aviation Materials Institute, VIAM, which tested our samples running on our machine with digital twin, and the minimum pore volume ratio was 0.0%. It is by one order less than best samples created with the use of casting technologies. But the next slide for the same materials made for tested in laboratory of Russian Marine Materials Institute, Prometei. It's also independent certified laboratory. And we demonstrate, and here the porosity less than 0.001%. It is such a best, it is correspond to the best characteristic of the materials of parts manufactured with the use of pressure shaping. So it's fantastic for additive technologies. The same positive results were obtained in study of growth demonstrated samples intended for define of surface roughness, the porosity and geometric accuracy of manufacturing. The next slide, following several slides, show samples of tested or all the parts. For example, here is the impeller of small-scale turbine engine for a managerial vehicle. You see the roll thickness is 0.2 millimeters. And it is working somehow. Here is another waveguide of aluminium alloy made for leading Russian satellite producer information satellite system. It also made all customer requirements. Here is also an example of our work presented here, very different, but all of them meet all customer requirements. Special interest, this slide. Here we demonstrate you the mixing head of rocket engine for spacecraft. Conventional technology, by conventional technologies, this mixing head consists of more than 100 parts, which produced separately and after welded together. And labor intensity of such mixing head is about 1,000 hours. While using the additive technologies, we can redesign the system as one digital model, absolutely the same geometrical characteristic. Labor intensity on additive machine is only 1 hour and the better quality. It's fantastic results, but unusually, because the advantage, real advantages of additive technologies can be completely revealed if the manufactured parts are designed taking into account all the possibility for obtaining the most various and complex geometrical shapes thanks to additive technology. It's called generative design. This approach fundamentally different from the normally used standard CAD, computer-aided design software, and is born right now with the development of additive technology. The first step is in this direction is the topological optimization. This approach makes it possible to obtain less materials intensive parts or lighter weight without changes of very functional characteristics. It is especially important for aviation and aerospace industries. Look, here is some examples.
I'm sorry, Prof.
That's okay.
We are now out of time.
Two slides.
Okay.
2 slides more. And finally, our last work for geroid structure modeling. It is an example of metamaterials having unique properties depending on the micro and nano geometry. And interactive study right now. In principle, it allows programming the properties of product and object. Additive technologies, especially the SLM, open the large possibility for creating such metal metamaterials. Next slides are our theoretical calculation and experimental design, experimental samples of the metamaterials, geroid type, and real application for example, turbine, gas turbine nozzle for cooling of the nozzle. So I finish. Thank you for attention.
Thank you, Professor Bareisho, for presenting high-level equipment. But we have your contacts, and we have to go further. Thank you. Okay, the next speaker is Dr. Atasi Pal from CSIR, from the Fiber Optics and Photonics Division. We can see your presentation.
Okay, thank you. Is it visible now? Yes.
We have we see the 10th slide. So then you should start from the first.
Yes, this is the first slides is there. Yes.
No, it's not the first now. It's still the 10th.
Okay.
I'm not sure whether it's all right.
No, this is no. I'm just sharing again.
I used to share the whole my screen, but not the certain presentation. If you can do it.
I'm not able. Yes, this is the screen. So,
yes, now we can see the whole your screen. Okay.
Yes.
Please.
Yes. Good evening to all. It's my pleasure to present our activity in fiber laser at Center Glass and Ceramic Research Institute in Kolkata. In our fiber optics and photonics division, we are in research on fiber laser technology development in the operating wavelength region of 1 micron, 1.5 micron, 2 micron. Our focused applications areas are material processing, additive manufacturing, marking and engraving, welding, and surgical device. Laser is a device that emits monochromatic light with high level of coherence. This can be an effective energy source in additive manufacturing for successive material deposition at designated targeted areas. Laser beam can be transferred large amount of energy into a microscale focused area to solidify or cure materials in air instantaneously. Therefore, it enables a high precision and high throughput manufacturing for a wide range of materials through SLA, SLS, SLM, and LENS technique. In commercial 3D printing mechanics, carbon dioxide, Nd:YAG, and ytterbium laser and excimer laser are commonly used. The laser parameters, mainly the operating wavelength, the power or energy, pulse duration, and spot size influence the manufacturing process. CO2 laser at infrared wavelength range around 10 micron is most widely used in additive manufacturing, mainly for special materials for optical components, silver or gold mirror. However, in metal-based additive manufacturing, there is a limitation in throughput due to low light absorption coefficient in this wavelength region of 10 micron. Also, the instability in laser output at high power level for gas-based gain medium and the free space optics-based beam delivery for CO2 laser is really a limitation. To overcome that, Nd:YAG crystal-based laser at around 1 micron is used in industries. But nowadays, in additive manufacturing, ytterbium fiber laser proves its efficiency, replacing the Nd:YAG laser. The ytterbium laser is most suitable for high power generation because of high quantum efficiency along with the high electrical to optical efficiency, because the optical fiber is the gain medium and all components are optical fiber based. And as it is an all fiber configuration in fiber laser, it provides an excellent beam quality, and also it gives a robust system against the environmental disturbance, and the system compactness is very much important, and where there is a operation is almost maintenance free. However, because of the material absorption at the laser wavelength, Nd:YAG and ytterbium laser is good for metals, but CO2 is best for polymeric materials to get the high throughput. In our lab, we have facility for fiber fabrication from raw materials and the drawing of fibers and the characterization and the laser development using the developed fiber. For the fiber laser, there is a requirement of synergy of expertise in the three domain, mainly three domain. One is optoelectronics to frame the optical engine as a laser resonator, and there is a requirement of mechanical design and manufacturing for the cold plate preparation for the optical engine cooling, and also there is a requirement of environmental control housing for the packaging. And another part is electronics and control engineering to control the laser set of laser diodes and interfacing and feedback for monitoring and display. At CDCRA, we are especially working on optical engine, where there is a one part is the fabrication of optical components and another part is the design and formation of the optical engine. In our lab, we have the facility for optical preform fabrication. We fabricate circular optical preform using modified chemical vapor deposition with vapor phase deposition technique. Then we go for the shaping of the optical preform to give a shape of octagonal, and this is required for the coupling of punctite with the core region. The core region is doped with ytterbium. If it is a ytterbium doped fiber laser at 1 micron, it can be doped with erbium and erbium ytterbium to get the lasing at 1.5 micron, and holmium and thulium if we go for a 2 micron laser. With that shaped preform, we go for the fiber drawing using our fiber drawing tower. This is the ultimate gain fiber with the octagonal shape cladding and the core doped with ytterbium. To make the laser resonator, we need fiber grating in the both sides of the active fiber to create the resonance. This is our fiber grating system to make the fiber grating pair as the desirable operating wavelength. In order to couple the multiple pump source to a single optical engine, there is a need of pump combiner. There is a requirement of pump combiner to scale up the laser power, because the laser diodes are limited at a certain level of power. So pump combiner is combining three or six pump source, and it gives all the laser output to a single fiber, which is coupled with the optical resonator. And here we are preparing 2x1, 4x1, 6x1 fiber pump combiner to couple the multiple pump lights at different wavelength. This is our lab setup for design the laser cavity. Here the most important part is the splicing of different components, maintaining the composition of different component fiber. That there is a requirement of recoating of the splicing region to get the flow of the pump light throughout the optical engine. There is a requirement of maximum coupling of the pump light to the core region where the main gain part is there. There is a necessity of handling the unused pump power for the high power laser, and we need to design the laser so that the waste heat is minimum and the laser should be stable in terms of temporal profile as well as spectral profile. Then we need we go for the rigorous characterization of the spectral property, temporal property, noise characteristics, and if it is a pulse mode, then the pulse width of the laser, and we have a beam profiler to measure the beam quality of the designed laser, and there is a thermal camera to analyze the total heat profile of the optical engine to ensure the stability of the laser for long-term operation. In the CW mode, the laser power remains constant independent of the time. There is some requirement of CW laser for the metal additive manufacturing. So far we achieved 520 watt laser power using silicium developed ytterbium doped fiber. So the beam quality is less than 1.2. So this power level with the custom beam quality, we can go for a complex structure additive manufacturing. Where CW laser is giving a continuous power, the pulse mode laser emits the laser power for a short duration of time at a particular repetition rate. The pulse mode can be achieved through Q switching, mode locking, and the pulse pumping. And the pulse laser can provide a much higher peak power than the continuous mode. So the light pulse with a high peak power can increase the temperature of material instantaneously with minor thermal energy dissipation to surrounding material, which makes it easier to reach the threshold energy required for the machining. Whereas the continuous wave laser, the same average power would be diffused to the surrounding materials, which makes it difficult to reach the threshold energy. So in terms of additive manufacturing, for the precision manufacturing, there is a pulse laser is much more suitable than the CW laser. Here, this is our Q switch pulse laser, which can provide up to average power of 20 watt, whereas the maximum peak power is 10 kilowatt. The beam profile is perfectly Gaussian, which is very much useful for precision marking and engraving. The energy greater than 1 millijoule with the good beam quality of less than 1.6 is useful for marking and engraving and micro manufacturing. We just integrate our Q-switched laser to a marking system, and this is the marking done by our laser, and color marking was also possible using that. Another kind of laser is a femtosecond laser, where the pulse width can be reduced up to in the femtosecond region, and we use the CPA method to get the amplified short pulse. Our target is to get sub 300 femtosecond pulse with the energy more than 1 microjoule. So this laser is useful for cold ablation kind of manufacturing. So there is during the fabrication using that femtosecond laser, the surrounding will be completely cool, and there will be no heat dissipation to the surrounding. So it can be do very precision marking and micro drilling also. These are our prototype. One is the 60-watt prototype for the CW, another CW, and the modularity is up to 500 watt. And those all are, we are going for filter. The Q-switch laser is used for marking and engraving, and the femtosecond laser we are using for the nonlinear wavelength conversion and for the ultra precision micromachining. The another wavelength region is 2 micron region. We are using a thulium fiber for that. Here the operating wavelength is in the range of 1.94 micron, 2 micron. Our main target of this of preparing that wavelength region is for surgical application. We developed our 30-watt prototype for lithotripsy, and now the power is up to 200 watt for tissue surgery. And this laser, we are also trying to convert this CW laser and also QCW mode for the material where the absorption is high in the 2 micron region. This is mainly the biological and other organic materials with significant water content, and as well as plastic and glasses where the absorption is quite high. So all this laser design we are doing for in the first the lab scale configuration optimization. Then we go for our lab scale prototype and go for some filter. After that, once the technology is ready, then the industry can take that technology for their modification, and as per the system requirement, they can go for the development of the pilot unit. That is all we are doing in our fiber laser activity at CSIRO. Thank you.
Thank you, Dr. Paul. You were very precise. That's why we have 3 minutes for questions.
Yes.
So if there are some. Okay. So thank you for your interesting presentation. And let us continue. The next speaker is Alexander Dubrov from Institute on Laser and Information Technology. Alexander, I can hear you. I can see you. So please.
Okay. Okay, I'm trying to share my screen, but okay, yes. Okay, can you see it?
Yes.
Okay, so hello everybody. My name is Alexander Dubrov. I'm a senior scientist of the Laser Matter Interaction and Additive Manufacturing Laboratory in the Institute on Laser and Information Technology, Russian Academy of Sciences. We're placed in Shatura, Moscow region. I'm glad to be here. I'm glad to make this talk. So in my talk, I wanted to briefly cover 2 recent direction of work of our laboratory. And generally the aim of our works of works of our laboratory is to develop the monitoring and control systems for additive manufacturing, to develop the approach to dealing with data which we get from these systems, and to research the physical processes which follows laser matter interaction in general and additive manufacturing in particular. So, but first of all,
Alexander,
yes.
Are you changing your slides?
I'm trying.
They are not
I
changed.
succeed.
Oh,
Yeah.
okay.
Okay, thank you. So first of all, I wanted to say a few words about our research facility. We have this machine. It's a laser metal deposition machine. It's developed and built here in our institution, in our laboratory. So when we developed it, we focused on two aims. Because it's a research machine, the first aim is to have the ability to integrate the monitoring equipment there, easily integrate. And second one is to have an open architecture of software and hardware platforms of this machine, so we can easily have access to any parameter in any time, and to any data of any sensor in any time, to get it, to collect it, to make some decision, and to react if we need it to modify the process. So the machine consists of fiber laser for 100 watt. It consists of robotic arm, and it uses powder feeder through the coaxial nozzle in laser head. So I'm sorry. Yeah. There are some sensors already integrated. There are multi-channel optical sensor, which allows us to independently register optical emission in several spectral range, which can use, for example, as a two-color pyrometry or laser reflection radiation sensor, and so on. Also, we have a high-speed imaging system in a coaxial configuration, and also the acoustic emission sensors. Okay, and so the first part of my talk is devoted to analysis of melt pool behavior using the optical monitoring. So we developed the algorithm and a software which can analyze the frames from the coaxial high-speed imaging and locate the melt pool region, and to calculate the key features of it. Among them, the area of melt pool, the brightness temperature, the major and minor axis of equivalent ellipse, which can be treated as the length and the width of the pool, and several other statistical features. So we have then time dependent or spatially dependent variation of that of these features, and we can use it as a real-time analysis, or we can use it for afterward analysis of recorded video. And worth noting that the melt pool behavior is rather violent. We know there is a high temperature gradient on the surface, so we have Marangoni forces, which leads to high convective behavior of the melt. So all the variation of the signals we basically have because of this convectional behavior. So we perform several experiments. We made stainless steel. We made a single line deposition with variation of velocity, and simultaneously we registered the coaxial video signal. Okay, so here the spatial dependencies of some of the features. On the upper oscillogram, we have the inverted temperature. It's gray, and the area. The temperature is inverted just for convenience, so we can see the strong relation between these features. And on the bottom oscillogram, we also have the length and the width of the melt pool. So the relation is obvious, but behavior is rather sophisticated. And to analyze the joint behavior and to analyze maybe some oscillatory behavior of them, we can use we use the short time correlation approach, which are some way similar to short time Fourier transform or wavelet transform, close in meaning that we performance this transform is in many overlapping short intervals, but use the correlation transformation instead of Fourier or wavelet. So, sorry. So after this transformation, we have 2D distributions like this. So in x-axis we have its time or space, and in y-axis it's essentially the correlogram. So if we look to the distribution of temperature and area, we see periods of strong negative correlation of them, and also we see the periods where is no such thing, and also we see this horizontal lines, which are oscillatory behavior, correlated behavior of these features. And worth noting that it lasts for some time. It lasts without changing, and then it switch to different states. So we always have some high frequency behavior, but it change periodically. This behavior is around can be characterized by frequencies around 140 and above, and it's the spatial range of it is maybe 30 70 microns, so it's well above well under the size of the melt pool, so it's a reflection of some convective motion of the liquid. So let's add to this distribution another one distribution of minor and major axes. So it's a joint behavior of length and width of the pool. And distribution looks different. It essentially have periods of positive correlation, negative correlation, and so on, with changing. And the interesting thing that when these two features have a positive correlation at the same time, we have a strong negative correlation between temperature and area. When we see their negative correlation, there is no such thing. And this is have a sense, because if the length and width of the pool changing in one way, for example, growing or diminishing, so the melt pool essentially is shrinking or growing. If we have negative correlation, so the area may be not changing at all at this time. So these periods basically defines some change in behavior of melt pool, and when this behavior change, with them we see the changing in high frequency components on the distributions. So this experimental data can be explained that the melt behavior, the melt dynamics in this process is characterized by presence of many periods during which a certain ordered character is preserved in it. So we can say it's some kind of stable states which last for some time and then change to another state. This state is essentially some stable structure, convective structure in a melt pool, and then it changed to another structure. And because the convective motion in a melt pool make a big deal in heat transfer, so different convective structure can have different ability to transfer heat from the surface to the bottom. So these states also can influence the solidification and melting. So it's rather interesting to analyze it in context of monitoring, online monitoring of the process. So more deep analyzing of this topic you can get in our recent paper. Here is the link, and I would go over the next part, which is about the process modification, and I mean by this combining the laser metal deposition technology with the laser remelting. Why do we need this? Why we can think about this? In terms of a quality of the material, we know that we need to use some certain parameters, some certain process parameters. We can define them, we can choose them, and so we can say we should use some optimal process parameters, and then the material will be we wouldn't have flaws, faults, but this process window is rather narrow, and it depends not only on the material but on the part itself. So if we look to this exemplary picture of the part with combination of thin walls and full body parts. So we never can choose one bunch of parameters which fits all the parts of it part. Somewhere we will be under melting, somewhere we will be overheating. So one of the way to deal with this situation is to add an additional step. We can use a laser remelting after each layer is built. So we can either we can remelt the material. So if there was some pores, we can bring this pores again to liquid and evacuate them, or we at least we can make the surface more even. So this probably give lesser chances to have a interlayer porosity on the next layer. So we perform some tens of experiments. We basically grow several tens of samples with combining LMD and laser remelting steps from stainless steel, and there was different velocities, different overlapping factor, and on the laser remelting step we basically was mainly changing the remelting velocity and the diameter of the beam. So yeah, here I can I should say that we should define two types of porosity which we can face there. So it's an intra-layer porosity or gas porosity, which basically is a gas bubbles which were in melt and then they solidified. Or it can be interlayer porosity or technological porosity, which occur if the technology is bad. So we under melting, not fully melting all the material. So we have voids on the border of beds or layers. And in this this work, we were mainly we have our main goal to explore the interlayer porosity evolution. So we choose the parameters of LMD. So we think this parameter are not non-optimal and would give us some porosity from the beginning. Okay, so LMD samples gives us, and then we measure the residual porosity on the samples and analyze that. So LMD samples gave us the porosity level from 0.6 to 1.7%, and the best regimes of laser remelting could give us lowering of the porosity from 2 to 3 times. But there were much more regimes, and if we could look here, the void void markers is the remelting velocity, and field markers is a residual porosity, and this separated markers is initial porosity of the LMD, single LMD samples. So we see that we achieve the lesser porosity with intermediate scanning velocities. If we go too slow or too fast, we still remove some porosity, but not all, not going to the best results. I mean, but this concerning the total porosity. If there is an intralayer porosity as well, but it's a little more trickier with it, because the initial level of intralayer porosity was rather small. So this void markers is the initial porosity, or initial level of gas porosity. And the other markers is porosity after the remelting with velocity ascending for different regimes. So
I'm sorry. Very interesting, but you need to finish.
It's almost, I think it's the last slide.
Okay.
Yeah, I'm sorry. Okay, so we sometimes we can get a little more, a little less, even less porosity than the initial, but most of the time we make things worse. But it's a compromise. Because we here we get maybe several hundredth of percent of intralayer porosity, but remove some tenth of interlayer porosity. So it's a compromise. We see here the initial section where the technological porosity with almost known gas porosity, and if we use remelting with velocity 6 times the initial velocity, we remove all the technological porosity, but bring new gas porosity. So yes, thank you very much. It was a very brief description. If you have some question, I would be happy to answer, but I think I have no opportunity. Thank you very much.
Thank you, Alexander, for your interest in science, for us, interest in research, but we have to go further. So the next speaker is also from the CSIR, Dr. Patanayak. I'm sorry for my pronunciation, but it's rather hard to be precise here.
Yeah, thank you, Maxim. So you are correct pronunciation, Patanayak. So my initial name is Deepak. So are you able to hear me and my slide is visible?
Yes.
Thank you. First of all, I would like to thank the organizing committee for giving me the opportunity to share my ongoing research activities of my group on role of process parameters on component development by selective laser melting technique. Here, basically, I will be discussing two different aspects. One is the process parameter, how it basically helps us to develop components of density close to the theoretical density of the metal or alloys. And subsequently, I will be discussing how we are trying to develop bone scaffolds or metallic implants using this selective laser melting technique. And finally, I'll be discussing how the surface functionalization of selective laser melted metallic implants basically helps for the osteointegration or bone integration in animal up to in vitro and in vivo study. For those who are not aware, CSIR basically is a public funded institute, and we have 37 laboratories all over India. And I belong to CECRI, Central Electrochemical Research Institute. That's the southern part of India. It's located in Tamil Nadu. So we have 100 plus scientists and 200 supporting staff, along with 100 PhD students working on different areas of corrosion, fuel cell, battery, and other areas. And in my research group, we are working on biomedical implants development using additive manufacturing or selective laser melting technique. And also we are working on AM for different other functional application. As we have been discussing, additive manufacturing technology has several advantages. Because of that, it is a growing technology for the next 10 to 20 years, I would say, because it has advantage of wastage of material, which is very minimum in the material or in terms of powder, and it can save a lot of time for the fabrication of the components, and we can make large number of components that can be manufactured at a time. And the most important advantage is we can design and develop any kind of porous component with complicated internal geometry, which is very much important for bone tissue engineering application and for other structural application also. And the added advantage, we can make any kind of customized component for any functional application, and this technology can be extended to polymers, ceramics, metals, and their composites. But there are several lot of challenges are there, which we have been discussing from the morning, that we have very limited number of additively manufactured grade metal powders. And we have been discussing that how to go for the large component manufacturing. And since the cost of the AM grade powder is little high, that's why the component cost is also going high. So these are the challenges which needs to be addressed in future. Basically, if you look into the basic principle of the selective laser melting, I don't need to go in deep, but we need to design it using that CAD or CAM design software. We have to make the 3D model, and from this 3D model, we have to slice it into several layers so that each layer will appear like a 2D layer, and layer by layer from the bottom to top, the laser beam basically selectively melt the metal powder and build layer by layer to construct the 3D three-dimensional object. So this is the additive manufacturing facility that we have created in our institute. And apart from that, we have all other the post-processing facilities available in our institute after building the component, removing the component, and post-processing treatment can be done at our facility that I have shown here. And since we established the facility in our institute, we have been working in various domains, and some of the components that I have shown here in the right hand side. Basically, we are working on development of various process parameter for wide range of AM grade metal powder, which are listed here. And also we are working on the process parameter optimization for irregular and indigenously developed powders for production of cost-effective component. And also we are doing the post-processing of AM grade components and its effect on microstructure and mechanical properties. Basically, while designing any kind of component using any kind of metal, AM grade metal or alloy powder, we need to optimize the process parameter such as laser power and scan speed, scan strategy, hatch space, etc. To optimize the process parameter so that we can get the component of density close to the theoretical density of the metal or alloy system. So I would like to show here an example of the process parameter that we tried to optimize for aluminum alloy AlSi10Mg alloy, where we selectively chosen the laser power, scan speed, and hatch space and layer thickness, which are shown here. And when we tried to print the coupon sample, we found that some of the samples failed in between. And then we tried to investigate in terms of the energy density, and we tried to calculate the volumetric energy energy density. And here you can see when the laser power is low at a fixed scan speed of 370 to 900, we found a kind of irregular porosities. And when we went higher laser power, you can see the irregular porosity has been changed to circular porosity. So we from this overall overall slide, I would rather say that the trend of porosity basically changed from the lack of fusion or irregular porosity to keyhole or circular pores or gas porosity when we went from the lower to higher volumetric energy density. And the energy density, basically from this slide, we can get the information that if you have the energy density, if you want to increase the energy density should be increased if you observe the lack of fusion porosity or irregular porosity, while the energy density is to be decreased if it has basically a keyhole porosity. So going a little more deep, actually, what do we understand by this keyhole porosity? Basically, this happens or occurs because of higher laser power and lesser scan speed, which mainly causes the overmelting and distortion of the edges. And this keyhole porosity, as I said, is basically a gas porosity, and these gas bubbles will entrap in the melt pool due to the surface tension gradient, which is basically known as the Marangoni effect. And coming to this lack of fusion defects, basically these are the irregular shaped defects which happens due to lower laser energy input for a particular scan speed. And this means the laser energy is not sufficient enough to penetrate deeply to fully melt the metal powder. And then we thought of going a little beyond of scan speed, and this is the total window that I have shown here, the laser power to scan speed, and this is the optimum process parameter window where if you for this alloy system where if you choose in this region, you can have the defect-free component. But if you are going for higher laser power with the lesser scanning speed, you can have 3 different area of defective zones. That is the region 1 that creates the, because of the low energy density, it creates the lack of fusion defect. And if you go to the region 3, where the because of the high energy density, it creates the keyhole porosity. And when you go for region 4, where too much high energy density, that lead to shear stress, and that shear stress leading to the failure, and we need to stop the printing for those samples. So this is how actually we optimize the process parameter for one system, and we use to optimize for every new material or new alloy system that we get. And based on the optimized process parameter, we try to make a suspension boost. This is for two-wheeler component. This is a very simple component, and we wanted to validate how the optimized process parameter component basically giving the properties compared to the conventionally manufactured boost component. Similarly, we do a lot of work on different system of titanium metal as well as titanium alloy system on process parameter optimization. Here you can see when we have an optimum laser power to scanning speed ratio of 0.5 and we can obtain the density of the component close to the theoretical density of the commercially pure titanium plate. And when the question comes, what is the minimum wall thickness that you want to print? Suppose when you are going for the hard space, basically hard space, as you know, is the distance between the two laser beam. So when you are going for more thinner wall, then that time more closure hard space will be better, or it will be advisable to go for the overlapped laser scanning. Will give us the better dense component. Here coming to the titanium 6 aluminum for vanadium, where we did a lot of studies we have done. Because of the time shortage, I am just showing one typical example where you can see when we have the hard space in between 80 to 120 micron, we can get the density of the component close to the theoretical density of the titanium alloy. Basically, what happens in this selective laser melting process, the formation of completely melted zone at the center of wall when the laser moved. And because of the when the laser moves, this heat conduction from the melted zone towards the powder happens, and because of this formation of an incompletely melted layer on the wall, because the metal powder, since entire surrounding of my powder bed fusion technique where powders can get attracted towards the melt pool zone and try to attach to the wall. And basically for certain application, this type of loosely bonded particles are not advisable, because for if we are talking about biomedical application, this type of loosely bonded particles are not advisable, because many times it can get detached in the human body and it can deposit in the spleen or some other body parts and leading to cancer. So that's why actually we need to do some kind of post treatment to remove this type of loosely bonded particles from the additively manufactured component. Here I can show an example slide when you as fabricated or as printed component, you can see a lot of metal particles are sticking to the wall. And we followed a simple heat treatment in inert atmosphere, and you can find that these loosely bonded particles form the neck and got sintered over the porous wall surface and forming the micro pockets. And these particularly this type of micro pockets are very much essential for biomedical application, because the tissue ingrowth can happen inside the pores or inside the micro pocket, and the interlocking of the implant with the new bone formation through the tissue ingrowth will be more better, and the strong implant fixation will be will happen. But you can immediately it may come to your mind that if you are doing the heat treatment at 1300, definitely it may affect the grain refinement of your microstructure of your sample, as well as it may affect the mechanical properties. So we investigated this and we found that as printed, because of the laser printing process is very rapid printing and cooling process, that's why very fine grains as we could observe. But when you are sintering or heat treatment, we are doing above 1000 degree, you can find the grain growth has happened and grains become large. We evaluated the mechanical property and the tensile property, and we found that an example here I have shown the tensile strength has decreased from 500 to 400, and on the other hand, the elongation was increased to 30%. But for biomedical application, actually this elongation is very much essential and advisable. And although the mechanical property is decreased, but it is more than enough for making any kind of bone implant application. So using this, we wanted to go further that because as you know, if you look into the bone anatomy or bone has different pore size and pore geometry. That's why actually we try to print samples that what could be the minimum pore size that we are able to print, and you can see around 200 micron pore size we can also will be able to print using this technique. And we wanted to see the validate the continuous porosity, whether we are able to print or not. We did the CT scan image. You can see there is a continuous channel type pores we are able to design. And you can see another example of a functional graded porous structure where the large pores are outside and inside is the smaller pores. So these type of designs actually we try to attempt, because suppose you want to develop or design any kind of bone implant with a different irregular geometry of pore size and pore structure, that will that may require the understanding of what could be the minimum pore size and pore dimension that we are able to print. And here I have shown some of the example of the different type of porous structure, and this is the dental screws that we have printed. This is the cancellous bone structure, and basically this is the CT image of the lumbar, and we have we are able to design the lumbar of cancellous bone structure. And here you can see this is the titanium porous structure from the CT scan data, and from there actually we have designed the metallic porous structure. And these are the different type of cranial implant for the head injury patient we were able to design by using this selective laser melting technique. But basically what happens when we design any kind of bone implant and we do the in vivo study, and we found that as printed or as developed 3D printed or SLM implant, when we put in the animal model, we found that there is a scar tissue formation, and that basically prevents the new bone formation directly adhering to the implant surface. This black portion is basically our implant porous structure, and you can see there is a scar tissue that basically prevents the direct bone formation adhering to the implant surface is minimum. But in order to improve, because for tight fixation or for permanent fixation implant like hip, knee or spinal implant, those implants basically going to stay in our body for at least 20 to 30 years. That's why actually direct fixation of the implant with the living bone is very much important. That's why actually in order to avoid this scar tissue formation, we need to do some kind of surface functionalization of this 3D printed or SLM scaffold. And this is a schematic diagram where basically we tried different type of surface treatment to improve the surface morphology of 3D printed or SLM sample, so that the bone integration can be faster or can be enhanced. So little going more detail into how we are trying to induce the biological activity of this porous scaffold of titanium and titanium alloys for better integration. We are attempting various types of surface functionalization of SLM scaffold, and these are the different type of techniques we are following in our group on either chemical modification or electrochemical modification, or in fact we are also doing the calcium phosphate coating over the implant surface by various technique, because as you know our bone composition is mainly calcium phosphate. So if we can have a coating of a calcium phosphate over the metal surface, then the bone integration will be faster and will be more faster, and the mechanical rigidity will be provided by the 3D printed structure. So coming to more detail, actually here what we did actually, since we are using this spherical metal powder for additive manufacturing process, and here I have taken this metal powder and we did the simple chemical treatment using alkaline or acid medium, and we modified the surface, and you can see this spherical titanium and titanium alloy surface got modified by this chemical treatment because of the chemical reaction that happens, and it forms a nanostructure network over the spherical titanium particle, and it forms a sheet-like structure of basically a hydrogen titanate layer. And basically this titanate layer, when you will be able to successfully incorporate various beneficial elements like calcium. Suppose calcium, as you know, is a bone forming or bone accelerating agent. So, and also sometimes actually this antimicrobial agent also, like silver or zinc or some other elements, we try to incorporate from in this titanate layer, so that we can get other beneficial properties like antimicrobial activity. The reason why we are more concerned about antimicrobial activity of the implant, because many times during the surgery, if the surgeon doesn't take proper precaution during surgery, and if any bacteria comes in contact with the implant surface and the surgery is done, this bacteria basically create the infection and cause formation, and that will be ultimately leading to the implant failure by the post formation, and then subsequently it will be a painful process to do the secondary surgery and removing the implant and putting a new implant. It is a tedious process. That's why actually in recent years a lot of researchers are working on how to provide the antimicrobial activity to the implant surface, so that any bacterial contamination, bacteria comes in contact with the implant surface, that can be killed before the surgery process. And this surface modification process, basically we wanted to evaluate the bioactivity. Basically we took this powder, surface modified powder, and put in the simulated or physiological body fluid solution that basically contains the composition or chemical composition of our blood plasma. From there actually this calcium phosphate basically deposited like cauliflower structure, you can see, and this indicates that the surface modification that what we have followed here basically improve the bioactivity, biocompatibility of the surface. And we have taken this additively manufactured titanium metal, and we have followed various type of surface modification approaches depending on what application we are looking for. You can see nanoporous network structure. The pits-like structure has been formed by different type of chemical treatment. And here you can see this is the we have taken the cross-sectional image, and you can see we have grown a 1 micron thick titanate layer. There basically we try to incorporate calcium and silver ions, so that the calcium will basically accelerate the bone formation, and the silver basically provide the antimicrobial activity. And this porous network structure is advisable because the cell growth can happen inside the network structure, and basically that will help for the interlocking of the new bone with the implant surface. And this is a HR10 image where you can just see the silver nanoparticles which are decorated over the titanate structure that provides the antibacterial activity. And this is the titanium 6 aluminum 4 vanadium 3D printed scaffold that we have modified even inside the pores also. Because of this chemical treatment, it helps for uniform treatment of the porous network formation even inside the porous cavities. That is the advantage we have in this technology. And we have evaluated the bioactivity with respect to the time frame, and you can see within 24 hours this apatite formation or the new bone formation has happened. Because this apatite formation is a preliminary indication that if it is forming the apatite, then and it has been proved by various research groups that if you go for the in vivo study in the animal model, the same way actually the apatite or calcium phosphate will directly deposit over the implant surface, so that the bone and it will lead to the bone formation. And basically, as you know, silver, although it has antibacterial activity, but in large excess actually is toxic to the body. That's why actually we try to optimize the silver concentration, that it should kill the bacteria, but simultaneously it should not kill the bone cells. So here you can see an optimization result where we have done with the scaffold surface, and you can see the MG63 osteosarcoma cell lines have grown in the silver, calcium silver containing sample. And we have gone one step ahead, that we wanted to do the mesenchymal stem cell interaction over the over this calcium or silver containing surface, and we found that the silver concentration that we have optimized has good adhesion and growth of the cell, expressing the cytoskeleton marker, which is and the DAPI, which is shown in this figure. Basically, and we follow the osteogenic differentiation or the bone formation ability or calcium deposit is happening or not, but by the MSCs that here you can see that this osteogenic differentiation is happening even in the silver containing samples. So that's actually what I would like to indicate here, that the calcium and the silver ions that we have incorporated in the samples that basically helps for the biocompatibility, bioactivity, as well as the antibacterial activity of this additively manufactured scaffold. Then when we went for this animal study of this surface modified sample compared to the unmodified sample, you can see there is a difference actually. Because of the surface modification, that new bone formation has happened directly adhering to the scaffold surface compared to the scar tissue that I showed in the beginning of our my presentation. So basically, I would like to summarize that yes, additive manufacturing is going to be that future technology where you can make any kind of customized bone implants for or patient-specific implant, because you know bone structure is different from patient to patient. So if a patient lying in the hospital and if we get the CT scan data from the surgeons or from the doctors, then we can mimic the bone structure similar to the defective bone, and then we can supply to the hospital and the doctor can do the surgery. So that is how actually the advantage of this additive manufacturing technology in biomedical field. And as I said, the process parameter plays a very vital role while developing a defect-free component, because the implant should not fail in between. Because as I said, my research group, we are working on permanent fixation implant that is going to stay in our body for 20 to 30 years. So in between this implant failure should not happen. That's actually process parameter for every system is study is very important. And the surface functionalization that I was discussing, that basically helps for additively manufactured components that could improve the biocompatibility, bioactivity, and antibacterial activity. everything. And this resultant titanium alloy basically show faster bone formation when implanted in the animal body. And I would like to acknowledge my Indian and foreign collaborator, as well as my industry partner from India and abroad, and all the funding support that I'm getting for carrying out this work. Thank you very much.
Thank you. Thank you, Prof. We still have 4 presentations. So the next presentation is from Russian Academy of Sciences, from the Siberian branch. Professor Panin, would you please start? You will have 15 minutes and 5 minutes for questions.
Okay, dear Mr. Chairman, so can you see my screen?
Yes,
yeah.
We can hear you and can see your screen.
Okay, so I would like to thank the organizers for giving this nice opportunity to share the results of our studies. In fact, I will not concentrate mostly on details on additive manufacturing process itself, but I would rather discuss the correlation between the structure that is formed under additive manufacturing and the properties of the components that are built with such an advanced manufacturing technology. So I'm going to talk about the polymers, and we will relate these studies to the medical application. However, we do not direct results of medical tests yet. So it will be a kind of prospects about the application of our results of our studies for the area of artificial joints and total replacements of the joints. So the problem itself is related to the artificial joints, and you see the key problem there is intensive wear. So it's mostly related to the knee and hip joints. And
I'm sorry. Are you changing slides?
Yeah,
we can't see the change. We can see only the first.
Okay. Okay. So let me restart. I'm sorry.
Would you please restart demonstration?
Okay. Okay.
You need to stop it. Okay.
So it's clear.
I'm not sure that you can change the slides. Would you please change the slide?
Yeah, I'm doing it.
No, we can't see it. So
okay.
you need to stop demonstrating your screen in Zoom.
Mm-hmm.
So stop, please. Yes. Okay. Now, please demonstrate the whole your screen, but not only the presentation. Use the same button for demonstration the screen, but choose to demonstrate the whole screen.
Okay. Is it changed now?
Yes. Yes. Okay.
Okay. Thank you. Great.
I'm sorry.
So that is exactly I was talking about the artificial joints, about the hard wearing of polymeric components, and you see the consequences of such a process. So here it is 14 years revision. So it's not our data. It's they're taken from the literature, but you see it is a problem. And what are the prospects there? What are the inventions in the literature? So people are talking about changing the metal polymer components into a polymeric one. And if to show this slide, you see there are several trends there. So nowadays there are several designs like ceramics on ceramics or metal on metal, and also the metal on polymer. That is the conventional one, and you see the friction coefficient there is the lowest. So, however, in this combination, metal is hard and polymer is soft. And one of the ideas there is to replace the steel covered with chromium molybdenum with some softer polymer, but which is harder than polyethylene. And following this idea, so there are some studies published in the literature. So it is offered to use hard polymer, that is polyester ketone, also loaded with carbon fibers, for instance, and also to have another part as a soft one, also produced from the same material. But as far as the trend nowadays is towards additive manufacturing, and the key advantage there is about the customized fabrication of the components, so based on the data of computer tomography. So the key idea that we are going to follow is to design and to test the tribological joint or artificial joint with one part consisting of a polyester ketone and another part consisting of ultra high molecular weight polyethylene. So the results will be shown at the end, but first we solve the key problem. And the key problem was, so the material that we deal with, that is ultra high molecular weight polyethylene. So it possesses nearly zero value of melt flow index. So it cannot be processed by extrusion. So it is necessary to modify it in order to make it extrudable and to process it by the fused deposition modeling. And in order to design such a composite, then we have to find out the optimum composition, and we need to understand its mechanical and tribological properties. So that is the aim. So first of all, we wanted to develop a soft component of this artificial joint, so to find its optimum composition, to run the test, the tribological test, and to finally combine its tribological behavior when mating with the polyester ketone, also fabricated by additive manufacturing. So here you see the equipment that were used in our studies. We use a twin screw extruder. So in order to mix the components, we use ultra high molecular weight polyethylene, that is it, and we use polypropylene as a plasticizing component. So we put them together and we extrude them in the shape of the granules of this size, and we then fabricate the samples with the laboratory scale printer that is shown there. And also, by the sake of comparison, we fabricated the plates by hot pressing, that is a standard or reference technology, just to compare what is the structure, what are the properties of samples fabricated by both techniques. And for sure, under hot compression, we are able to prepare the specimens with the near zero porosity, while under fused deposition modeling, we have to improve the printing parameters in order to obtain the lowest porosity and the highest mechanical properties. So in order to characterize the tribological performance of the specimen, we use two different schemes. So all of them are well approved in tribology. One is ball on disc, and another is block on ring. So we varied the load and the velocity there. We varied the lubrication. We used silane just as an equivalent to the synovial liquid in a human being. But I mean that is the composition of the sodium chloride solution that was used for testing, just to estimate the behavior of the polymer composites under lubricating friction. So, and here let me show first the result of comparison three various procedures to prepare the specimen. So we just mix the powders. We took a polypropylene. You see it was of a large size. So polypropylene was about 600 micrometers in diameter, while polyethylene was much smaller, about 5 to 10 micrometers. So that was the first reason why we used twin screw extruder to compound the polymers. But just to compare, we use the hot compression of the powders, and just to estimate the mechanical properties, you see that as soon as we add polypropylene, so mechanical properties, elongation and break dropped largely, and the problem will be explained in the next slide. So also after twin screw compounding, so we prepare a specimen with hot compression and with fused deposition modeling, and you see that elongation is much larger. The highest value were achieved for fused deposition modeling when the amount of polypropylene was about 30%. So here you see quite an easy explanation of the mechanical properties that is given in terms of the molecular structure. We analyzed it with scanning electron microscope. So you see when we just mix the powders, you see a large inclusion of polypropylene. You see very poor adhesion at the interface between the components. So that was the reason of abrupt drop of elongation. So, but after a twin screw compounding, you see that the structure is very uniform. And what is the most important result? So, twin screw compounding were able to provide very uniform distribution and even refinement of polypropylene. So, in the final products, the size of the polypropylene inclusions, instead of 600 micrometers in initial form, it was just about 10 micrometers. So we have a composite, ultra-high molecular weight polyethylene composite that is enforced by small polypropylene inclusions. So you see the structure, and so it characterized that because of high melting temperature and because of the high shear stresses or strains developed in a twin screw extruder, so we were able to obtain such a structure. And then we dealt with the problem of finding the optimum composition of the composite of the blends, because you see here there is no evident difference between 10 and 40%, and amount of polypropylene provided larger elongation. So then we came to tribological test. We ran them at ball on disc and on pin on ring, block on ring schemes. So here you see the results of the test, but probably more evident they are at these diagrams. So for ball on ring, we didn't reveal quite significant difference in terms of variation of polypropylene weight fraction, and but anyway, the samples prepared by fused deposition modeling by additive manufacturing was quite similar to pure polyethylene that is used nowadays for artificial joints. So it means this composite that was manufactured by fused deposition modeling possess the equal properties with the solid one prepared by hot compression. So it was very nice. And the same result was for another tribological scheme, but here we revealed even higher wear resistance for specimens prepared by fused deposition modeling. And here we see that 20% of polypropylene was a kind of better weight fraction just to provide the higher wear resistance. So here you can see the micrographs, optical micrographs that illustrate the surface of the wear track and also the surface of the counterface. So I'd rather not concentrate on this result, but I would come to the ideas of the design or optimum design of polymer composite. So what was the idea of this chapter? So since we have 9 different compositions, so we varied the content of polypropylene and we varied the number of the processing. So 0 corresponds to hot compression of the powders. So a unit corresponded to hot compression of the granules, and it's not unit, it's just 0.5, and unit corresponded to fused deposition modeling. So we make an approximation of these experimental points. So we draw the surface, and we draw this surface for Young modulus, for tensile strength, for friction coefficient, for wear rates, for elongation and break and yield strength. So we put all this surface together in a one plot, and we assigned a certain threshold for every parameter. And this green region, so it corresponds to the condition that all of the prescribed requirements, so they were true. So, and it means that if we within this green region, so it will give us the optimum composition, and it might be about, for sure, it's just fused deposition modeling, because two processing by extrusion, and here is the optimum content of polypropylene. So it made us possible to find out the composition and the processing route. So then we took this particular composition, that is 20% of polypropylene, and so we prepared the specimen by powder technology, that is hot compression, by twin screw compounding, also hot compression of the granules, and additive manufacturing of the granules. So you see here the results of measuring the wear rate for the low pressure and low load and low velocity, and high load and high velocity. So what is very nice for us, in contrast with the pure polymer, so we have quite high wear resistance, and so it means that at variation of load and speed parameters, our composite were quite stable and were even better than polymers that are nowadays applied for fabrication or manufacturing of the processes. So then we applied the lubrication. So also we compared specimen prepared by powder technology and by additive manufacturing, and we compared them at variation of load. So we assigned the load to 60, to 100 and 140 newtons, and so we just compared them, compared their tribological behavior under lubrication. So, and it was shown that, so curve number 1, it is a neat polymer, and curve number 3, it is our composite that was prepared by additive manufacturing. So in terms of wear rate, just this variation of the load, so we were the same with the wearing. So it means this composite was very stable even in silent environment, and in this condition it possesses low wear at least with the same level as the mid ultra high molecular weight polyethylene. So
I'm sorry, Prof.
Yeah.
We're out of time.
Yeah. So just to summarize, I will show 2 extra slides about the results of the testing. So we prepared the specimen from polyester ketone and specimen from ultra high molecular weight polyethylene. That is the structure of PEEK, that is the structure of polyethylene. So that was enforced with the fibers, and this was the mixture with the polypropylene, much like I described before. And here you see the results of wear test. So hot compression, so zero porosity, and additive manufacturing. So the same amount of wear that shows quite a benefit of our composite. And under the water lubrication, so we didn't register any wear in both types of composite, also because of the low friction coefficient. It just supports the ideology that we use, and it just supports that this composite and technology for its fabrication is of promise and might be used in practice. So that is it. The same ideas are shown, they are summarized in the conclusion. So let me not repeat. So thank you very much for your attention.
Okay, thank you. It's already 8 p.m. in India, but we still have 3 presentations. So the next is Dr. Mukherjee from CSIR. Am I right? Dr. Mukherjee, are you here with us?
Yeah, I'm here.
Would you please start?
Yeah, sure. Yeah, my presentation is visible?
Yes.
Yeah, okay. So thank you everyone for giving this opportunity to me. I am Dr. Mukherjee I am senior scientist in Central Mechanical Engineering Research Institute, CMERI. And my presentation will contain basically development of this similar structure of in wire arc additive manufacturing process. So basically, before I go into that, just start with the very basic things that WAM process is particularly used in wire arc additive manufacturing. Already our previous speakers discussed regarding this matter, so I am not going to details of this. Only thing is that WAM can be used as a beneficiary tool for in industry, particularly in India, and for the demonstration of prototypes, development of new products, shortening of the product life cycles, and for particularly small and medium scale enterprises, research and development, strategic industries like defense sectors, and so on and so forth. So I'm not going into details of this. I'm directly jumping into our system that we have a robotic WAM system, and we are trying to enhance these systems in a different manner. Our objective is to develop a synchronized robotic platform to deposit medium-sized component to the large-scale component. We are playing with different kind of material systems, stainless steel, aluminum, Inconel, and the combination of these materials as a dissimilar material. So that I am going to discuss in a later slide. And we are also engaged ourselves in the additive manufacturing and development of refurbishment of different components to enhance their service life. So the advantage that we get from the additive manufacturing, particularly the WAM process or the wire arc additive manufacturing process, is the directional solidification, large volume of deposition, lower material wastage, multi-material deposition is also possible, high productivity, availability of the material, because the wires are available in the welding wires, because we are using the welding wires, different category of welding wires is available, design flexibility, weight reduction of large components. So there are many advantages, other advantages of the WAM processes. What we understood from the WAM process during the last few years of working, that we can achieve the higher strength, particularly the yield strength or proof stress in low carbon steel, stainless steel, Inconel 625, Inconel 718, as well as titanium. So we can achieve better property, reduce the material wastage, generate less defect and completely solid, and completely dense parts out of the WAM deposition. So we can generate that, and these are the few collaborators who actually provided our machines, and we are collaborating with them, the few industries. So this is the beginning of our work at the very initial stage, and then we deposited few components like the clutch component that we developed. Then we used to develop the Inconel components. We just given some experimental data here. We developed different category of pressure reducing and shut-off valves that you can see in this particular picture. You can see. So there is around from the conventional machining process, there is almost around 56 to 59% of material saving, depending on the conventional machining or casting. Similarly, we have developed the cylindrical head for the cylinder development. We later developed a large cylinder of that. Similarly, we also developed the hybrid Y structure for the chassis development, chassis application for automotive industries. And then, so on, we developed lots of components of the similar component, means similar single material component. However, the WAM verticals actually having three major process, that is the process variable, then the simulation for the optimization of the stresses, optimization of the distortion, and optimization of the different parameters. Then the basically simulation before execution, that is the single step process optimization, one vertical, and the process monitoring and control, that is the third vertical that we are working with in this particular domain. So coming into the another aspect that we are working with, that is the effect of deposition path strategies. That what we find in this deposition path strategies, that people generally go for different kind of spiral path, different kind of zigzag pattern, different kind of lengthwise direction, widthwise direction, and so on and so forth. So what is I am going to tell you that in these kind of path strategies of stainless steel, particularly stainless 316L, we are getting a different kind of morphology, means different kind of phases. You can see the phase fraction here. It is shown here that FCC percentage and the PCC percentage. In this kind of percentage, you can see in the unidirectional condition, I am getting a typical kind of BCC fraction. Bidirectional, I am getting a different kind of BCC fraction. Similarly, for solid depositions like spiral deposition, lengthwise deposition, and widthwise deposition, you can see here this is the spiral deposition, lengthwise and widthwise deposition. These are basically the solid deposition, solid bulk deposition. So we are getting different kind of BCC fraction. Now we all know that this phase fraction ultimately governs the microstructural behavior as well as the mechanical behavior. So what is the idea is the tailoring microstructure. If I combine these path strategies into different aspect in the different layer, I can generate the different kind of microstructure as and when required to enhance the particular locational strength or localized strength to improve the property of the material. And that is, I will say, the microstructural engineering kind of concept that I can generate, I can enforce, I can induce microstructural development, microstructural variation into the system to enhance the property. One way it is that the anisotropy will be enhanced, but this will be beneficial for the service life of the component that we are developing. Similarly, another aspect also I can see, that is the previous one is the stainless steel. Now I can see that the Inconel also having the similar kind of behavior. You can see here that we have used two different strategies. One is the conventional bidirectional, another one is switchback. That's when we are giving a particular oscillation to and fro motion in this particular longitudinal direction, and then we are creating the deposition, and ultimately we are getting a different kind of microstructure in both the cases. If I combine these two, I will get different kind of microstructure altogether. So gamma pipe precipitate that it is forming in these two particular cases having different kind of morphology. One is the discontinuous type, another one is having an interlocking kind of nature. You can see the strength wise or the hardness wise, the behavior is also changing. The phase fraction of the gamma and gamma prime also changing in two different mode of strategies. So obviously I am changing in strategy with the same composition, same parameter, I am changing the microstructural property. So this is the kind of tailoring microstructure for the similar kind of material. So this is the one thing that for the similar kind of material, however, I am getting a dissimilar kind of behavior, not the similar kind of behavior I am generating. I am generating dissimilar kind of behavior as and when and at what portion it is required to develop. That means as per my service condition, I will develop the microstructure as and when required. So that is the one thing. Second one is that I mentioned that the feedback control mechanism or geometry monitoring is very important. So we have also worked with this geometry control monitoring with the depth camera. So in the depth camera, we have taken the measurements of the heights, widths, and all those things. And ultimately, we find it is a very nonlinear kind of equation, and we have fitted the equation into a particular nonlinear polynomial equation. From that equation, we have generated different kind of equations to control the input parameter while it is deposited, and we find out that our methodology is working, means it is giving us better control over the uncontrolled phenomena. Like you can see the open loop and proposed method. In proposed method, it is quite controlled within a particular standard deviation. Similarly, in uncontrolled condition, we are having a deviation. In this black line, you can see the open loop condition. It is having a deviation. That's means after certain deposition level, the height of the deposition is reducing. That's when there is a geometrical deviation, it is observed. So obviously this deviation ultimately leads to the higher deposition to achieve the particular or standard height. So, but control deposition, ultimately it is achieving the proper height with the same number of layer without any additional material deposition. So this is how we are also controlling the behavior. Why these things are important? Because when you are going for dissimilar thing, the severity of the deformation, severity of the stresses, severity of the thermal condition will be much more than the single material system. So therefore all these things has to be implemented into the system. So when I'm coming to the dissimilar thing, now dissimilar means there will be a dissimilar mismatch between the one material to the another material. So therefore there may be different kind of matrices between the two material or two is immiscible material, like FCC to FCC, FCC. So this is a miscible material. So obviously this kind of material will not crack. However, if there is a different kind of material like FCC, BCC and FCC microstructure, then there will be a chance of cracking at the BCC interface. Similarly, BCC, FCC, BCC material is there, then it will have a tendency to crack from the BCC side. Or BCC leaves and BCC phase is there, then this kind of material may not crack. So this kind of microstructural behavior we already observed. So this similar material can be applied in different sectors of industries like aerospace, turbine, nuclear, automobile, oil and gas sector, mining, defense, so on and so forth. So what are the problems with dissimilar material? The first thing is that finding the compatible interlayer. That means we have to find out the interlayer that we are giving to join two material, to incorporate incompatible material. We have to find the proper compatible interlayer material. That is the one problem. Second problem is the effect of process parameter. Yes, obviously the heat input, that means the heat I am providing to the material, that will create the thermal shock, that will generate the thermal stresses, that will create different kind of variable thermal distributions. So automatically the process parameter came into play. Then the optimization, obviously, because none of all the parameter domain in the deposition process is not going to give the best result. So what is the best process parameter? A very small window will be there which allows us to deposit dissimilar material or develop dissimilar material or dissimilar component. So optimization is very, very important. Then finding the interface characteristics. Because what we find that the interface characteristics is gain orientation, gain distribution, even the intermetallic formation, different sort of intermetallic formation is also impacting the strength of the interface. So finding the interface characteristics, what are the characteristics, how the intermetallic is forming and what category the intermetallic is forming, that is also very important. Then suitable mode of deposition. I already mentioned that there are different ways to deposit the material like spray mode, pulse mode, switchback mode. There are different modes of material deposition. So that is also important in case of intermetallic deposition or dissimilar deposition. And effect of heat distribution across the interface, that how I am cooling the material after one layer of deposition, how I am depositing the another material, or what kind of cooling mechanism that we are using to create that kind of dissimilar material. So that these are the all problems to be addressed when we are trying to deposit a dissimilar material. So the first thing that we tried with this SS316L to L4043 dissimilar structure with nickel 6025 buffer layer. So these are the composition of these alloy systems. We have used 304L substrate. On top of it, deposited the 316L. Then there is a buffer layer of around 5 millimeter thickness, and then we deposited L4043, and we have gone through an entire design of experiment to get out to get the different response variables like AGS, average grain size, and IMD thickness, that's mean the intermetallic thickness, and then the primary dendritic arm spacing. So we are trying to observe that how these parameters across the interface is changing, and we find out that there is a very complex behavior between these parameters. It's not a very straightforward behavior, it's a very complex behavior. So we went to the different kind of optimization technique, prediction technique, and optimization technique. We use different arrays of neural network systems to generate the prediction value, and then we validated it. When we find out that the prediction and validation is giving me better results, we divided this entire dissimilar thing into two halves. One is the SS-Ni interface, means stainless steel to nickel interface. Another one is the aluminium nickel to aluminium interface, because both of them have different kind of parametric levels or response levels. So ultimately, with this kind of prediction, we went to the toxicity analysis. For optimization, we can go to the genetical algorithm also, or any other optimization tool to generate this kind of optimization parameters, and then we optimize those parameters to a particular level for different dissimilar interfaces. And when we deposited these interfaces, we get the better result. We get the optimum parameter, and then with the optimum parameter, we get better results. And this is a typical thing that I want to show, that in case of nickel aluminum interface, because SS-Ni interface is quite stable, so that the intermediate thickness is also very minimum, and there is no cracking tendency between these two alloying elements. So therefore, that interface is quite stable. However, nickel to aluminium has a very typical kind of behavior while depositing the materials. That you can see here that there are three different categories of intermetallics that forms between the nickel and aluminium. One is Ni3Al, then there is a big array of NiAl, and the aluminium side, it is forming NiAl3. That's mean the aluminium rich intermetallic in the aluminium side, nickel rich intermetallic in the nickel side, and nickel aluminium almost 50-50 ratio in between. Now we also observe that the Ni3Al is quite coarser, quite larger, and it generally have blunt edges. So the cracks are not generally created from the Ni3Al side. The cracks are generally created from the center NiAl, or in the fine precipitates of NiAl3 side, and ultimately propagates across the interface, particularly going towards the aluminium side. However, when we get the optimum parameter, as I mentioned in previous slide, we get the better result, better strength, and better property. So this work is under review and it is going on. Similarly, however, this nickel, we have also tried with different other nickel composition, and then we also find the similar kind of optimization. So the parameter is different for different kind of nickel buffer layers or nickel alloy systems. So automatically we have optimized all those parameters for each and every single nickel interlayer conditions. Apart from that, we also tried with another material, that is Al2O3, and Al2O3 with a 325 mesh size, around 30 to 40 micron particle size. We simply deposited on the stainless steel surface, the particles deposited, and then after that we simply used aluminium to deposit the material, and we find out a very better and prominent result. In the previous condition, you can see, or I can tell you, that the aluminium side, the grains are very larger, very coarser, and that are unable to restrict the cracks when it is generated. However, in this particular case, you can see the particular condition. In particular condition, these aluminas are going towards the aluminium side and creates a very fine grain structure of a very few micron level grain structure, which actually giving the crack resistance behavior of the material. With the variation of the current level, as I mentioned, the heat input is very important. With the variation of the current level, you can see in the B or 30 amps current gives the best quality. In other cases, the growth of alumina or diffusion of the alumina is very high. It is creating large precipitates and it creating a lots of problems, and it also generates cracks. However, in 30 amps current condition with a specific heat input condition, it generating beautiful microstructure with a very beautiful property. So this is another way to create this similar kind of component for a different application. Similarly, another dissimilar kind of application that we are doing with the copper and titanium. So we are having three different kind of heat input variations. And to deposit this copper, previously in case of aluminium also and in case of copper also, we have used a particular chamber, shielding gas chamber, that we developed in-house, and the patent is pending. So we have developed this kind of chamber to resist oxygen, to interact with the aluminium and the titanium, so that oxidation or the porosity comes into the picture. So we are using those kind of chamber to deposit this kind of titanium or aluminium. In case of titanium, we also use different kind of current. We are fixing the travel speed, and then we are using different kind of current to change the heat input variation. And we also find out that at a typical current of 70 amps, in this particular picture it is showing that in the 70 amps, the interface is very fine. The intermetallic that is forming, the copper titanium intermetallic that is forming is quite low in nature, and the bonding between the two materials is quite strong compared to the other two cases like 90 amps and 100 amps. In case of 100 amps, you can see there is a interfacial cracks. So obviously 90 amps is the maximum that we can go with the process, but 70 amps, 80 amps is giving us better results. So similarly, we have analyzed those interface, particularly 70 amps. As I said, the 70 amps is better, giving better results. So we analyze with the DAX analysis, line scan, and then we find out there is a diffusion of copper and titanium into that particular interface across the interface, and that is around 20 to 30 micron in particular length. And that give us the idea that if the interface region or the intermetallic length, intermetallic thickness is less than 30 micron, then it will not give any harmful impact on the dissimilar interface. If it is going beyond, then it will give harmful impact that you can see in the particular diagram, that the phases and intermetallic lengths and diffusion length or the intermetallic length is increasing with the increase of current. And similarly, the hardness, you can see the 70 amps hardness, obviously the intermetallic hardness is quite massively high immediately, just jumping from say just below 100 to around 600. However, the 100 amps is even higher. So the cracking tendency during the deposition itself is getting bigger and bigger and bigger. So the importance of optimization of a particular parameter to deposit a dissimilar material and are finally making a particular component out of it is very, very important and very, very challenging. So that's how we can generate this kind of copper titanium component also to enhance the thermal property as well as the thermal conductivity, heat resistance property, and so on and so forth. So now with this very short glimpse about what we are doing in this particular domain of dissimilar intermetallic dissimilar component, we are also working towards the multi-robotic system that we are working with. Initially, we are working with single robotic system. Then now we are working with the double robotic system. And we are planning to put another set of robotic system to create the multi-robotic system platform. That is our, we are goaling and we are working towards that particular goal to achieve multi-robotic, collaborative robotic platform system. So for different kind of WAM deposition, dissimilar WAM deposition, big area WAM deposition, and so on and so forth. Accordingly, we are also having a plan to create a hybrid WAM process for deposition and machining in a single phase. Previously, what we are doing, we are depositing and then we are going sending the entire specimen to our CNC center or the machining center to machine it out. But we are having plans to develop this hybrid manufacturing system in the robotic itself. That's why we are going towards the 3 robot system or 4 robot system. One of them robot will be the machining robot. So they will perform the machining after deposition of the material immediately. And we have proposed, we are trying to develop this kind of collaborative, this kind of hybrid robotic additive manufacturing entire setup where the robots will have a platform, and there is a big platform where we can simply deposit the material, machining the material, and it can go out with the entire flow chain. And it will be completely cloud-based computing. That means it can be directly operated by a single operator. It will communicate between each other as we are developing the control system, also feedback and control system. So it can be monitored, it can be governed, it can be controlled by a single platform. And we are working towards this particular goal in this upcoming future. So probably I will give you a live example of this in next whenever we meet again. So thank you for listening. Thank you for giving me this opportunity for present. Thank you.
Okay, thank you. I'm sorry, we have no time for questions. We still have 2 very interesting presentations. So the next is from Institute of Silicate Chemistry, Professor Sychov. Will you please start your presentation?
Good evening, dear colleagues. now I will try to start my presentation. I will make it short, so I will skip some slides in order to save your time. My presentation is devoted to digital material science, a new concept which is developed in our university. I will skip. Так, почему не листает? Those slides which you know very well, and we'll go right to the digital material science or industry 4.0, which includes all of these components which you know very well. But in our opinion, this industry, digital industry, which is mostly was developed as a manufacturing, which is machine building, it should be complemented. To it should be added digital material science. What is digital material science then? Here are some descriptions, but I will focus on the modeling of macrostructure and properties of materials. And we'll give you one example, is a cellular structures, which are used to protect from, for example, explosions, blasts, and to protect spaceship at the landing from crashing, and to protect cars and vehicles during accidents, and so on. So major property of such materials is to absorb mechanical energy. Typical such structures may be such irregular shape or regular honeycomb structures, but we use such triplet periodic materials. They look like this. Some of them you know very well, for example, gyroid. And this is how they are crushed. You can see that they are crushed layer by layer. That is provides their good energy absorbing properties. They may be produced, for example, from plastic using selective laser sintering, FDM, and stereolithography processes. Okay. I'm sorry. This is mechanical loading curves. They are typical for energy absorbing materials. Of course, properties depend on the manufacturing technology as well as surface roughness. But what is more interesting is how to predict properties of these materials. We use approach based on skeletal graphs. That means basically nodes and ribs. So each figure may be reduced to such nodes and ribs, combination of nodes and ribs. Then there are such characteristics, for example, as total length of the arches, number of arches meeting at the nodes, fill factor, of course, and surface of the cell. Then we can suggest such a criteria which allows us to predict mechanical properties. Here is a specific strength. So we can predict properties basing on the geometry of the material. Then is interesting next step is how to develop new geometries. This was known for long ago geometries. New ones we can develop using basically nodes and ribs. Yes, this is the structure of crystals. This is electron energy distribution, and this is basically the cell. This is a cellular structure. We developed several such structures, and they show very good properties Moreover, such materials may be produced from metal and ceramics. Here is aluminium and silicon carbide diamond composite material. For that, we developed ceramics 3D printing process based on extrusion of heated slurry. Thank you for your attention.
Oh, well, you've got 10
I was
minutes.
short, right?
Okay, we have time for questions now. Thank you for your interesting presentation. You know, I've got a short question. Could you please show your previous slide? Where you show the modeling, I think, results. Yes, this is, no, that the second, the next, yes. And what is for the third picture? Is that the voids of the crystal structure? Do I understand you right?
Yes, yes. Basically, this is atoms and chemical bonds between atoms, right? This is a modeling of distribution of electronic properties. And this is basically the 3D render, 3D model of the same electron density distribution. Actually, I did not say that previous result allows us to choose perspective topologies, to choose which crystal structure to 3D print and which one will provide us a good mechanical properties using skeletal graph approach, which I described above. Thank you.
Okay. Okay, we are now on a last presentation. Dr. Mina from CSIR and MCI. Dr. Mina, are you with us?
Oh, yes, actually, there is slight change. I am Dinesh Pankaj. I'm going to present on behalf of him.
Oh, I'm sorry. Okay.
Is my screen visible to you?
Yes.
Okay. So I'm Dinesh Pankaj from Central Scientific Instrument Organization, Chandigarh in India. I am going to present applications of additive manufacturing in orthopedic and maxillofacial implants. This is the work primarily carried by Dr. Vijay Kumar Meena, who I convey his apologies that because of his some personal commitment pre-planned, he is not able to present here. So I, along with his PhD student, Mr. Prashant Kumar, is going to present the work. So I should skip this market part, but we can see that additive manufacturing in the implant, medical orthopedic implants, the market was $1.4 billion in 2019 and expected to grow for about $13 billion by 2028. And major part is the hip device segment is covering the major part. So all of us know that there are certain benefits of additive manufacturing, which are making it more suitable for orthopedic implant manufacturing. These are greater design freedom, which allows, because as we know that there are the complex anatomical structure of human organs. So additive manufacturing gives the freedom to design according to those anatomical complexities. Then the personalization, since standard implants are also available, But when the standard implants do not fulfill the need of the patient, then specific implants need to be made or designed. So this gives additive manufacturing gives edge on that part consolidation again, because of the complexity of anatomical structures. In conventional manufacturing, there may be certain parts, body parts, which need to be made in multiple parts, and while additive manufacturing gives advantages that in a single part we can construct the whole anatomy. Flexible manufacturing, again related to the greater design freedom and mechanical matching. That is because the most preferable material in implant design is titanium, which has 110 gigapascals elastic modulus, but the bones in comparison to that has elastic modulus in the range of around 2 to 6 gigapascal of the cartical bone. So again, I'm an additive manufacturing standard and patient specific segment. These are the two segments. When standard implants do not fulfill the requirement, then patient specific implants need to be made according to the specific need of the patient. So some of the examples are mandibular joint, skull cap, skull plates, and maxillofacial reconstructions. If we see that when we go for implants, the major I cannot say the drawback, but the major reason of failure is the mechanical loosening of the implant. So this basically happens again because of the high elastic modulus of the implant material in comparison to the bone. So because of that, all the stress is taken by the implant itself, and this makes the bone degrade, and hence the implant get loosened. So study about the stress shielding effect was carried out in his lab by him, where a healthy femur is aligned with the patient physiological load and muscle loading, and the model was of the 60 kg male with 5 feet 8 inch height, and again in the other experiment from the CT data, the implanted femur was extracted, and again it is loaded, is aligned with the physiological load and muscle. So the study shows that in case of healthy femur, the stress is completely taken by the femur bone itself, while in case of the implanted femur bone, the stress, there is no stress sharing by the bone, but it is completely taken by the hip stem. So if you see that the lattice structures are the clear-cut choices to match those Young's modulus of the bone. So in his lab, he has created 2 different types of lattices and achieved Young's modulus in the range of 3.2 or 3.8 gigapascal in comparison to 110 gigapascal of actual titanium material. If you can, there is a small video where it can show that the same titanium material has achieved the elastic property in it. And when this was lattice structured bar was implanted into the rabbit, so it has shown that the bone ingrowth has happened there. So other example of his work is lattice structured acitubular cup, where a cup has been designed with pore sizes in the range of 300 micron to 600 micron, because it is mimicking the bone pore size, and with average or the mean pore size is around 490 micron. So you can see the same image of both the cartical bone and cancellous bone and pore structure of lattice structure. It looks similar. So these are the different implants that he has created in his lab, developed in his lab. Another work that is being done at CSIO, Central Scientific Instrument Organization, is development of full range of augment implants required for the revision surgery. Here we can see when the implant gets loosened, so it has to be removed and revision surgery has to be carried. While removing the implant, there comes the deformities or defects in the bone. So this is the actual, human bone cup, and where this orange part shows the defect. So this need to be corrected. So buttress augments are designed to fill this gap created by the defect. So, and similarly, if the defect is more, then shell augments are required. So these full range of shell augments has been developed in his lab. He is also working for the disc degenerative disease, spinal implants for disc degenerative diseases. These are the different lattices, generate different type of lattices with which spinal cages are designed. Apart from the standard implants, he is also working on patient-specific implants, where the you can see the design cycle, where clinician comes with the CT scan of the patient, CT scan data of the patient, and then it is 3D model is reconstructed using the software available, and with that implant is designed and surgery is performed. So I will skip this. I will show a few case studies which has been carried out. This is the mucormyosis patient whose eyeball was, his actually his you can see on the left side there is an infected area where which is creating deformities in the appearance, and with the CT data, the correct side was replicated on the deforming side, and implant was designed. And this is the CT image after the implant, and it is the patient's position after 2 and 6 months. Again, this is a trauma patient who has whose zygoma floor has been damaged in an accident, and you can see that his acetabular orbital floor was damaged, and his eye was not in the proper position. So with CT image, he has created in two parts the orbital floor, and zygoma was recreated, and this is the CT of the patient after the implant and his correction in the maxillofacial area. Similarly, there was these are a few complex cases which has been done here. The patient's primary surgery was failed, and his all bone stock has been damaged. And in pre-operation operative X-ray, we can see that his pelvis, the two axes were mismatched to a great extent. So with his CT image, CT data, implant was designed, and after surgery, his pelvis axes are similarly. There are the mandibular cases. He was a cancer patient whose mandibular was completely removed. You can see in this 3D model and created with the CT image, and with the help of this, a mandibular was designed, and after surgery, this is the CAD model, but I do not have after surgery pictures. This is again a mandibular for another patient. The two mandibulars are different in the sense that here it is these spikes are given for the dental implants, while in case of second one, the structure was made in this way to create the bone growth with stem cell treatment. So after surgery, the patients, you can see the correction are like that. It is again one of the hip implant case, and this is my last slide. So this is the work basically carried out in his lab, and the facilities available in his lab includes 3D metal printer and plastic printers, apart from the post-processing machines. Thank you from my side.
Thank you. So we are now have finished the second section. Now it's time for the discussion of it. If there are any questions, please, you're welcome to discuss any presentation in this section.
Maxim, I just got the information that representatives of MISIS want to present something or to participate in a discussion. Is it right? Am I right?
Yes.
Okay,
So,
yes.
Dr. Masamba and
yes,
his colleagues will present and then start the panel discussions. Yeah, Dr. Masamba, please.
Greetings, dear colleagues. Thank you very much, Dr. Shishir, for inviting us. Very interesting presentations. We want to take a slightly different take on the technology and come to it from the point of view of education. So I would like to present National University of Science and Technology, MISIS, which specializes in metallurgy, material science, and mining. And we want to present our partner CU Systems that specializes in 3D printing equipment and various technologies. So this presentation is more to do with the collaborative perspectives of this technology that is picking up all over the world. So our university is established in the format of several institutions that take its base from the mining academy that was established in 1918, so over 100 years ago, where metallurgical department that came out in 1930s developed into a standalone institution, which now is the basis of our university, a leader in material science in Russian Federation, for sure. So the development of metallurgy from casting and transition from casting technology to powder and 3D printing has been the theme of our school for quite some years. We deploy the College of Lifelong Learning, which allows us to generate our own teaching materials, and we standardize them within the framework of the ministerial guidelines. So our institution, because it's a research institution, produces its own teaching materials, specifically in the field of metallurgy and its various applications in infrastructure development, transport, space, atomic energy, and so on. As I said, the university was established in 1918, over 100 years ago, and it had several transitions, the key transitions. So in 1962, the Moscow Institute of Steel and Alloys, this is the acronym in Russian, Moscow Institute of Steel and Alloys, MISIS, became an institute. So the metallurgy, the modern metallurgy, I would say, started this year. Then our university entered the governmental program and became the first national university of science and technology, dedicated to research, particularly in metallurgy and material science. We are the participants of the governmental program 5100 and now the priority 2030. So the research and education in the field of metallurgy is heavily supported by our governmental bodies. And at the university, we try to popularize science, popularize metallurgy and the professions in this novel applications such as 3D printing. The slogan of our university is student first, and it reflects in our academic rankings. So these are a few years back before the pandemic, we started climbing, and currently we are in the top 100 for material science and top 50 for the mining of the world ranking. When it comes to education, we are located right in the center of Moscow, few kilometers away from Kremlin, and we heavily engage with the school community. So we've developed a program of professional navigation where we start to introduce the disciplines necessary for entering into our university from school level. That is specific physical chemistry, physics, and mathematics necessary for this specialized education that is then undertaken in our schools. The implementation of occupational navigation program is done throughout with various participants around. Someone, yep, with the novel educational components and novel educational training camps around the country. So perhaps we can look at doing an international camp in 3D printing, and hope to develop some interesting projects from it. We are fully dual lingual university, so partners coming from foreign countries can study here in English language, specifically in our master's programs. And specifically for this conference, we want to advise our partners to look into advanced metallic materials program, which really is the cutting edge for research in metallurgy, developing various powders and materials for 3D printing technology. I mentioned about this. The scientific component is heavily supported by our industrial partners, and we have state-of-the-art scientific centers based at our university. But most interesting for this conference is, of course, a Center for High Complexity Industrial Prototyping, Kinetica, which is capable of producing a prototype of basically any detailed, any complexity with the full cycle of the equipment and technologies deployed, from developing of materials to the final product ready to be mass-scaled in production. We are monitored by International Scientific Advisory Council, so we are constantly updating our science in accordance with the world's best practices, and we are constantly upgrading the laboratory base in order to compete and participate in the Q1 and Q2 academic publications in these fields. At this point, I would like to pass on the word to our colleagues from CU Systems, our industrial partner, which will share the light on the possibilities of collaborative projects specifically for universities. We encourage 3D technology through education, and our partners have a full set of equipment and the materials deployment equipment for such projects within university framework and industrial applications as well. So please, Andrei from CU Systems, can you come on this virtual stage for us?
Yeah, sure. Thank you very much. Can you hear me?
Yes, yes.
Thanks a lot. So I would like to say that I'm glad to be here to have all this information, very interesting information, showing that the implementation of additive technologies are growing in the world. So as from my side, I would like to tell about the company when I'm working and our possibilities for education and laboratories. I can share a screen, I guess, right? Okay. Can you see my screen?
Yes.
That's good. Okay. So I would like to show you a small presentation. It will not take a lot of time, but we'll show you our possibilities. Okay. Yeah. Okay. Our company named SIU System, and we are leaders in Russian market industry of additive technologies. So we're supplying equipment and supplying a solution for our customers, different different fields of technologies. At the moment, we operate throughout Russia and CIC more than 40 sales representatives. It means we have a lot of partners and resellers all over the Russia. Okay. SIO System cooperates with the largest industrial and scientific research and development companies in Russia, Europe, and Asia. So it means we have a lot of experience in this and would like to share it with each company who would like to work with us. Also, SIO System leads a turnkey in additive manufacturing integration, consulting, and training projects. So welcome everyone to cooperate with us and achieve your own goals with our help and our experience. So at the moment, we have our CIC and our customers already happy to have their solution in such fields of industry as aviation, space, medicine, dentistry, shipbuilding, education, jewelry industry, of course, automotive industry, and heavy engineering. Of course, metallurgy and oil and gas. So all these fields is covered by our equipment, and in all these fields, we have customers and already have supplied a lot of equipment, which already working as a good solution to achieve the goals of our customer and lead in the technology. Okay, here we can see our partners companies. As you can see, we can see here a leader of 3D printing industries, 3D Systems company, which have a lot of headquarters in France, United States, Belgium, Israel, and other countries. 3D Ceram is the leader of 3D printing of ceramics, which came from the Ceramic University in France and have a lot of experience in making ceramics and especially in additive manufacturing ways. And also Voxeljet company, which is actually the leader, one of the leaders in producing equipment for 3D printing molds, casting molds, sand casting molds. Instack is a South Korean manufacturer of 3D printers, which working with metals. Zortrax is a Polish one, which working with plastics and resins. And Nexa 3D is a young company from the United States also, which is also making great steps in innovating resin 3D printing. Here you can see the most common 3D printers, which usually used in education and laboratories. So we can see a model from Zortrax, Nexa 3D XIP. 3D Systems represents their figure 4 machine for these fields, which work with resin. To create its small machine which already work with metals, giving us not expensive solution to print metal parts. And Atolab, this is a new equipment. It's a laboratory atomizer which gives us an opportunity to produce powders, special additive manufacturing. Okay, actually, my laptop is dead, but this actually was the last slide from my side. Thank you very much, everyone.
Okay.
Thank you very much, Andrei. That's perfect timing. That is perfect timing indeed. So, dear colleagues, I think we can share our details with the representative of Embassy of India, who invited us here, and we are open for collaborations. And please approach us. We are open. So, interested in educational partnership or research or industrial partnerships, where you are more than welcome. Thank you very much for the platform.
Actually, this last slide is very important. our director in the morning, Professor Hirani, mentioned that skill development is very important. And, you know, the devices which you had shown in the last slide from SIU systems are very important. They could be used in universities and colleges and some skill training centers. So Dr. Avik, is that correct?
Yeah, skill development is one of the major thrust area of government of India also and our institute also.
Yes.
So we are taking various measures on that, and definitely this equipments of SIU and MSIS. So definitely Mrs. Yeah. So we will start interacting.
Yes.
And we will definitely converge to something that will help both the nations.
Absolutely, absolutely. And thank you very much, SIU Systems and Mrs. for presenting this. The moderator for the last session, Professor Maxim, I'm sorry, you could take over the panel discussions, please. Both the moderators from the first and second session.
Okay.
Yes, please.
Okay, I would like also to thank my colleagues for presenting our leading educational organization and the additive technology solution. So the only few words, I would like to apologize for being too strict, meeting the timetable. That's why that is all. I think we can go to our closing speeches. So, Dr. Chatterjee, would you take?
Yeah. Thank you, Dr. Maxim. So it is already 9 o'clock in India, at 9 o'clock at night. So just I will take 1 or 2-3 minutes maximum. So since it is a really very beautiful day and we have a lot of interaction, R&D interaction from the industry, from the academia, who has shared their actual research work. That is the thing that we should appreciate. Everything that is present has been done in original work, which has been done, and knowledge has been shared. And they has been shared by many eminent speakers from India as well as from Russia. So as we think that next step, what should be the next step? So what I propose is the next logical step is to forge out the areas of mutual interest. And we should now work towards that. And once we identify the area of mutual interest between CSIR, RAS and industry, and then we can start the collaborative R&D initiative. This we have to initiate. So everybody has the email IDs of the speakers. So there may be one-to-one correspondence, there may be one-to-many correspondence through mail. And we are very hopeful that we will converge to some domains which have mutual interest and which are complementary to each other. Because in some areas we are working and we have some lacuna. Maybe in that areas, RAS scientists and professors, they have done a wonderful work. So these complementary action and complementary proposals should be there. That is, of course, my thinking. And lastly, I want to thank the organizations like RAS, Russian Academy of Science, CSR, and of course, Indian Embassy, and our industrial friends from India and Russia to actively participate and to organize this day-long hectic program. And I think we are immensely benefited in that. And lastly, I am also very much grateful from India to all the speakers who have given their time, their valuable time, and they have shared and enlightened us with their research information. And definitely it will bring some weightage and it will put into the correct direction of the entire collaborative R&D. With this brief note, I just want some words from Ina and of course from Dr. Sisi to conclude.
Thank you. Thank you very much. Well, you know, for me, it's quite difficult to judge the presentation the presentations we were listening for today, but I hope very much that they were very useful for all specialists working in the field of additive manufacturing technologies. So, and my special thanks to Dr. Avik Chatterjee and Dr. Mukherjee for their cooperation and support during the process of organizing this webinar. Thank you very much. So, Shua Shashir Shrotre.
Thank you. Thanks to Russian Academy of Science and our leading specialist from International Department, Ms. Ina Cyrus. She has done a lot of work for promoting these exchanges. And special thanks to all the distinguished experts who have participated. I'm also happy to announce that today, Russian Science Foundation and Department of Science and Technology have given approval to 26 high technology projects, and additive manufacturing is one of the areas in those projects. And you would be happy to know that a lot of principal investigators and a lot of institutes from Russian Academy of Science and Indian institutes have won these grants. So these funding grants are to the tune of around 4 to 7 million rubles per year from the Russian Science Foundation, and about 20 crore in terms of Indian rupees, up to a maximum of 20 crore for each project from the Indian funders. Similarly, we are going to announce another research call, which is from Ministry of Science and Higher Education of the Russian Federation, and also from Department of Science and Technology, India, and which is on the anvil. Another call is being launched. There's another call which is also being launched on biotechnology. Of course, the experts in this forum are not involved in biotechnology. So many of these research calls are coming, but more than these research calls, there are some technology partnerships which are very important, and you could create some virtual centers of excellence together. And these centers of excellence would be very important to forge solutions in the domain which the industry requires. So as Dr. Avik was mentioning, and many of the experts also said, that we have to combine strengths, and many strengths are there on both sides. Many researchers on both sides mentioned that they have already been collaborating, and I just mentioned that 26 more projects have been launched or approved. But besides these opportunities for funding, there are many other opportunities which the industry can also provide, and the national technology missions on both sides can provide these additional fundings. So there are in India we have national missions which are special missions for special technology areas. Similarly, in Russia also there are some national technology initiatives. So there are a lot of funding opportunities, and we should just combine and look for these opportunities also from the industry to get together and capture this emerging technology market space and create solutions together. So thank you all the distinguished experts, and thank you to those who are listening live on YouTube. Thank you, Russian Academy of Science.
Thank you. Maxim Homenko, thank you very much.
Thank you very much. Thank you.
Thank you.
Thank you, sir.
Goodbye.
Goodbye and good night.
All right. Goodbye. Good night.
Goodbye.
Thanks, everyone. Have a nice evening.
Yeah.
Thank you.